Imagine a radio system as a pair of magic boxes that can send and receive messages through the air without any physical connection. This sounds fascinating, right? Now let's break it down further with a real-world example. Think about the car radio you have likely tuned into at some point. It receives music, news, or talk shows that were broadcast from a large radio tower nearby. This interaction involves three main components. The transmitter. This is the big radio tower sending out the signals. The transmission medium. The invisible bridge that carries the signal. In this case, the air around us. Receiver. Your car radio, which catches the signals and converts them into the sound you hear. So it's like a magic, but it's all based on a science. The transmitter sends information encoded into signals through the air, and the receiver decodes these signals back into a form you can understand, like sound or data. Now here's a visual representation. Radio transmitter, air, which is signal pathway, and radio receiver. But you may ask here, what exactly is being sent through the air? It is a signal, a form of energy that carries the encoded information. What exactly is a signal? A signal is a way to transfer the information by changing some physical property. Now let's break it down with a few simple examples to make this concept crystal clear. Example number 1. This is the flashlight signal example. So, picture this. It's a nighttime, and you and a friend are on opposite sides of a wide empty field. Your friend here sometimes needs your help, but how can they let you know? They decide to use a bright flashlight. Whenever the flashlight shines in your direction, you know it's a time to head over to help your friend. In this case, the flashlight is a transmitter, sending a signal by changing the physical property of light. Your eyes are the receiver, interpreting the signal as "come help me." The simple act of turning the flashlight on and off changes the light level in a way that delivers information, making it a signal. Example 2. The telegraph signal. Now let's go back in time to the era of old-fashioned telegraphs. In the system, a transmitter on one end of a wire alternates between sending electrical current and stopping it. At the other end, the receiver creates a beeping sound when it detects the current and stays silent when there's no current. Using a system like a Morse code, where patterns of beeps and silences represent letters and numbers, people could send messages across great distances. Here, the signal is based on changing the property of electric current in the wire. In the world of software-defined radios, we focus on radio signals, which are electromagnetic in nature. You might recall that from science class that electromagnetic waves can carry energy through the air. What makes radio signals so special is that they change the properties of these waves to represent information. But don't worry if this sounds too technical. You don't need to dive into heavy physics or math to work with SDR. Instead, we will focus on what kind of information radio signals can carry. Sound. Think of AM or FM radio, which carry music or speech. Video, like the shows and news on over-the-air television broadcasts. Control information. For instance, the signal from your car key fob that locks or unlocks your car. Data, such as the internet traffic your Wi-Fi router sends to your laptop or mobile phone, and much more. And here's the interesting part. All these types of information, sound, video, data, are themselves signals. They are essential quantities that change over time. To make radio signals useful, they need a way to connect with the information they are carrying. This is where modulation comes in. So think of modulation as a clever technique for embedding information into a signal, like putting a letter into envelope before mailing it. On the receiving end, the modulation extracts the information, turning the signal back into something meaningful like music, text, or video. By understanding how signals work and how modulation transforms them, you will unlock the power of SDR to communicate all sorts of information, whether it's music, video, data, or even commands to a drone. Now let's dive deeper and see how it all comes together. Now let's take a closer look at how a basic AM radio system works. AM, amplitude modulation radio, is one of the simplest types of radio communication, making it a perfect example to explore. So imagine a transmission tower at a radio station. So here's what happens step by step. Audio source. The radio operator starts with an audio signal. This could be music or someone's voice. Carrier signal. To broadcast this audio over long distances, the audio signal needs to piggyback on a carrier signal. The carrier signal is just a steady electromagnetic wave at a specific frequency assigned to the station. In this example, the frequency is 1560 kHz or 1560 on your AM dial on your car or AM receiver. Modulation. The audio signal is combined with or modulates the carrier signal. Modulation changes the carrier signal's properties, specifically its amplitude, to represent the original sound. This modulated signal is then sent out into the air via an antenna. Transmission through air. The signal travels as electromagnetic waves, reaching all the radios tuned to that station. What happens in your car radio? Now, let's shift to the receiver side of the equation, like AM radio in your car. Tuning. When you turn the dial to 1560, the radio focuses on the carrier signal at 1560 kHz, filtering out all the other radio signals in the air like 570, 590, or 1300 kHz. Demodulation. The radio circuitry extracts the original audio signal from the modulated carrier signal. Playback. The audio signal is sent to the speakers, turning it back into the music or voice that you can hear. In our example, the carrier frequency is 1560 kHz, which determines where the station is located on your AM dial. Each station in your area broadcasts at a different frequency. These frequencies act as an unique addresses, allowing multiple stations to operate simultaneously without interference. The ability to tune into just one frequency at a time is what allows your car radio to play only the desired station, even though many other signals are flying through the air around you. The simple process of modulating a carrier wave, transmitting it through the air, and then demodulating it on the receiving end is the foundation of all radio communication, not just AM radio, whether it's a FM music, Wi-Fi, data, or satellite signal, the same basic principles are at play. In the next lecture, we will dive deeper into these signals involved in AM and FM radio and how exactly they carry sound. From there, you will start to see how radio engineers have managed to broadcast sound and data over vast distances. I'm Typhoon, and I'm waiting you in next lecture. Let's start by understanding what a signal is. A signal is like a messenger that carries information by changing something over time. These changes can happen in many ways. Air pressure, which changes in air pressure, creates the sounds you hear, like someone talking or music playing. Electric voltage. Changes in voltage allows radios and other devices to work. Radio waves, changed in electromagnetic waves, are picked up by antennas to bring sounds to your radio. Even though these signals are very different in real life, we can draw them in a similar way. So imagine using this graph here. The up and down line, vertical, shows how strong the signal is. The left to right line, which is horizontal, shows how time passes. For example, in this picture, I draw the graph of very simple sound called audio tone. This wave moves up and down smoothly, creating shape called a sine wave. This is what the sound of single beep or tone would look like. Now let's imagine a radio station wants to send this sound to listeners. How does it do that? A radio station uses something called a carrier signal to send sounds through the air. The carrier signal is another wave, as you can see here. It looks similar to the sine wave of the audio tone, but there is one key difference. Carrier wave moves much faster. So we have two signals. The sound we want to send, which is audio signal, and the wave that carries it, which is carrier signal. But these two waves are separate right now. How do we combine them so the carrier wave can deliver the audio signal to radios? The AM in AM radio stands for amplitude modulation. Now let's break that down. Amplitude means how tall or strong the wave is, its height. Modulation means changing something to add information. In amplitude modulation, we change the height of the carrier wave to match the audio wave. When the audio wave is strong, the carrier wave also becomes taller. When the audio wave is weak, the carrier wave gets shorter. This process creates a new wave called modulated signal, as you can see here. Now let's take a closer look at this modulated signal. You can see here. Now you can see the distance between the wave peaks and troughs stays the same as the carrier wave in this picture. This shows it's still the same carrier wave. Now you can look at the height of the wave's peaks. They have changed to match the shape of the audio tone from our earlier lecture. So it's like the audio signal is riding on the carrier wave. This is how AM radio sends sound waves through the air. But what about real sounds? So far we have used a simple sound, a single tone as an example, but the real life sounds like people talking or band playing music are much more complicated. Now you can see here what a real audio signal looks like. Even though it's more complex, the same rules apply. When we modulate this signal onto a carrier, the carrier wave changes its height to match the audio signal's shape. When you listen to the radio, your device performs a process called demodulation. This means it takes modulated wave and removes the carrier signal. What's left in the original wave? The music, voice, or sound you hear. So think of it like peeling a sticker of a package. The package, which is carrier wave, helps deliver the contents. Once it arrives, you put it away to reveal what's inside, which is the audio signal. Why do we need a carrier signal? So you might be wondering, why not just send the audio signal by itself? The answer has to do with how radio waves travel. The audio signal itself doesn't have enough energy to travel far, and the carrier wave acts like a booster, making it possible to send the audio signal over long distances. Now you know the very basics of AM radio, but we are just getting started. In the next lecture, we will also answer more questions. How do we pick the right carrier wave frequency? Are there other types of modulations beside AM? How can we use computers to work with signals? Stay tuned as we dive deeper into the exciting world of radio waves and signal processing. I'm Tayfun and I'm waiting you in next lecture. In our previous lectures, we have encountered signals as squiggly lines changing over time. These lines represent a real-world phenomena like sound waves, radio signals, or electrical currents. But how do we get these signals into a computer? Transforming them into digital data our software can manipulate. In this lecture, we will introduce the fascinating world of digital signal processing a field dedicated to capturing, analyzing, and reproducing signals using computers. Our focus here will be on sampling, the process of measuring the signals repeatedly over time to convert them into computer-friendly format. We will just scratch the surface of digital signal processing here, but don't worry, with a few foundational concepts, you will be ready to dive into hands-on world of software-defined radio. At its core, sampling is simply measuring. Computers require numbers to process information, and sampling involves taking a series of measurements over time to convert these analog real-world signals into numerical values. If you measure often enough and with sufficient accuracy, the resulting series of numbers will closely approximate the original signal. Each of these measurements is called a sample. Now let's start with a simple example. Imagine a signal as varying voltage on a wire. Over time, this voltage change 1.3 volts at one moment. It can be like negative 0.042 volts. The next, 110 volts after that. So, to represent this dynamic signal digitality, we must repeatedly measure the voltage, generating a sequence of numerical values that capture its changes. These measurements allow the computer to see and work with the signal. Analog to digital conversion. The device responsible for translating real-world signals into computer-readable values is called analog to digital converter. This hardware component samples the continuous analog signal and outputs a stream of digital values. Since the computers interpret the world in discrete steps, the analog to digital conversion's job is crucial in bridging the gap between analog reality and digital computation. The simplest signal you might encounter here is square wave, alternates periodically between two fixed values. Now consider a square wave that switches from 0 volts to 3 volts every second. So if you feed this signal into analog to digital converter, it will measure the voltage at regular intervals, producing a steady stream of samples. And the samples could look like this, like 0, 0, 0, 0, 3, 3, 3, 0, 0, 3, 3, 3, 3, 0, 3, 3, and so on. So visually, we can plot these samples as dots on a graph. By connecting the dots, we did approximate the original square wave. Even though the digital representation is not perfectly smooth, it captures the essential features of the signal. Now you may ask, how we can sample the sinusoids? Sinusoids, these smooth oscillating waveforms, are fundamental in SDR and many other applications. When a sinusoid is sampled, the continuous analog wave is broken into discrete dots. Although these dots only approximate the original waveform, their arrangement still reveals the sinusoid's characteristic oscillations. Now, real-world signals like audio or radio waves are often more complex. When sampled, these signals also transform into numerical streams. For instance, an arbitrary waveform might produce samples like this: 1.0, 0.6, negative 0.7, negative 1, negative 0.3, and so on. Although the sampled version might lose some of the nuances of the original waveform, it remains a reasonable representation. However, understanding what details are lost and why it requires exploring topics like sample rates and precision, we will discuss that later. Just as we can digitize analog signals using analog to digital converter, we can reverse the process with digital to analog converter, DAC. A digital to analog converter takes numerical values from a computer and converts them back into real-world analog signals. For instance, when you listen to music on your computer, the digital to analog converter translates the digital audio file into a signal that drives your headphones or speakers. In summary, while analog to digital converters digitize analog signals, digital to analog converters brings digital data back to the analog world. Together, these devices enable seamless interaction between real-world phenomena and digital technology. One critical factor in the sampling process is the sample rate, or how often measurements are taken. Sampling too slowly can result in an inaccurate representation of the signal, a phenomenon known as aliasing. On the other hand, sampling at sufficiently high rates ensure the digital version closely mirrors the original signal. We will explore sample rates and their implications in more depth later in this course. Analog to digital conversion is the gateway for real-world signals to enter the digital realm, while digital to analog conversion allows computers to output signals back into the physical world. Although this section only introduces the basics, these foundational concepts will serve you well as you begin working with SDR and other signal processing applications. For now, we will focus on understanding the flow of information, capture signals with analog to digital converter, process them in the computer, and reproduce them with digital to analog converter. I'm Typhoon, and I'm waiting you in next lecture. At the beginning of the 1990s, the global system for mobile communications triggered an unprecedented transformation in the way people communicated. Earlier analog wireless telephony systems, such as advanced mobile phone systems or Nordic mobile telephone, were limited in scope, being country-specific and used by only select few. These systems often suffered from poor interoperability and limited user capacity. In contrast, GSM, a global system for mobile communications, represented a global standard designed to facilitate compatibility across borders and cater to a far longer user base. By the late 1990s and early 2000s, GSM had been adopted worldwide and served billions of users during its peak, revolutionizing personal and business communications. This widespread adoption was largely driven by ongoing advancements in telecommunication technology, which led to significant cost reductions for both infrastructure equipment and mobile devices. Affordable devices paired with widespread network deployment made mobile communication accessible to the masses. GSM's architecture, with its scalability and adaptability, also laid the foundation for packet-switched extensions like General Packet Radio Service and enhanced data rates for GSM Evolution, which provided early mobile internet services. These systems are discussed in detail in next lectures, but moreover, GSM served as a precursor to more advanced technologies such as the Universal Mobile Telecommunications System, UMTS, and High-Speed Packet Access, HSPA, which are covered in next lectures. The journey of GSM began in the mid-1980s when the European Telecommunication Standards Institute, ETSI, initiated the standardization process. Despite its origins in this era, GSM remains in use today, demonstrating its robustness and adaptability. While its role has diminished with the rise of 4G LTE and ongoing deployment of 5G networks, GSM continues to play a crucial part in modern mobile communication systems, particularly in regions where advanced networks have not yet fully replaced older infrastructure. With the advent of 4G LTE networks, voice communications has evolved through the introduction of Voice over LTE. This service allows voice calls to be transmitted over the LTE radio network, providing superior call quality and faster connection times. However, the transition to VoLTE is still incomplete. Many devices, especially older models and some networks, lack VoLTE support. In such cases, mobile voice calls rely on flashback mechanisms reverting to GSM or UMTS networks for call handling. Additionally, the GSM and UMTS networks remain the backbone for voice telephony during international roaming. As of creating this course, only a few operators have extended their VoLTE services to support seamless roaming, leaving GSM and UMTS as critical components for global voice connectivity. Understanding GSM's architecture and evolution is vital for grasping how modern mobile networks function. Over the years, the deployment of GSM networks has undergone substantial changes. Initially, the GSM systems were designed with relatively simple structure aimed at providing basic voice services and SMS. The original architecture comprised a base station subsystem, BSS, for handling radio communications, a network switching subsystem for call routing, and operation and support subsystem, OSS, for network management. As user demands grew and the technology advanced, GSM evolved to support additional features such as GPRS for data transmission, Edge for higher speeds, and integration with IP-based services. Today, even as GSM coexists with more advanced networks, its legacy endures. It continues to be a critical fallback option, especially in rural or remote areas with limited LTE or 5G coverage. GSM's compatibility and reliability make it a valuable tool in scenarios like disaster recovery, machine-to-machine communication, and emergency services. In summary, GSM not only transformed mobile communication during its heyday, but also established the foundation for subsequent generations of wireless technology. Despite the dominance of 4G and emergence of 5G, GSM remains relevant in certain contexts, particularly for voice telephony and basic connectivity. A deep understanding of GSM's architecture, evolution, and practical applications is essential for anyone involved in the deployment and management for mobile networks today. This section will first explore the original design of GSM and then trace the significant enhancements that have shaped its evolution over the decades. Initially, GSM was designed as a circuit switch system, mirroring the structure and functionality of fixed-line telecommunication networks. In this design, a dedicated direct connection was established between two users for the entire duration of call. This connection spanned every interface between all network's nodes involved, ensuring an exclusive path for communication. While this approach guaranteed a reliable and uninterrupted link, it also meant that network resources were locked for duration of the call, even during periods of silence. Over time, advancements in technology and growing demand for more efficient communication methods led to the virtualization of physical circuit switching. Today, GSM networks nodes are typically connected through IP-based broadband connections, allowing for more flexible and efficient resource usage. And here in this lecture, you will also learn about the overview of the traditional architecture of circuit switched GSM networks, while later in this lecture, we will explore the transition to virtualized circuit switching and its benefits. The GSM mobile telecommunication network was initially modeled after circuit-switched fixed-line networks. These systems relied on establishing a direct and exclusive communication path between two parties, ensuring consistent voice quality and reliability. At the beginning of a call, the network would set up a connection between the caller and the receiver, and this path would remain dedicated to their conversation until the call ended. In this illustration, you can see the switching matrix employed in a traditional switching center. This matrix acted as the central component for routing calls, connecting the originating party to the destination party. Once a connection was established, the conversation flowed transparently through the matrix, with the switching center intervening only to clear the connection when the call concluded. And this circuit switch approach was not unique to mobile networks. Fixed-line telecommunication networks of the time also employed similar mechanisms. Initially, these networks transmitted analog signals directly between subscribers, creating a continuous electrical circuit. However, the mid-1980s saw a shift toward digital technology in switching centers, marking a significant improvement in how calls were processed. And in this new digital paradigm, analog voice signals from subscribers were digitized by the originating switching center. The digitized signals were transmitted to the terminating switching center. At the destination, the digital signals were either converted back to analog or processed digitally, depending on the type of subscriber equipment. In countries where integrated services digital network ISDN lines were popular, the entire transmission process became fully digital. And ISDN allowed for better call quality and faster data transfer rates, as it eliminated the need for analog to digital conversion during transmissions. And the conversion to analog signals occurred directly in the user's phone, ensuring seamless communication. When GSM was standardized, it reused much of the existing fixed-line telecommunication technology, such as switching centers and long-distance communication equipment, minimizing the development costs and leveraging proven technologies. However, GSM introduced a crucial innovation, the ability to wirelessly connect subscribers to the network. In fixed-line networks, subscriber connectivity was straightforward, requiring only 2 dedicated wires per user. And this simplicity was not feasible in mobile environment where users were free to move and change locations dynamically, and GSM had to address several challenges unique to mobile networks. Dynamic subscriber location. In mobile networks, the user's location could change at any time, unlike fixed-line networks where a subscriber's physical location was static. GSM required a flexible system to track and manage subscriber locations in real time. And this necessitated the development of mobility management architecture capable of routing calls to a subscriber's current location. Handoff and roaming. During a call, a subscriber might move out of the coverage area of one radio transmitter and into another, and the GSM had to ensure seamless handoffs between cells without disrupting the ongoing call. This required sophisticated software capable of dynamically adjusting the call routing. Switching center modifications. While the hardware of a mobile switching center, MSC, was similar to that of a fixed-line switching center, GSM introduced significant software changes. These changes supported functionalities such as subscriber mobility management, call handoffs, and integration with the wireless radio network. And in this figure, you can see how the same hardware could be adapted for fixed line or mobile network use through the different software configurations. Telecommunication equipment vendors like Ericsson, Nokia, Alcatel-Lucent capitalized on this versatility. They offered unified hardware platforms that could be deployed in both fixed-line and mobile networks, with the operational role determined solely by the installed software. Virtualized circuit switching. Over the years, the limitations of physical circuit switching became apparent, particularly in terms of scalability and resource efficiency. The rise of packet switching technologies like GPRS and later LTE introduced more flexible methods for transmitting voice and data. In modern GSM networks, physical circuit switching has largely been replaced or complemented by virtual circuit switching over IP-based broadband connections. This transition allows for efficient resource utilization. Network resources are allocated dynamically, reducing idle time during voice calls. Scalability. So virtualized switching can handle higher traffic volumes with fewer hardware requirements. Integration with modern networks. So IP-based systems facilitate seamless interoperability with newer technologies like LTE, and voice over IP. The virtualization of circuit switching represents a significant step forward, ensuring that GSM networks remain viable in a rapidly evolving telecommunication landscape. In the 1990s, voice calls dominated communication. However, today, a broader range of internet-based communication methods has taken precedence, with voice calls remaining important but no longer central. These newer services primarily rely on the Internet Protocol to connect users globally. Unlike traditional circuit switching, where a dedicated channel is reserved exclusively for two parties, IP-based communication uses data packets, each containing a destination address. These packets are routed independently through the network, utilizing shared high-bandwidth links that carry data for multiple users. And this paradigm shift forced network operators to maintain two separate infrastructures, a circuit switch network for voice communication and a packet switch network for internet-based services. Managing these dual networks proved costly and inefficient, prompting the replacement of the circuit switching hardware in the mobile switching centers with media gateways. And this transformation virtualized circuit switching, enabling voice calls to transmitted via IP packets. And the result was unified IP-based networks that eliminated the need for physical circuit switched infrastructure. This approach, standardized under the term Bearer Independent Core Network (BICN), streamlined operations and reduced costs. But despite this shift, the core functioning of GSM remained largely intact. But the key change occurred in the lower protocol layers responsible for call signaling and voice transmission. Over time, IP-based communication extended into GSM radio network, particularly with the advent of multi-technology-based stations supporting GSM, UMTS, LTE, and 5G NR. And today, such base stations typically connect the core network via a single IP link, simplifying infrastructure management. But for mobile devices, the GSM Air interface, the communication link between devices and the network, remained unchanged during this transition. From a user's perspective, the move from circuit switching to IP-based transition was seamless, as it primarily affected the underlying network infrastructure. The telecommunication industry is characterized by fierce competition among network infrastructure manufacturers striving to secure contracts with telecommunication operators. And to enable seamless interoperability and ensure consistent communication capabilities worldwide, the standardization of interfaces and processors is essential. And without international standards, global communication would face significant barriers. For instance, making phone calls across borders would be impractical, and operators would be locked into proprietary systems provided by the first vendor they have partnered with, severely limiting flexibility and growth opportunities. The International Telecommunication Union plays a pivotal role in defining and maintaining global telecommunication standards. And one of its most popular and influential standards discussed further in next lecture is Signaling System number 7, a protocol essential for call routing and interconnectivity between networks. However, in the early days of standardization, many ITU guidelines served only as a basic framework for the lowest common denominator, with individual countries introducing national extensions to suit their specific needs. While these extensions helped localize services, they created challenges for global equipment manufacturers who had to adapt their software and hardware to each country's unique requirements. And of course, this fragmentation led to significantly higher software development costs and integration complexities, especially when interconnecting networks from different countries. And the introduction of the global system For mobile communications, GSM marked a turning point. And for the first time, a common wireless standard was adopted across Europe. And of course, GSM's success in Europe prompted its adoption worldwide, making it the first truly global standard for mobile communication. And this widespread acceptance brought several key benefits. International roaming. Subscribers could use their devices seamlessly in any GSM network with a roaming agreement, eliminating the need for network-specific devices. It also was very cost-efficient, so manufacturers could produce hardware and software on a large scale with only minimal adjustments needed for local markets to significantly reduce research and development expenses. And it also was the interoperable, so the standardized framework enabled devices from different manufacturers to work together without issues. And the development of GSM was spearheaded by the European Telecommunication Standards Institute, ETSI, an organization responsible for creating and maintaining numerous telecommunication standards. ETSI's GSM standards are compiled into a series of technical specifications, each focusing on a specific aspect of the system, such as radio access, core networks, and interfaces. And these documents serve as a valuable resource for those seeking detailed information about GSM's architecture and functionality. The success of GSM laid the groundwork for subsequent innovations. To oversee the evolution of mobile communication, the third generation partnership project 3GPP was established as a global organization. European Telecommunication Standards Institute became one of the regional members of 3GPP, which now manages the development and maintenance of GSM, UMTS, LTE, and 5G standards. By centralizing efforts under 3GPP, the industry achieved a unified approach to advancing mobile technologies, ensuring global compatibility and reducing fragmentation. And today, all 3GPP documents are freely accessible online via ETSI and 3GPP, enabling researchers, engineers, and developers to stay updated with the latest advancements. In traditional circuit switch telecommunication networks, data transmission was organized into discrete channels. The smallest unit of transmission was the digital signal level 0, DS0 channel, which operated at a fixed speed of 64 kilobit per second. As DS0 channel could be used to transmit either voice or data, making it versatile in its applications. So instead of being referred to as speech channel, it was commonly called a user data channel, reflecting its broader utility. Higher transmission speeds were achieved by combining multiple DS0 channels. So in Europe, the standard for such aggregation was the E1 connection, while in the United States, the equivalent was T1 connection. So both types of connections relied on twisted pair of coaxial copper cables, but different in their capacities. An E1 connection had a gross data rate of 2.048 megabits per second, divided into 32 time slots, each 64 kilobits seconds in size. But one time slot was reserved for synchronization, leaving 31 time slots available for data transmission. A T1 connection offered a gross data rate of 1.544 megabit per second, divided into 24 time slots, with one reserved for synchronization and 23 time slots available for data. However, in practical deployments, some of these available time slots were allocated for signaling system number 7 signaling, further reducing the number of time slots for user data. You can see here. And so SS7 played a critical role in call setup, routing, and network management, making it an indispensable part of telecommunication networks. And for applications requiring higher capacity, an E3 connection was introduced, providing a data range of 34.368 megabit per second and supporting 512 TS0 channels. So this was achieved using advanced multiplexing techniques over twisted pair or coaxial cables. To meet the demands of long-distance communications and high-capacity networks, optical transmission systems based on the synchronous transfer mode (STM) standard were adapted. So, synchronous transfer mode offered significantly higher transmission speeds and was particularly well suited for intercity and international communication. In the illustration you can see on the screen, there's an overview of STM transmission speeds and corresponding number of TS0 channels supported. And these speeds were achieved using fiber optic cables, which offered unmatched bandwidth, reliability, and resistance to electromagnetic interference. Transition to IP-based networks. So the rise of packet switch networks brought a paradigm shift in telecommunications. So instead of using circuit switch technology with fixed channels, modern networks rely on virtual circuit switching over IP. This transition was facilitated by widespread adoption of Ethernet as a standard for IP-based communication over both the copper and fiber optic cables. Ethernet-based systems offer several advantages. High speeds, transmission speeds of 1 gigabit per second and higher are common, making them ideal for data-intensive applications. It offers cost-effectiveness as advantage, like standardized Ethernet technology enables the production of affordable network equipment, reducing overall infrastructure costs. And it also offers flexibility, so Ethernet supports both local area networks and wide area networks, making it versatile for various use cases. In modern networks, optical Ethernet links are predominantly used for interconnecting network nodes, ensuring high speed, scalable, and cost-efficient communication. The adoption of Ethernet as the de facto standard has significantly simplified network design and reduced operational complexity. For establishing, maintaining, and clearing a connection, signaling information must be exchanged between the end user and network devices. So the signaling process enables the network to manage communication sessions effectively from the moment a call or connection is initiated to its termination. In traditional fixed-line networks, analog telephones signaled their connection requests in a straightforward way. When the receiver was lifted off the hook, it indicated to the network that a connection was being requested, and the phone number was sent to the network through one of two methods. Pulse dialing, this involved the phone sending a series of electrical pulses corresponding to the dialed numbers. Each digit was represented by a specific number of pulses. And dual-tone multi-frequency, DTMF dialing, also known as tone dialing. This method used a combination of two tone frequencies to represent each number. So it was faster and more reliable than pulse dialing. With the advent of fixed-line ISDN phones and GSM mobile phones, signaling evolved significantly. So instead of relying on the same physical channel for both signaling and voice, modern systems use a dedicated signaling channel for exchanging control information. For example, information such as the destination phone number and call setup parameters are sent as digital messages through this dedicated channel, enabling faster and more efficient communication. The SS7 protocol is also integral to GSM networks and has been enhanced by the European Telecommunications Standards Institute (ATSI) to address the unique needs of mobile communication, such as subscriber mobility management, tracking and updating a subscriber's location as they move. The SS7 standard defines three primary types of network nodes that perform distinct roles. Service switching points, SSPs. SSPs are switching centers, also referred to as network elements, that handle the setup, transport, and forwarding of voice and data connections. These are responsible for initiating and terminating calls and managing the signaling required for these tasks. Service control points, SCPs. SCPs are specialized databases equipped with application software to influence the connection process. For example, in GSM networks, SCPs store the current location of a subscriber. During a call setup to a mobile user, the switching center queries the SCP to determine the subscriber's current location to forward the call accordingly. And this functionality is crucial for mobile communication and is detailed further in next sections of our course. Signaling transfer points, STPs. STPs serve as intermediates that forward signaling messages between SSPs and SCPs. Not all nodes in network are directly linked, so STPs ensure messages reach their destinations efficiently, functioning similarly to IP routers in the internet. However, unlike IP routers that handle all types of packets, STPs only forward signaling messages necessary for establishing, maintaining, and clearing calls. But the actual voice and data are carried on separate dedicated links between SSPs. The general structure of an SS7 network includes STPs, SCP databases, and SSP switching centers interconnected to enable seamless signaling and communication. The arrangement ensures that signaling messages traverse the network efficiently, even when the multiple nodes are involved. While SS7 was initially designed for circuit switch networks where a dedicated path is established for the duration of a call, it has also been adopted for virtual circuit switch networks, such as those operating over IP. In IP-based networks, signaling messages are no longer confined to dedicated time slots on an A1 link. Instead, they are encapsulated within IP packets and transmitted across the network. The adaptation allows SS7 to function in modern communication infrastructures, bridging the gap between traditional telecommunication networks and newer IP-based systems. But don't worry, in this lecture and also next lectures of our course, we will explore the SS7 protocol stack in greater detail, and we will discuss how SS7 messages are transported over IP networks, illustrating the protocol's versatility and continued relevance in evolving communication systems. So, the key takeaways from these informations is SS7 enables seamless communication by managing signaling between various network nodes. It has evolved from analog pulse and signaling to a sophisticated protocol capable of handling modern telecommunication demands, including mobile subscriber mobility. The SS7 protocol stack supports both traditional circuit switch networks and modern IP-based systems, showcasing its adaptability. The signaling system number 7 is a set of telecommunication protocols that plays a critical role in managing and controlling telecommunication networks. To understand SS7 better, we can use the well-known Open System Interconnection USI 7-layer model as a reference. The USI model provides a standard framework for describing communication protocols across different layers, which you can see in this illustration, alongside the SS7 and TCP/IP protocol stacks. And at the very foundation of the stack is MTP1, which is Message Transfer Part 1, which corresponds to the physical layer in the USI model. So this layer defines physical properties of the transition medium, such as type of cables, like copper, fiber optics, and so etc., signal levels, electrical or optical, and transmission speeds, measured in bits per second. For example, imagine you are setting up telecommunication network. The physical layer ensures that the infrastructure, like the type of cables and signal properties, meets the requirements for reliable data transmission. And moving up, the data link layer is implemented by the MTP, Message Transfer Party 2, and its primary role is to manage the framing of data into packets and ensure proper synchronization between sender and receiver. Key responsibilities include framing messages into packets. This includes marking the start and end of each packet, error detection and correction. This ensures that the error introduced during transmissions are identified and corrected when possible. So you can think of this layer as a traffic officer ensuring that all vehicles, which is data packets, have proper identification and follow their assigned routes without collision. The network layer is represented by the MTP tree, Message Transfer Part 3. This layer handles the crucial task of packet routing, ensuring the data reaches its intended destination. So functions of MTP tree include assigning source and destination addresses to packets and forwarding packets across different network nodes. Instead of IP addresses as used in TCP/IP, MTP tree utilizes point codes to identify network nodes. These point codes serve the same purpose, but are specific to the SF7 system. For example, when a call or message is transmitted, MTP3 protocol ensures it is routed to the correct telephone exchange or service. From layer 4 to 7 of the OSI model support a variety of SS7 protocols depending on the application. And here's an overview. ISUP, Integrated Services Digital Network User Part. So the ISUP protocol is used to manage call setup, control, and tear down. For instance, when a mobile subscriber, for example, party A, initiates a call to a fixed line subscriber, let's call it party B, ISUP facilitates the exchange of messages required to establish the call, alert the recipient, maintain the connection during the conversation, tear down the connection when the call ends. Now you can see the example call flow in this illustration. Party A dials party B's number. The mobile switching center of party A analyzes the dialed number and detects that it belongs to a fixed line network. Then call is forwarded. If the mobile switching center and fixed line switch are directly connected, the call can be routed directly. Otherwise, intermediate nodes such as signaling transfer points, STPs, handle the routing. The mobile switching center sends an initial address message, IM, to the fixed line switch, indicating the call number and desired channel. Then the fixed line switch sends an address complete message, ACM, back to the mobile switching center to confirm that party B is being alerted. Then conversation begins. When party B answers, the fixed line switch sends an answer message, ANM, to the mobile switching center, enabling the conversation. When either party hangs up, a release REL message is sent, followed by release complete confirmation. Signaling connection and control part. SCCP operates on layer 4 and serves a function similar to TCP/UDP in the IP world. It manages application identification and routing of non-circuit related signaling. So, by application identification, I mean it differentiates between applications running on the same node using subsystem numbers, SSNs, instead of port numbers, and a routing of non-circuit related signaling, which is essential for database access and messaging services. For example, just as TCP uses port 80 for HTTP and port 21 for FTP, SSCP uses unique SSNs to route incoming messages to applications like billing systems or voicemail services. Transaction Capabilities Application Part, TCAP, is used for querying databases in telecommunication networks. It standardizes how messages are structured and exchanged to retrieve information such as subscriber location for call routing, like via home location register, HLR, and service-specific data for applications like roaming or billing. An example use case is when you are roaming internationally. TCAP enables the system to verify your subscription details and ensure seamless connectivity. While SS7 is specifically designed for telecommunication networks, parallels can be drawn with the TCP/IP stack, which is commonly used for internet communications. MTP3 in SS7 is similar to IP in TCP/IP in routing packets, and SCCP in SS7 is very similar to TCP/UDP in TCP/IP in managing sessions and applications. And this comparison helps bridge the gap for students familiar with IP networks, making SS7 concepts more relatable. And that's it with our lecture. The SS7 protocol stack is the backbone of traditional telecommunication networks, enabling reliable signaling for calls, messaging, and database queries. So understanding how its layers correspond to the OSI model provides valuable insight into the architecture of telecommunication systems and prepares students for exploring more advanced topics like signaling security and modern IP-based telecommunication systems. I'm Tayfun, and I'm waiting you in next lecture. Thank you for watching. The GSM network utilizes additional protocols beyond the traditional SS7 protocols used in fixed-line networks. These protocols address the specific requirements of GSM communication. The Mobile Application Part Protocol, standardized in 3GPP, facilitates communication between the Mobile Switching Center and Home Location Register. The Home Location Register maintains subscriber information and is queried by the Mobile Switching Center, for example, to establish a connection to a mobile subscriber. In such cases, the Home Location Register provides information about the subscriber's current location, enabling the Mobile Switching Center to forward the call to the appropriate switching center. This process sets up a voice channel between the Mobile Switching Center and the next hop using the ISUP, which is ISDN's user part message flow, and you can see this in this illustration here. Mobile application part is also essential for communication between two mobile switching centers when a subscriber moves into a new mobile switching center's coverage area during an ongoing call. And as you can see in this illustration, the mobile application part protocol operates over the transition capabilities application part, signal and connection control part, and message transfer part protocols in the lower layers. The BSS-MAP protocol manages communication between the mobile switching center and radio network. It enables functions such as establishing a dedicated radio channel for a new connection to a mobile subscriber. Unlike mobile application part, which is database query protocol, BSS-MAP, which is base station subsystem mobile application part, interacts directly with SCCP bypassing TCAP. The direct transfer application part, DTAP, enables transparent communication between the mobile station and mobile switching center. For example, during a call setup, the mobile station sends a setup message to the mobile switching center containing details such as phone number of the called party. As the mobile switching center forwards this message without processing it, intermediate nodes do not need to understand the DTAP protocol, Direct Transfer Application Part Protocol. And in this illustration, you can see the enhancement of the SS7 protocol stack to meet the GSM requirements. Modern GSM networks employ IP-based transmission for SS7 signaling messages, replacing the traditional MTP1 and MTP2 layers with IP and transport medium specific protocols, such as Ethernet. So this adaptation is described in this illustration you can see here, which contrasts the IP-based and traditional SS7 protocol stacks. There's a key features of the IP-based stack here, for example, layer 4 protocols, M3UA, and SIGTRAN. So UDP or TCP are commonly used here, but the Stream Control Transmission Protocol, SCTP, is specified for SS7 signaling due to its ability to handle multiple simultaneous signaling connections between network nodes. And we also have the MTP3 user adaptation layer, M3UA, replicates the functionality of classic MTP3 layer, ensuring compatibility with higher layer protocols such as SCCP. This makes the transition to an IP-based stack seamless for higher SS7 protocols. And SIGTRAN. The IP-based SS7 stack is often referred to as SIGTRAN, a term derived from the IATF working group that defined these protocols. The GSM network consists of three primary subsystems. The base station subsystem, BSS, also referred to as the radio network. So the BSS contains all the nodes and functionalities required to connect mobile subscribers to the network via the radio interface, commonly called the air interface. The network subsystem, NSS, also known as the core network, includes all the nodes and functionalities necessary for call switching, subscriber management, and mobility management. Intelligent Network Subsystem, IN. The IN adds optional functionalities to the network, such as prepaid services. These services allow subscribers to found an account in advance for phone calls, SMS, and internet access. When a prepaid subscriber uses network services, the relevant IN node deducts the charges from their account in real time. The network subsystem is a crucial part of mobile communication system that manages call switching, call control, and routing between mobile switching centers, other telecommunication networks, and subscribers. The network subsystem also supports subscriber management functions such as registration, authentication, mobility management, and location updates. In this lecture, we will delve into these components and interfaces of the classic NSS, which is network subsystem architecture, and its modern IP-based network subsystem counterpart, as represented in this first and second illustrations. Each figure highlights the structure, interfaces, and nodes necessary for communication, emphasizing the evolution of these elements over time. The classic network subsystem relies on circuit switch connections using dedicated E1 lines for communication between its nodes. The key nodes and interfaces in this architecture are mobile switching center, gateway mobile switching center, base station subsystem, visitor location register, home location register, and public switched telephone network. And these elements are interconnected through standardized interfaces, which include A interface, E interface, C interface, and D interface. Each of these interfaces plays a vital role in managing call setup, routing, signaling, and subscriber information. Now let's explore each component and interface in detail. The mobile switching center is the central component of the network subsystem in a classic mobile network. It performs several key functions: call switching, call control, mobility management, and SMS handling. So the mobile switching center connects calls between mobile subscribers and also routes calls to external networks such as PSTN. And it manages call setup, routing, and teardown, ensuring smooth call establishment and termination. The mobile switching center handles mobility management tasks such as handovers when a subscriber moves between cells and location updates when no active connection exists. The mobile switching center forwards SMS messages between subscribers, so it also handles the SMS. And the mobile switch center is connected to other components of the network through specific interfaces. Now here you see the A interface. This connects the mobile switching center to the BSS, so it carries both signaling and voice data, allowing communication between mobile devices and the core network. And here in the E interface, link to the mobile switch center to other mobile switch centers, enabling handovers and call routing across different regions. This ICUP protocol establishes a speech path, while the MAP protocol handles mobility signaling. And here you can see the C interface. This is a signaling only interface between the mobile switching center and HLR, which contains subscriber information. And in the D interface, this connects the mobile switch center to the VLR, allowing temporary subscriber information to be stored locally. The gateway mobile switching center serves as an entry point and exit point for calls between mobile network and external networks such as PSTN, routing of incoming calls and routing of outgoing calls. So when a call is directed to a mobile subscriber, the gateway mobile switching center queries the HLR to determine the subscriber's current location and routes the call to the appropriate mobile switching center. But for the outgoing calls, the gateway mobile switching center acts as a bridge, forwarding the calls to the appropriate external network. The gateway mobile switching center also interacts with the VLR and HLR through the C interface and the D interface. Base station subsystem connects the radio access network to the mobile switch center. It consists of two main components. Base transceiver station, BTS. The BTS handles radio communication with mobile devices, including signal transmission and reception. And also base station controller, BSC. The BSC manages multiple BTSs, handling tasks such as radio resource management, handovers with the same mobile switching area, and traffic load balancing. And you can see this A interface between the BSS and mobile switching center enables voice and signaling traffic to flow seamlessly. The visitor location register, VLR, is a database temporarily storing subscriber information for mobile users within its coverage area. So, when a subscriber enters a new mobile switching area, their details such as IMSI, MCISDN, and current location are copied from the home location register to the visitor location register. The visitor location register supports mobility management, including location updates, authentication, and account handling. So it ensures the network knows the subscriber's current location, it verifies the subscriber's identity before establishing a connection, and it assists the mobile switching center in managing incoming and outgoing calls. The home location register. The HLR is a central database that stores permanent subscriber information, including subscriber identity, IMSI, MCISDN, service subscription details, and current location, which is associated with the mobile switching center and VLR. The home location register interacts with the mobile switching center via the C interface, as you can see here, providing subscriber data for call routing and mobility management. Public Switched Telephone Network, PSTN. The PSTN represents the traditional fixed line telephone network. The gateway mobile switching center interfaces with the PSTN, enabling calls to and from external networks. And now let's basically summarize what we have seen here. So here the A interface connects mobile switching center to base station subsystem, which carries voice and signaling. And here on the top you can see here the E interface connects mobile switching center, but actually this connects multiple mobile switching centers, supports handovers and call routing. And in the C interface, you can see on the middle of the triangle, it is signaling only link between mobile switching center and home location register. And lastly, in the D on the right bottom, you can see this connects the mobile switching center to visitor location register for temporary subscriber data. And with the advancements in telecommunications, the classic network subsystem has transitioned to an IP-based architecture. This evolution brings increased flexibility, scalability, and cost efficiency, while still retaining the fundamental functionalities of the classic network subsystem architecture. This IP-based network subsystem introduces new components and interfaces, including mobile switching center server, media gateway, serving gateway, and IP-based interfaces. And now let's examine these components and their interactions in detail. Mobile switching center server replaces the traditional mobile switching center in an IP-based network subsystem. It is responsible for call control, mobility management, and subscriber management functions, while the actual switching of voice traffic is offloaded to the media gateway, MGW. And key responsibilities of the mobile switch center server include call setup, routing and control, authentication and location updates, coordination of handovers, and management of subscriber data through interactions with visitor location register and home location register. The mobile switching center server interfaces with other components using IP-based links, as you can see on this illustration. You can see in NC interface, this connects mobile switching center server to the media gateway for signaling and call control. And you can see the C and D interfaces connect mobile switching center server to the visitor location register and home location register, ensuring subscriber data is accessed and updated. The media gateway MGW, the MGW handles the actual switching of voice and data traffic. It bridges circuit switched and packet switched networks, converting signals as needed. And here, as you can see in this illustration, the NB interface connects media gateway to the other media gateways for voice traffic exchange. And in this MC interface, this links media gateway to the mobile switching center server, enabling communication between call control and switching functions. And the separation of call control, which is mobile switching center server, and media switching, which is media gateway, MGW, enhances flexibility and scalability, as multiple media gateways can operate under the control of single mobile switching center. In modern architectures, the SGW serves as a packet data gateway, enabling the transfer of data services, for example, LTE and 5G over IP-based networks. Integration with IP networks. So serving gateway, SGW, interacts with packet core networks to route IP-based traffic, and it also helps with support for multimedia services, ensures the delivery of voice, video, and data services seamlessly. The IP-based NSS replaces traditional circuit-switched E1 links with IP interfaces, such as NC, MC, and NB, which provide higher capacity and greater flexibility. And as you can see in this illustration, the A interface at the top remains between the BSS and mobile switching center server, but may use IP for signaling. And this NB interface facilitates the media gateway to media gateway communication for media traffic. And this MC interface links mobile switching center server to media gateway for controller signaling. And this NC interface supports communication between mobile switching center server instances. The evolution of the network subsystem from a classic circuit switched architecture to an IP-based architecture reflects the growing need for flexibility, scalability, and efficiency in modern telecommunications. The classic network subsystem relied on dedicated E1 connections and centralized mobile switching centers, while the IP-based network subsystem leverages mobile switching center servers, media gateways, and IP interfaces to enhance performance and support advanced services like data and multimedia. But both architecture plays a pivotal role in ensuring call establishment, routing, and subscriber management, with the IP-based network subsystem paving the way for next-generation mobile networks such as LTE and 5G. The visitor location register is a crucial component in mobile telecommunication networks, particularly within the GSM architecture. It temporarily stores information about subscribers currently within the coverage area of a specific mobile switching center, and this setup reduces signaling between the mobile switching center and the home location register by maintaining local copies of subscriber data, facilitating efficient call setup and service delivery. Key functions of the visitor location register is subscriber data management, location tracking, service authorization, and roaming support. Subscriber data management. The visitor location register stores essential subscriber information, including the International Mobile Subscriber Identity (IMCI), mobile station ISDN number, and details about subscriber services. This data enables the network to verify and manage subscriber access to various services. As subscribers move, the visitor location register updates their location information, ensuring accurate routing of incoming calls and messages. And when a subscriber enters a new mobile switching center area, their data is transferred to the new visitor location register, and the previous visitor location register deletes the subscriber's record after a fixed period of inactivity. Service authorization. The visitor location register maintains information about the services a subscriber is permitted to use and any restrictions in place, such as banning outgoing calls while allowing incoming ones. This ensures compliance with subscriber agreements and prevents unauthorized service usage. Roaming support. When a subscriber roams outside their home network, the visitor location register collaborates with the home location register to manage roaming permissions and service continuity, ensuring seamless connectivity across different network areas. While the VLR can be implemented as a separate hardware component, it is commonly integrated as a software module within the mobile switching center. This integration is feasible because mobile switching center and visitor location register utilize different signaling connection control part SCCP subsystem numbers SSN and allowing them to operate on a single physical node. The interaction between the visitor location register and other network components is standardized through specific interfaces. In the B interface, this connects to mobile switching center to the visitor location register, facilitating the exchange of subscriber information and signaling messages. In the D interface, this connects to the visitor location register to the home location register, enabling the transfer of subscriber data when the user moves between the different mobile switching center areas. These interfaces ensure efficient communication and data management across the network, supporting seamless mobility and service delivery for subscribers. The Home Location Register is a central database in GSM networks that stores comprehensive information about each subscriber authorized to use the network. It plays a pivotal role in managing and authenticating subscribers, facilitating seamless communication and mobility across the network. Key functions of the Home Location Register is subscriber information management, authentication and security, location tracking, and service profile management. The Home Location Register maintains detailed records for each subscriber, including personal information, service subscriptions, and preferences. And this data ensures that subscribers have access to the services they have opted for and are restricted from those they haven't. And by storing the International Mobile Subscriber Identity, IMSI, and associated authentication keys, the Home Location Register verifies the identity of subscribers attempting to access the network, ensuring secure communication. The Home Location Register keeps track of the current location of subscribers by recording the identity of the Visitor Location Register or serving GPRS support node, SGSN, managing the subscriber. And this information is crucial for routing incoming calls and messages to the correct destination. And lastly, service profile management stores data related to supplementary services like call forwarding, call barring, and ensuring that ensures these services are appropriately applied based on the subscriber's profile. And these are the key functions of the Home Location Register. And the International Mobile Subscriber Identity. IMSI is a unique identifier assigned to each subscriber in a GSM network. Now, as you can see in this illustration, it consists of three parts. Mobile country code at the left. This is a 3-digit code representing the subscriber's home country. Mobile network code at the middle, MNC. This is a 2 or 3-digit code identifying the subscriber's home network within the country. And Mobile Subscriber Identification Number, MSIN. The remaining digits uniquely identifying the subscriber within the mobile network. The Mobile Station International Subscriber Directory Number, MSISDN, is the phone number associated with the mobile subscriber. Now you can see here the country code up to 3-digit representing the country. National destination code, typically 2 to 3 digits identifying the subscriber's operator or region within the country. And subscriber number, this is a unique number identifying the subscriber within the network. And how they interact with other network components. So Mobile Switching Center, MSC, the Home Location Register communicates with the Mobile Switching Center to facilitate call routing and mobility management. Visitor Location Register, when a subscriber roams into a new area, the Home Location Register provides the Visitor Location Register with the subscriber's profile to ensure service continuity. And for the Authentication Center, the Home Location Register collaborates with the Authentication Center to authenticate subscribers and secure network access. So, in summary, the Home Location Register is integral to the functioning of GSM networks, ensuring that subscribers are authenticated, their services are managed, and their location is tracked to provide seamless mobile communication. The Authentication Center is a vital component within the GSM network security architecture, responsible for authenticating subscribers and ensuring confidentiality of their communication. It works closely with the Home Location Register to manage and verify subscriber identities, preventing unauthorized access to the network services. There's two key functions of the Authentication Center, which is storage of secret keys and generation of authentication triplets. So each subscriber is assigned a unique authentication key known as key I. which is securely stored in both the authentication center and subscriber's SIM card. So the key I is never transmitted over the network, ensuring its confidentiality. And by the generation of authentication triplets, I mean during the authentication process, the authentication center generates a set of values called an authentication triplet, comprising a RAND, that is a 128-bit random number used as a challenge to the mobile device, signed response, SRES, a 32-bit response generated by applying the A3 algorithm to the RAND and key I, and key C, ciphering key. This is a 64-bit key derived using the A8 algorithm with RAND and key I, utilized for encrypting the communication between the mobile device and the network. Now you will also learn about integration with the network components, which is home location register. So the authentication center is often integrated with home location register, sharing subscriber information to facilitate authentication and service provision. And it works with the mobile switching center as well. The mobile switching center interacts with the authentication center to obtain authentication triplets and execute authentication process during subscriber access attempts. By implementing these functions and processes, the authentication center plays a crucial role in maintaining the security and integrity of GSM networks, ensuring that only authorized subscribers can access network services and their communications remain confidential. It is time to dive into GNU Radio, an incredibly powerful and open source toolkit for creating and experimenting with radios. GNU Radio allows you to design radios using a graphical interface called GNU Radio Companion (GRC), which uses a block-based programming to make radio design intuitive and accessible. With GNU Radio, you can build and test radios entirely in a software, which means no soldering, no physical circuits, just your computer. In this section, you will learn how to install GNU Radio. I will walk you through how to set up GNU Radio on your computer so you can start experimenting. You will learn how to create flow graphs. Flow graphs are essentially programs in GNU Radio. They represent the flow of data through different processing blocks in your radio system. You will use GNU Radio Companion (GRC) to build these flow graphs visually by connecting functional blocks like Lego pieces. You will also learn about input and output basics. You will learn how to feed data into your flow graphs, process it, and send it out to various destinations like speakers, files, or even antennas. And in this section, lastly, you will learn how to manipulate data. You will discover how to modify and control data within your flow graphs using simple yet powerful tools in the GNU Radio Companion interface. Back in the early days of software-defined radio, installing top-tier software like GNU Radio could be a bit of a hassle. It took a lot of time and effort to get everything set up correctly. However, thanks to the incredible progress of open source software and hard work of the contributors, those days are behind us. Today, you can install GNU Radio quickly and easily, no matter which operating system you are using. Before we dive into the installation steps, let's take a moment to talk about the best environment to run GNU Radio in. While it is possible to run GNU Radio on various platforms, the ideal operating system for the software is Linux. GNU Radio was originally developed on Linux, so it runs most smoothly on this platform. While there are now ways to install GNU Radio on Windows and Mac OS, Linux offers the most stable and reliable experience, especially when you are first starting out. Therefore, I strongly recommend running GNU Radio on Linux for the best performance. For this tutorial, we will focus on Ubuntu, a widely used Linux distribution known for its stability and ease of use. Specifically, we will be using Ubuntu 24.10 LTS, although GNU Radio is compatible with other Linux distributions and versions as well. We won't cover these here. If you are using different version of Linux, don't worry, just head to the official GNU Radio website here. GNURadio.org. Now here you can see additional information and installation guides. Now to get started with GNU Radio on Ubuntu, you will follow simple steps. The first, we will open the terminal window. And we will update our system's package list with this sudo apt update command. Enter your password. That's it. Now it is updating. That's it. Now we will need to upgrade your system to ensure everything is up to date. In order to do that, we will write sudo apt-y upgrade. That's it. Our upgrade process is done. And finally, we will install GNU Radio with this following command: sudo apt-y install GNU Radio. That's it. You might be asked to enter your password for the first command if you haven't done so recently. Once the installation is complete, you are all set. Now you can start exploring the world of SDR with GNU Radio. So while GNU Radio runs most smoothly on Linux, specifically Dragon OS, which is operating system for radio SDR, and here I have the Ubuntu 24.10. You can still use it in Windows or Mac OS. However, instead of installing the software directly on your system, which is not possible for now, the best approach is to run it inside virtual machine. So I can recommend VMware and VirtualBox for this job here. Now, here, this method allows you to install an instance of Ubuntu, the recommended Linux distribution, within a virtualized environment without needing to modifying your main operating system. In your case, it might be Windows or Mac OS. So basically, you will first need to choose your virtualization software. You will need a virtualization tool to run a Linux virtual machine on your Windows or Mac OS machine. Popular options include, as I said, the VMware or Oracle VirtualBox, which is free. VirtualBox is free and open source. Now, once you have selected your virtualization software, follow the instruction provided by the software to create a new virtual machine. So you will need also to download an Ubuntu ISO file, specifically Ubuntu latest version. I prefer. In this case, I'm using 24.10. Restart later. Now you come here, products, Ubuntu desktop, and that's it. You will need to download the ISO file from here, and after you have successfully set up the virtual machine, you will repeat the steps we did in this lecture. And while using a virtual machine does work, keep in mind that it may slightly impact performance as you're running another operating system within your primary operating system. So therefore, unless you have a specific reason to use a virtual machine, we recommend starting with Linux, especially Ubuntu, as your go-to operating system for SDR. So if running a full virtual machine feels like overkill or you're concerned about performance, another great option is to use Radio Conda. This tool allows you to install GNU Radio on your non-Linux computer without the overheat of a virtual machine. It provides a lightweight, efficient way to get started quickly, also while avoiding some of the complexity that comes with full virtualization. In the section, we have covered how to get GNU Radio up and running, whether you are using Linux, Windows, or Mac OS, by now you should be ready to dive into and start building your first SDR projects. I strongly encourage you to use Linux for the smoothest experience, and if you run into any issues along the way, don't hesitate to refer to the GNU Radio website for more detailed guides or ask me directly. With the GNU Radio installed and ready to go, you are well on your way to mastering the art of software-defined radio. Let's get started. Welcome to our introduction to GNU Radio Companion, often abbreviated as GRC, a powerful tool for building and experimenting with software-defined radio applications. GNU Radio Companion serves as the graphical user interface for GNU Radio, providing an intuitive way to design and visualize signal processing workflows without diving into complex coding. Instead of writing extensive scripts in languages like C++ or Python filled with if statements, while loops, and various function calls, GRC empowers you to construct programs visually. These programs are structured as flow graphs, where data flows seamlessly from one block to another. To launch GNU Radio Companion, open a terminal window on your system and type GNU Radio Companion. Press enter. Within a moment, the GRC interface will appear before you, a thoughtfully designed workspace that simplifies the process of creating flow graphs. Now let's break this down interface step by step to understand its key components and functionality. When GNU Radio Companion opens, you will notice several distinct areas. The first is the block menu. On the right side of the window is a comprehensive menu listing all the available blocks you can use in your flow graphs. Blocks represent different signal processing components such as sources, filters, sources, filters like this, and sinks, and other blocks, and each serves a specific purpose. The second is the central panel. The main section of the window is the workspace. This is where you will build your flow graph by dragging blocks from the menu and placing them there. Think of the workspace as your canvas for creating signal processing magic. And we also have the toolbar. Across the top, the toolbar offers essential controls. Use these icons to open existing projects, save your progress, or execute your flow graphs. Running a flow graph simulates the data flow in real time, providing immediate feedback. At the bottom of the console, which displays messages, warnings, and errors as you design and execute your flow graph. It is a valuable tool for troubleshooting and optimizing your work. To start building, simply drag blocks from the block menu into the workspace. Once placed, connect these blocks. Let's also get the multiplier. Connect these blocks by clicking and drawing lines between their input and output ports. These connections defines how data will flow through your program. After laying out the blocks, double-click on each one to configure its properties according to your specific requirements. Among the many types of blocks in GNU Radio Companion, sources and sinks are particularly crucial. The sources, for example, these blocks act as an entry point for the data. They could represent a signal generator, a file reader, or even input from a connected radio device. And we also have the sink. These are the endpoints where the processed data exits the flow graph. Examples include like audio input and audio sync, or graphical displays like digital television, and so on. And we also have the file writer, so we can write our output into a file like this. Now we are just seeing simple variables by default, options and variables, which automatically created when we started our GNU Radio Companion. The one on the left corner top is the options block that has output language Python, and we also have variable has an ID samp rate value 32,000. You can see 32K. This means 1,000. As you progress, you will gradually build more complex flow graphs, applying the concepts we discussed to create functional and innovative programs. Let's dive deeper into the fundamental components of any GNU Radio Companion flow graph: sources and sinks. These are the entry and exit point of your program, where the data flows into and out of the system, creating the backbone of your signal processing pipeline. Source blocks are where your flow graph begins. They introduce streams of data that will be processed as they travel through the connected blocks. Think back to the analog to digital examples we discussed earlier. Remember how a sequence of numbers streamed from the analog to digital converter? Yeah. Source blocks work similarly, injecting streams of data into your flow graph. One of the most essential types of source blocks is the SDR source, which pulls data directly from your software-defined radio hardware. This block lets you work with real-world radio signals. But don't worry, this comes later in your journey. For now, we will stick to the source blocks that don't require any hardware, making it easier to learn basics. There are some key source blocks you will encounter in your journey. The first is file source block. File source. This block retrieves its data from a file on your computer. For example, in this course, we have prepared a data file that mimics the behavior of real SDR hardware. You will use these files to practice streaming data into your flow graphs, building foundational skills without needing any specialized equipment. We also have a signal source block. As the name suggests, this block generates synthetic signals, including pure sinusoids. You will use it to create test signals for your flow graphs. These signals are invaluable for learning how different processing techniques affect the data. Constant source block. This is the simplest source of all. It creates a stream of identical numbers. While it might sound basic, you'll soon see how useful this block can be in certain situations, such as testing or initializing a flow graph. Just as sources bring data into your flow graph, sync blocks handle the output. Data flows through your flow graph, gets processed, and then exits through a sync block. Sync block define how your processed data is utilized, whether it is saved, visualized, or sent to hardware for further use. Similar to source blocks, some sync blocks interact with the hardware, like this SDR sync, which transmits radio signals. However, many sync blocks don't require special hardware, making them perfect for your early experiments. There are some sync blocks you will frequently use. The first is audio sync. This audio sync, this block routes data to your computer's sound card, letting you listen to processed output as audio. Whether you are tuning a radio signal or experimenting with signal modulation, hearing the result can be incredibly informative. You might also need to save the output for your analysis later, which the file sync block captures processed data and stores it in a file in your computer, ensuring you have a record of your flow graphs output. And we also have the instrumentation blocks. There are special type of sync block that don't have a direct counterparts among source blocks. Instead of sending data to hardware or files, they visualize the data in real time. For example, you can use a graphical display or observe waveforms, spectra, or other metrics as your flow graph runs. This immediate feedback is invaluable for debugging and fine-tuning your programs. That's it with our lecture. In your first flow graph, you will use both sources and sinks to see how data flows from input to output. As you gain experience, you will begin interacting more advanced blocks, including tools that interact with SDR hardware. But for now, focus on mastering the basics, using simple source and sync blocks to process and analyze data. Sources and sinks may seem straightforward, but they are the cornerstones of every flow graph you will build. By understanding their roles, you are setting a strong foundation for tackling more complex signal processing tasks. Next up, we will walk you through creating your very first flow graph, complete with instrumentation blocks as the output. Let's get started. Welcome to another lecture of Software-Defined Radio. I'm Tayfun. Much like the iconic Hello World of programming, our journey into GNU Radio begins with a simple yet foundational exercise. We will generate and display a constant signal. This project may seem basic at first glance, but it introduces you to several key concepts essential for building and running flow graphs. By the end of this lesson, you will have a clearer understanding of the foundational steps in working with GNU Radio Companion. When you open a GNU Radio Companion for the first time, it automatically presents you with a blank flow graph, a workspace where you will create and connect blocks to design your SDR projects. If for some reason you don't see a blank flow graph, don't worry, you can quickly create one by navigating to File, New, and Qt, Graphical User Interface, and that's it. Or you can also simply use the handy keyboard shortcut for Ctrl+N, and that's it. Once that's done, you are ready to dive in and craft your first SDR masterpiece. Flow graphs in GNU Radio are essentially collections of interconnected blocks, each serving a specific purpose. While you could scroll through a list of over 100 blocks to find what you need, a much faster method is using the search function. This feature saves you time and effort, especially when you know the name or even part of the name of the block you are looking for. To use the search function, click on the magnifying glass icon located near the right end of the toolbar. This action will open a search box at the top of the block list, making it easy to narrow down your options. For example, source. And here we are seeing the source. Our first goal is to create a stream of unchanging numbers and visualize them. For this, we will use the constant source block, which generates a steady stream of numbers with a fixed value. And here from the waveform generators tab, we will drag constant source here. Position the constant source block on the left side of your workspace. While it is not mandatory, this layout follows a logical flow where source blocks start on the left and data flows to sync blocks on the right. This conversion makes your flow graphs easier to read and understand. Next, you will add a throttle block to the right of the constant source. This block plays a crucial role in managing the speed of data flow through your system, ensuring your computer doesn't overwork itself unnecessarily. Without it, the flow graph might consume more resources than needed, potentially causing your machine to run harder and slower than desirable. Using the search bar to look for a throttle and drag the block into your workspace. Place it just to the right of the constant source block, creating a logical data path. To visualize the digital data stream generated by your flow graph, you will need an instrumentation block. Enter the T2 graphical user interface time sync. And don't worry about the capitalization here. Like we can also write like this, time sync, and drag into your workspace and position it to the right of the throttle block. Now your flow graph is starting to take shape and you have already taken some significant steps toward mastering GNU Radio, but this is just the beginning. Great work so far. Now it is time to bring your flow graph to life by connecting the blocks you added. Think of this step as creating a pathway for data to travel from the source, where data is generated, to the sink, where it is displayed. To connect the blocks in GNU Radio, you don't just click, you drag. Here's how to link the constant source block to the throttle block. You will move the cursor to the output port on the right side of the constant source block, labeled like out. We will click and hold and then drag a line to the input port on the left side of the throttle block, labeled in. Once the line is complete, you should release the mouse button. You should now see a connection line with an arrow pointing from the constant source block to the throttle block. This arrow indicates the direction of data flow, showing that the constant values generated by the source are being sent to throttle for processing. Now let's complete the flow graph by linking the throttle block to the key to graphical user interface time sync. Position your cursor over the output port on the right side of the throttle block. Click and drag from the throttle's output port to the input port on the left side of the key time sync, and release the mouse button to establish the connection. Well done. You will see another arrowed line, this time indicating the flow of processed data from the throttle to the graphical user interface sync for visualization. The connections in a flow graph are not just decorative. They represent the actual flow of data within your program. Each block processes the data it receives, modifies it according to its function, and then passes it along to the next block. For instance, the constant source block generates an unchanging stream of numbers. The throttle block regulates the flow of data to prevent your computer from overloading, and graphical user interface time sync receives the regulated data and displays it graphically in real time. The rows in your flow graph ensure you always know the direction in which data flows, making it easier to debug and expand your designs later. Before moving on, take a moment to tidy up your workspace. While block positioning doesn't affect functionality, a clean and logical layout makes it easier to understand your flow graph at a glance. Now use the click and drag method to reposition any block and place source blocks like the constant source on the far left of the sync blocks, like time sync on the far right, and keep the intermediate blocks like throttle in between. Like, think of this as a maintaining code hygiene for flow graph, it is easier to read and maintain a neat workspace. With all the blocks connected, your first flow graph is complete. Take a moment to admire your work. You have built a functioning SDR flow graph. This seemingly simple exercise introduces you to the core workflow of GNU Radio, adding blocks, connecting them, and creating data flows. Up to next, we will configure the settings for each block and run the flow graph. Also, we will observe the magic in action. Let's keep building your SDR expertise. Saving your work is a crucial habit when working with GNU Radio or any software really. Imagine losing your progress after all the effort you've put in. To save your flow graph, you will simply click on File in the menu bar and then choose Save, or simply press Ctrl S. And here I have a folder named Typhoonix SDR, and let's change name to sourcing.grc and save it. And here we are. Now it is time to run the flow graph and see it in action. To execute it, I will click on the execute icon on the toolbar. It looks like a play button, but if everything is set up correctly, GNU Radio Companion will compile and run your flow graph, opening a display window with the output. But if the execution button is grayed out like this, it means there's an error in your flow graph. Look for any blocks or connections highlighted in red, like in this case. These are your culprits. Red usually indicates a missing connections or misconfigured property. Fix the UG and try running the flow graph again. That's it. When your flow graph runs successfully, a window will pop up displaying a waveform. In this case, you will see a constant waveform from the value 0. If the display window seems too small like this, you can resize it by clicking and dragging its corners like this. Once you've admired your waveform, you can close the window by clicking on the X in the upper right corner. This will also stop the flow graph from running. Take a moment to appreciate this milestone. You've just executed your first SDR flow graph. Let's make things a bit more exciting. A flat line 0 isn't much to look at it. Let's modify the constant source block to produce a more interesting value. We will double click on the constant source block, and in the properties window that appears, find the constant value field and change it, let's say 3.14, a nod to our friend pi. And once it looks good, click on the apply, or you can click directly to OK to save your changes. And notice now how the constant source block in the workspace updates to reflect the new value. GNU Radio Companion automatically adjusts the block's visual representation to show its current settings. This feature is incredibly useful for quickly understanding your flow graph's configuration without diving into each block individually. Now that you've made changes, run the flow graph again by clicking the execute icon. This time, the output window will display a constant line at 3.14, but you might not see it right away. If you don't see the new line, you're probably zoomed in too much. Use your mouse wheel to scroll out until you see a second line appear in the display. The constant line at is 3.14 should be now visible. Here, you will notice another line labeled signal 2, sitting at 0. What's going on here? Welcome to the world of complex numbers. In GNU Radio, many blocks produce complex numbers, which consist of two parts, a real part and an imaginary part. Signal 1 represents the real part, and signal 2 represents the imaginary part. While complex numbers might sound intimidating, they're essential in signal processing, especially for handling frequency and phase. Don't worry, we will explore them more truly later. For now, it is enough to recognize them as a core concept in GNU Radio. Stay tuned, we are just scratching the surface of what GNU Radio can do. You've seen how to get data into your flow graph with source blocks and how to get it out with sync blocks. What do you do in between? The short answer is math. We will do a little bit of multiplying here. Now we will type multiply in the search bar and double click on the multiply const or drag and drop to add your workspace. Now the block multiplies the incoming signal by a constant value and outputs the result. Now right click in the line between the throttle and time sync, then select delete. Or alternatively, you can also just click on it and click delete. Now we will connect the throttle block's output to the input of multiply const. Then we will connect the output of multiply const to the input of time sync. By default, the multiply const block uses a multiplier of 1, meaning it doesn't change the signal. Let's test. Here, it's the same output. But let's modify this. We'll double click on the multiply const block. In the properties window, update the constant field to Q. And click OK to save your changes. And this block will now display the new multiplier in the workspace as shown here. Now we will click the execute button to run our updated flow graph. And here, when the display window appears, zoom out further by scrolling up with your mouse wheel. You will now see the signal line, and signal 1 will appear at double the previous value as shown here. While multiplying by 2 might seem basic, this exercise highlights a key concept in signal processing. Everything happening between your input and output is just a math. As you progress, you will explore more advanced mathematical operations and how they shape signals. Now, in conclusion, congratulations, you've built a flow graph that performs basic signal manipulation using GNU Radio Companion. At this stage, you have learned how to add and configure blocks, how to connect and reconfigure flow graph elements, and how to perform basic signal processing tasks. This is just the beginning. With this foundation, you are ready to take on more complex projects like building your first radio. Let's dive deeper into what GNU Radio can do. Hello everyone, I'm Typhoon, and in this lecture we will take our first steps into the exciting world of software-defined radio by building a basic amplitude modulated receiver, AM receiver. Think of it like an AM car radio, capable of receiving AM signals and converting them into audio you can listen to. However, instead of working with the live radio signals right away, we will simplify things by using pre-recorded file of captured radio data. This approach lets us focus on learning without needing any hardware just yet. You can download this file from the resources section of this lecture. And at this stage in your SDR journey, there are two key areas to focus on. The first is learning how to use GNU Radio Companion, a powerful tool for SDR development. And the second is understanding the theory behind how SDR works. In this lecture, we will concentrate on the first, getting hands-on with GNU Radio Companion. While we will touch on the radio theory later, the main goal here is to build your practical skills. So if some of the steps feel a bit like following instructions for assembling a model airplane, don't worry, this approach is intentional. As we progress through the few sections, we will revisit this AM receiver project to explore the underlying concepts in greater depth. By the end, you will not only know how to build a receiver, but also why each component works the way it does. For now, let's dive in. We will open a GNU Radio companion and let's start building your first project. Let's start by creating a new flow graph. You can do this by navigating to File, New, Key to Graphical User Interface, the first one, and that's it. Or you can simply press Ctrl N. This action will open a basic flow graph template with 2 blocks already present in the workspace. Every new flow graph begins with these 2 blocks. The option blocks, this blocks contains the fundamental settings and some documentation for your flow graph. And this variable block, this represents a variable named samp rate. So if you have worked with programming languages like C or Python, you can think of these blocks as a way to define and manage variables within the flow graph. Specifically, this samp rate relates to the sample rate for your project. So think of this as a variable in programming language. While it is not strictly required, it is considered good practice to personalize the option block with some basic information. Now we will change the title. I'll change the title to like my first, or let's AM receiver project, or like AM receiver, and we will update the description. Let's say lecture on AM receiver. Next, we will add a new block to our flow graph. Specifically, we will enter the Q2 graphical user interface entry. We'll drag and drop here, which we will use this shortly. So to locate the new blocks efficiently, you can always press Ctrl F and type the name into the search box. So your flow graph should now look like this here. Let's organize this so it looks nice. Now let's take a closer look at this Q2 graphical user interface entry block. Similar to this variable block, this entry block stores a value that can be used throughout the flow graph. However, there's an important difference. The value in this GUI entry can be modified in real time while the flow graph is running. Now it is a common practice to group variable blocks and entry blocks together at the top of the flow graph. While this makes your workspace more organized and easier to understand, it is not strictly necessary. So the flow graph will run the same way regardless of where the blocks are placed. To configure this entry block, we'll open it with double clicking on the to open its properties window, and we will change the ID field to frag, and we will set the default value to 880E3, which I will explain this right now. So now let's break this down. The notation 880E3 here is exponential notation, which stands for, let's open a notepad, which stands for 880,000. So, or for this, times 10, 3 on the like small side, like this, right? So, the part after this E represents the number of zeros added to the number before it. For example, this here we wrote means is equals to this. Similarly, this equals to Exponential notations is widely used because it makes large numbers much easier to read and interpret compared to their expanded form. Also remember this notation, it will come up frequently as you work with GNU Radio Companion. But here's the catch. If you click the apply, you will notice an error message at the bottom of the window. This happens because the default value you've entered isn't valid yet. The error message looks something like this, right? Now let's address this problem. Let's address the problem causing the error. This issue is related to data types. So far, we have learned that how flow graphs can be imagined as numbers flowing from sources through processing blocks and into sinks. However, we haven't yet explored what kinds of numbers those are. In GNU Radio Companion, just like a programming language such as Python, Java, or C++, there are different data types. Each data type determines what kind of numbers a block can work with. Now, take a look at the type property of this entry, ETU graphical user interface entry block on your screen. By the default, the type is set to integer, meaning the block can handle whole numbers like both positive to negative, like 65. Oops. Yeah, like 65, 700, like 100,000, right? 100,000. Or like positive negative numbers like 60 minus 65, like 500 or 5,000, like this. Now, this is where the issue arises. So the default value we entered earlier, this, uses exponential notation, which creates a floating point value. The floating point numbers include decimal points and look like this. For example, p, right? Or minus 8.9. Since an integer type block doesn't accept floating point numbers, the mismatch triggers an error. And now we'll open this pull down menu in this type properties, and we will change the setting from integer to float, and then click apply. This adjustment ensures that the blocks can accept the floating point value we have provided, and the error will disappear. And here you will notice that the appearance of the block in the workspace has updated to reflect the value you've entered. This feature is incredibly helpful as it allows you to quickly understand the configuration of your flow graph at a glance, even as it becomes more complex over time. Now let's add another key to GUI entry block with a different ID and the default value. Instead of creating it from scratch, we can save time by copying and pasting the existing block. The newly created block will appear in this workspace with this ID set to frag_0 by default. So we will double click on the block to open its properties. We will change the ID to center frag, and we will change the default value to 900A3 and click apply. Because this block was copied, the type here is already set to float, so there's no need to adjust that setting again. Once you are done, your flow graph should look like this. While this isn't required, it is a helpful practice to keep all variable and entry blocks grouped together at the top of the flow graph. This organization makes your workspace easier to navigate as your project grows in complexity. Hello everyone, my name is Stefan, And now let's bring some radio data into our flow graph by adding a source block. Now to start, we will locate and add a file source to our workspace. This block allows you to use a file as the radio data input for your flow graph, which means you won't need an SDR hardware to proceed. This file here contains raw radio data captured from a real airwaves by an SDR enthusiast and saved for later use. If you were building a fully functional radio receiver, you would use a different source block designed to connect with your SDR hardware. That block will provide the real-time radio data directly from the airwaves. Next, we will configure the file source block. Double-click on the block to open its properties. In the File field, click the three dots and navigate to the project files you've downloaded earlier from the resources section of this course. I will also share it on my website. And we have selected the file named 2024 AM example typhoonix.iq file. You might notice a warning at the bottom of the properties window saying the port isn't connected. Don't worry about this for now. We will address it shortly. At this stage, your property window should look similar to this. Once everything is set, we will click on OK to close the window and return to the workspace. And this is a good point to save your work. Press Ctrl S or go to File, Save. So you can use any valid Linux file name, but let's actually call it, let's say, first AM example or first AM receiver. That's it here. Now, when working in flow graphs, remember to save early and save often. This ensures you don't lose progress if something unexpected happens. From this point on, I will assume we are familiar with the basic steps for adding blocks, accessing their properties, and configuring their values. So instead of spelling out every action, we will focus on explaining what each block does and how it fits into flow graph. Let's move ahead and continue building. Now that we have set the file source, let's move on adding to blocks that will process the radio signal. Don't worry too much about understanding every detail just yet. We will delve into how these blocks works in later sections. For now, the goal is to assemble the functioning flow graph. Now we will start by adding a signal source to your workspace. This block generates a continuously repeating sequence of values that represent a sinusoidal waveform. Now double-click on the signal source block to open its properties window. Now for the frequency property, instead of entering fixed number, type center frag minus, also we need to change this to center frag. Now here signal source center frag minus frequency here and here. Now you can see, let's open again, what just happened here. Instead of putting input a static value, you enter the mathematical expression involving variables, the center frag and frag. In fact, GNU Radio Companion allows you to use almost any valid Python expression for block properties. This feature is incredibly powerful and will make your flow graphs much more flexible. In this case, the frequency of the signal source is determined dynamically by subtracting the value of the block with the ID frag from the value of the block with ID center frag. After clicking OK, you will return to workspace. Notice something interesting. The block no longer displays the mathematical expression you entered, which this needs to be 900. I forgot to save the work. Now, here, the block no longer displays the mathematical expressions you entered, right, like this. Instead, it shows the calculated result based on the current values of center frag and frag. And again, in the workspace, you'll notice that the signal source block's frequency is displayed as 20 key or 20,000. This value comes from the calculation of center frag subtract by frag. With the default values we set earlier, center frag is 900,000 and frag is 880,000. So the result of this subtraction gives us 20,000, which is exactly what we are looking for. Next, it is time to add multiply block to the flow graph. This block will combine the outputs of our two sources. It is important to be careful here and ensure that you select the correct multiply block, as there are several blocks with similar names in the GNU Radio companion library. Now, to connect the blocks, as you can see here, we need to get multiply here. So, to connect the blocks, simply click the output port of the first block, such as one of sources, and then click the input port of the multiply block. You can also click in reverse order. The connection will work either way. When connecting the inputs to the multiply block, pay attention to labels next to the input ports. You will see in 0 and in 1 labels. These are the ports where you will connect your sources. In general, the inputs are on the left and outputs are on the right. But be aware that some blocks may be rotated. Once the connections are made, your flow graph should look like this. As you continue adding and connecting blocks, it is a good practice to take a moment to tidy up the flow graph layout. This helps with readability, especially as the flow graph gets more complex. You can click and drag blocks to reposition them. And notice that the connections between blocks are sticky. So they will follow along as you move, move the blocks. So while organizing the flow graph isn't strictly necessary, to be honest, it makes them much easier to follow and understand. Now, let's proceed by adding low pass filter block. Now, this type of filter is essential in many radio signal processing workflows because it removes or reduces unwanted frequencies. Filters like this will be explored in more detail in section 6, but for now, configure the low pass filter block by setting the cutoff frag to 5E3, which is 5000, and transition width to 1E3, which is 1000. Leaving all other properties as defaults. Now, once this is set up, connect the input of the low pass filter to the output of the multiply block. After doing so, your workflow should look like this. So by following these steps, you will have successfully proceeded the signal with multiplier and filter, which is fundamental technique for many signal processing tasks in SDR applications. At this stage, you may notice that the low pass filter block's label appears in red. This happens because GNU Radio Companion actively checks your flow graph for errors as you build it. When a block has an illegal condition, its label turns red, indicating there's an issue. In this case, the problem is that the output of the low-pass filter isn't connected to anything. It is important to pay attention to these visual cues as they help you catch issues before running the flow graph. Other common causes for red labels include missing or invalid properties or connecting multiple outputs to a single input. Now, let's add AM demode block. This block will perform the critical function of demodulating the incoming radio signal, effectively extracting the audio signal that we can listen to. You can configure the AM demode block by setting its channel rate to the value of samp rate and it is audio decimation to 1. After configuring the block, you will need to connect its input to the output of the low pass filter block. When connected, your workload should appear like this. The AM demode block will now be responsible for translating the raw radio signal into something audible, allowing us to extract the audio content from the AM broadcast. So we will delve into specific of how the AM demode block operates in next sections, but for now it is essential to recognize its role in the overall system. As you continue building the flow graph, there's an important detail you should be aware of when connecting blocks. The input and output ports of each block are color-coded. For instance, the AM demode block's input port is blue, like the rest of them, while output port is orange. These colors are meaningful. They indicate that the type of data flowing through the ports. So blue ports handle complex numbers, while orange ports handle floating point numbers. At this point, we are not diving into the complexities of complex numbers, but it is important to remember this rule. Connections can only be made between ports of the same color. So if you try to connect an orange port to a blue one, the flow graph will signal an error, typically turning the connection to red. Keep this in mind as you progress. Now that we have addressed the color coding issue, let's move on to adding the rational resampler. This block plays a crucial role in adjusting the sample rate of the audio signal, ensuring it matches the requirements of your sound card. So we will set its interpolation to 32 and its decimation to 400. Once you've configured the block, connect its input to the output of AM demode block. Initially, you may notice a red arrow appear between these two blocks, indicating that something is wrong, obviously. So the issue stems from trying to connect ports of different colors, orange and blue. Just as we mentioned earlier, this is similar to trying to pass an integer where a string is expected in programming. To fix this, we will open the rational resample block's properties and change the type from complex to float to float. Real taps. After doing so, click OK, and the ports of the rational resampler block will now turn orange, and the red arrow indicating the invalid connection will change to black arrow as normal, confirming that the connection is valid. At this stage, we are very close to completing the flow graph. We have set up the sources, applied several processing blocks, and resolved the issue with the port color mismatch. However, we still need to consider one last thing. What are we going to do with the processed data? Right now, all the data flows through the blocks But we need a sync to output the final result. So we will learn that in next lecture. To output the data from your flow graph, you will need to add an audio sync block to your workspace. This block is responsible for playing the audio through your computer's sound card, allowing you to hear the broadcasted sounds. Now here's how to set it up. We will place the block into our workspace. I will set the sample rate. We'll double click the audio sync block, and in the properties window, we will set the sample rate to 32,000, which is 32 kilohertz. Now, most computer radio hardware supports the 32 kilohertz rate. However, if needed, you can tweak the flow graph to select a different sample rate. Now, we will connect the output of the rational sampler block to the input of the audio sync block, like this. By setting this up, the audio from your flow graph will be output through your speakers, allowing you to hear the domain-related signal in real time. Now, let's address one last detail. We will adjust the sample rate for the flow graph. So you may have noticed that most blocks in the flow graph have a sample rate property to 32 key or 32,000. This value corresponds to this sample rate variable, which was defined at the beginning of the project. You can modify this variable to affect the sample rate for all blocks that depend on it. Double-click on the variable block with ID sample rate, and we will change its value to 400 kilohertz, 400 E3. And that's it. After making this change, you will notice that the sample rate updates through your flow graph, impacting the sample rate for all blocks, except this final block. This is a great example of how adjusting a single variable can propagate changes through the entire flow graph design. Now it is time to run the flow graph. To do so, we will simply click the play button. And once executed, you will begin to see some text scroll by the console. After a few seconds, you should hear some music. It might come with a bit of static, as is typical with AM radios, but you should clearly hear voices and music. The audio will loop after a few seconds because the file source block is set to repeat and it doesn't contain much data. So if you don't hear anything, double check your computer speakers to ensure they are properly adjusted. Let's stop this. So if you notice choppy audio, and if you're running GNU Radio Companion in a virtual machine, you may need to tweak the audio sync properties. So open the audio sync properties window and change the device name to sys default. So if you're not using a virtual machine, however, changing the setting isn't recommended. So earlier in this project, we discussed how you can modify the key to graphical user interface entry values while the radio is running. However, if you want to change an ordinary variable block like a sample rate, you will need to stop the flow graph, adjust the value, and restart the flow graph to apply the changes. Now let's experiment with tuning to different radio station in the execution window. Okay, we had the problem here. Let's change. Okay, now let's again here. So here we will change the value, the frag here to 750 kilohertz. 1, 2, 3. And after a brief moment, you will hear a different repeating chunk of audio. That's because you tuned into a new radio station. So you can also experiment with other stations by setting the frequency to, for example, 710 or 750 again. As well as a few weaker ones like this. In this section, you've successfully built a simple AM radio receiver using GNU Radio Companion. So before we dive deeper into the mechanics, let's take a moment to peel back the layers of your radio design and look at the big picture. At a high level, your AM radio receiver flow graph accomplishes the five main things. It injects pre-recorded radio data into the flow graph. It tunes to a specific AM radio channel by filtering out the other channels. It demodulates the signal of the desired channel. It performs resampling on the signal to match the audio playback requirements, and it plays the resulting audio through your computer speakers. As you go through this project, you may have a few lingering questions. For instance, how does a filter work? What does it mean to resample? And how does multiplying a radio signal by sinusoid help in tuning? Like with this, remember? So, these are crucial questions that you will explore in the upcoming sections. By answering them, not only will you gain a deeper understanding of how your AM radio flow graph works, but you will also uncover some critical radio concepts that will prove valuable as you continue your journey into the world of software-defined radio. My name is Typhoon, and I'm waiting you in next section. Hello everyone, my name is Typhoon, and now that you are comfortable navigating GNU Radio, let's delve into foundational concepts of frequency, gain, and filters, the key elements behind the AM receiver you built in previous lectures. As you will soon discover, filters are central to almost every type of radio you will create, making it crucial to understand how they work. In physics, frequency is defined as the number of oscillations of a periodic event per unit of time. A periodic event is any action that repeats with consistent timing. Frequency is measured in hertz, Hz, where 1 hertz equals 1 cycle per second. Frequency isn't tied to any specific type of event, it is a universal property of various phenomena. For instance, frequency is integral to the radio stations you tune into, your Wi-Fi router or mobile phone specifications, the speed of your computer processors, often measured in megahertz, MHz, or gigahertz, GHz. The audible spectrum, the range of frequencies humans can typically hear, spans from 20 Hz to 20 kHz. While this range varies with factors like age and exposure to loud noise, like heavy metal concerts, it gives a broad framework for understanding sound frequencies. We have the low frequencies, which produce deep, rumbling sounds. Mid-range frequencies are where the most everyday sounds and human speech occur. High frequencies, treble, create sharp, piercing tones. Frequencies outside this range will fall into two categories. The first is subsonic and ultrasonic. Subsonic sounds below 20 Hz, too low for humans to hear, and ultrasonic sounds above 20 kHz, audible to animals like dogs, but not humans. Understanding sound frequency gives an intuitive way to grasp radio wave frequency, as many of the same principles apply. For example, just as we filter out unwanted sounds to focus on a specific conversations, radios filter signals to isolate a specific frequency channel. Let's explore frequency by creating a simple audio tone. GNU Radio treats audio data just like any other numerical data, so even though we are working with sound, it is effectively processing a stream of numbers. For this exercise, we will use GNU Radio to generate and play 500 Hz tone, providing a practical introduction to signal generation. First, we will need to create a new flow graph. In order to do that, we will open GNU Radio Companion and click on File, New Key to Graphical User Interface, the first option here. Click on it, and here we are. And we will need to add a signal source block. We will place signal source block in the workspace. We will configure the block's properties. The output type is going to be float. The frequency is going to be 500, and the amplitude is going to be 0.1. This block generates a stream of floating point numbers representing a synthetic 500 Hz signal. Now we will add audio sync block. We will drag and drop audio sync block into workspace. We will connect the output of the signal source to the input of the audio sync. And if you are using virtual machine, mostly in virtual machines, you need to set a device name property of the audio sync to sysdefault to ensure proper audio output. But if you are still getting the output without this option, this may compromise your output settings if you are even on virtual machine. So in my case, I will not change it. And we will save our flow graph. As single 500 Hz tone. Save it. And now we will run the flow graph by clicking the play button. You should hear a continuous 500 Hz tone, a mid-range sound according to the audible spectrum in here. The tone isn't practically low-pitched like bass or high-pitched treble, but comfortably in between. If you don't hear anything, ensure your speakers or headphones are properly connected. Use headphones for better audio clarity. On a virtual machine, double-check the audio sync's device name property. This hands-on experience demonstrates how audio signals can be represented numerically and generated synthetically. It also provides a starting point for understanding frequency through direct experience. In the next section, we will build on this by exploring how to combine and manipulate these signals to create more complex audio patterns. Hello everyone, my name is Tayfun, and in previous lecture, you have already heard what the 500 Hz tone sounds like through this audio sync. But now we will take the next step. We will visualize its waveform. Seeing the waveform in action not only confirms the behavior of your flow graph, but also deepens your understanding of how signals behave in the time domain. This section introduces the Q2 GUI time sync block, a powerful tool for monitoring signals. Think of it as your signals diary, showing what signal is doing at any given moment. Let's dive into the process of visualizing the tone while exploring some foundational concepts. So you might ask, what does it mean to visualize a signal? When we talk about visualizing a signal, we are referring to graphically representing the amplitude of the signal over time. This allows us to confirm the signal's behavior matches our expectations, detect unexpected distortions, anomalies, or noise, and develop an intuitive sense of frequency, amplitude, and other properties. In the case of our 500 Hz tone, the visualization will help you confirm that this signal is pure signal frequency tone represented by a sinusoidal waveform. To bring this visualization to life in GNU Radio, we will insert the GUI time sync block into your flow graph. In the block properties here, set the type to float. This ensures it processes the floating point data stream generated by your signal source. And we will attach the output of the signal source to the input of the GUI time sync. Leave the signal source connected to the audio sync so you can still hear the tone while visualizing it. And now we will run the flow graph. Let's make it big here. And along with the hearing the tone, a graphical a graphical window will appear, displaying the signal as a function of a time. In the display window, you will observe a sinusoidal waveform oscillating smoothly between the maximum amplitude of 0.1 and minimum amplitude of minus 0.1. The repeating pattern represents a 500 Hz tone, where the frequency corresponds to how many cycles or peaks and troughs occur per second. To better understand the waveform, we have three options. The first is mouse screw zoom, the second is box selection zoom, and the third is nested zooming. So let's go with the first, mouse screw zoom. You can use your mouse wheel to zoom in or out vertically, adjusting how much of the amplitude you see. And you can also click and drag your mouse to drop a box around the specific section of the waveform. When you release the mouse button, the display zooms into that region. You can repeat the box selection to zoom further into specific details, such as a single oscillation, and you can use the right mouse button to undo zoom levels incrementally, like the first right hand click, second and third. And when you zoom in far enough to focus on a single up and down segment of the waveform, you will see the classic sine wave shape. So you might ask, why does the 500 Hz tone look like a sine wave? This ties into fundamental properties of pure tones. A pure tone consists of single frequency, which mathematically corresponds to a sine wave. Here's why. The sine waves are the simplest periodic signals. In audio terms, they represent the cleanest sounds possible to devoid any harmonics or noise. Any real-world sound can be broken down into a combination of sine waves, thanks to Fourier's theory. But a single sine wave is as pure as it gets. By visualizing this tone, you are witnessing the building block of more complex signals. In real-world signal processing tasks, visualizing signals is essential for debugging, quickly spotting if something in your flow graph isn't working as expected, understanding signal behavior, developing an intuition for concepts like frequency, amplitude, and phase, and for optimizing designs, ensuring your flow graph produces the desired outputs efficiently. The combination of audio and visual feedback enriches your understanding of signal, while your ears confirm the tone's presence, and time sync confirms its purity and periodic nature. Now that we have visualized a 500 Hz tone, let's push the boundaries to explore the audible frequency spectrum. This is where things get interactive. No more stopping or restarting the flow graph every time you want to try a new frequency. Instead, we will integrate a real-time control mechanism to adjust the tone dynamically and make the experiment more intuitive. Manually editing the frequency in the signal source block, stopping the flow graph, and restarting it for every new frequency can quickly become tedious. What if you could slide between the frequencies while the flow graph is running? We will enter the GUI range block. This is a versatile tool that provides a graphical slider for real-time adjustments. And we will add this to our flow graph. And here's how you can set up your flow graph to adjust frequency dynamically. And we will put it here. This is not a variable, to be honest, but let's put here. And we will open its properties. We will set the ID to frag. So you will use this ID later in the signal source. Default value to 500. Start we will set to 100 Hertz. This is the lowest frequency you can select. The stop to 32,000, so 32 kilohertz. This is the highest frequency you can select. And the step, let's set to 100 Hertz. This is the increment value for each slider tick. And we will click on apply. Okay. In the signal source block, we will replace the static frequency value to frag. This one. This is the matching the ID with this GUI range. Click on apply. Okay. And keep the signal source connected to time sync for visualization and audio sync for playback, for hearing sounds. Once you execute the flow graph, a graphical user interface window will appear with two main elements: a sinusoidal waveform display in the time sync block and a slider from the range that lets you adjust the frequency in real time. As you move the slider, let's actually as you move the slider, so as you move the slider, the tone's pitch will change dynamically. The waveform in the time sync will adjust, oscillating faster or slower depending on the frequency. And let's analyze what happens as you interact with the slider. You will notice let's actually close it and change the value a little bit. So we will start widget. Let's actually start to 10 Hertz and step to, let's say, 10. Let's start it. And here we are. Now we will go below the 20 Hertz. Here. You will notice this slow moving sinusoid in the time sync block. However, you won't hear much because these frequencies are below the human auditory range you learned in previous lectures. And let's go, as you know, human hearing range is from 20 Hertz to 20,000 Hertz. As you increase the slider value, The tone pitch rises and the waveform oscillates faster. Most humans can hear the tones up to 16 hertz. To be honest, I'm not hearing this, depending on and that also it depends on age and hearing ability. And beyond the 20,000, let's say 25,000, right? Oh. While this time sync will still display its waveform, your sound card or speakers may struggle or even like uh, to produce these tones accurately. So what we are hearing is not 25 hertz, 25,000 hertz sound. It's what our speakers are struggling to. And if it will be 25,000 hertz sound, we won't hear it. So while this time sync will still display this waveform like this, it's here. And you might also observe the aliasing effects where the tone's pitch unexpectedly drops instead of rising here. So this occurs because of aliasing, a fundamental concept in signal processing. Here's a simplified explanation. The sample rate of your flow graph is, let's say, 32 kilohertz, like this, meaning the system captures 32,000 samples per second. According to Nyquist theorem, the maximum frequency you can accurately represent is half the sample rate. In this case, it is about 16 kilohertz. And frequencies above this threshold appear as lower. Let's see, like this. Oops. Here. And also it appears lower and aliased frequencies due to undersampling. And aliasing is a key reason why high fidelity audio and precise signal processing require adequate sampling rates. It underscores the importance of choosing a sample rate that's at least twice the highest frequency of interest. And at this point, you might be wondering, what's the big deal about frequency? Here's why it's critical. Signal identification. Frequencies are unique identifiers for signals. For example, radio stations are assigned to specific frequencies. It also matters for filtering. By isolating certain frequencies, you can remove noise or extract desired signals. And also communication. Frequency manipulation is the basis of technologies like AM, FM radio, Wi-Fi, and cellular networks. Whether you are working with audio, radio, or even medical signals, understanding and controlling frequency is fundamental. Before diving deeper into frequency manipulation, it is worth mentioning that all these concepts tie into a larger framework called frequency domain. While we've been visualizing signals in the time domain, amplitude versus time, many real-world applications analyze signals in the frequency domain, which is amplitude versus frequency. This standardization will unlock powerful tools for signal processing, but for now, keep experimenting with your frequency slider to build a strong intuition about how signals behave. This range block doesn't just make frequencies adjustment easier, it also bridges the gap between theory and hands-on experimentation. By dynamically controlling the frequency, you have experienced the interplay between pitch, waveform, and aliasing. Keep these principles in mind as you move forward. Frequency is one of the most powerful tools in your signal processing toolbox. I'm Typhoon, and I'm meeting you in the next lecture. Hello everyone, I'm Typhoon. In our previous lectures of this section, we have explored how signals behave in the time domain, where the x-axis represents time and the graph shows how the amplitude of a signal varies over time. Now, while this perspective is useful, it's not always the most informative way to understand complex signals like music, speech, or radio transmission. Many real-world signals are composed of a mix of frequencies that evolve simultaneously. To dissect these goals, we need a new lens, the frequency domain. The frequency domain is a way of visualizing signals by plotting frequency on the x-axis instead of a time. So instead of showing the signal's shape, the graph shows which frequencies are present and their relative strengths or amplitudes. This view allows us to break down complex signals into their consistent frequencies. For example, a pure tone, like the one generated here and earlier in this section, this will appear as a single spike in the frequency domain, corresponding to its specific frequency. A complex sound like a music chord or rumbling bass will appear as a multiple spikes or spread of frequencies, showing the mix of frequencies that create the sound. This concept extends beyond audio radio signals. Electromagnetic waves and even biological signals can all be analyzed in the frequency domain. Let's take an example of a music. A bass guitar produces low-pitched sounds in the frequency domain. You'd see the spike at the lower frequencies. A flute produces high-pitched sounds, resulting in spikes at higher frequencies, like this. A full orchestra produces a complex mix of low, mid, and high frequencies, all visible as a rich pattern in the frequency domain. By visualizing these signals, we can distinguish their components. For instance, even though the subwoofer's rumbly bass and vocalist melody overlap in the time domain, they are clearly separable in the frequency domain. To visualize signals in the frequency domain, we need a mathematical tool that analyzes the signal and extracts its frequency component. This tool is the Fourier transform, named after the mathematician Joseph Fourier. So you might ask, what does the Fourier transform do? The Fourier transform takes a signal, a varying amplitude over time, and breaks it into constituent frequencies. For instance, a single sinusoidal wave translates to a single frequency spike. A complex wave translates to a spectrum of frequencies. In simpler terms, it answers the question, what frequencies are present in the signal and how strong are they? The discrete Fourier transform, DFT. Since SDRs and modern systems use sampled, which digital data, we rely on the discrete Fourier transform, DFT, which performs the same operation as the Fourier transform, but on a discrete data points. Fast Fourier transform, FFT. The FFT is computationally efficient algorithm to compute the DFT. It is widely used in software-defined radio systems because of its speed and reliability. In an SDR, the process of analyzing a signal in the frequency domain typically follows 3 steps. The first is signal sampling. The SDR captures a continuous radio signal and converts it into discrete samples. Fourier transform. The sampled signal is processed using an FFT, revealing its frequency components. Third is the visualization. The frequency data is plotted, showing the strength of each frequency component. By analyzing the frequency domain, you can identify active frequencies like radio channels, filter unwanted signals or noise, extract useful information from a crowded spectrum. This capability is what makes SDRs so powerful. They can isolate, identify, and manipulate signals with remarkable precision. To further deepen our understanding of the frequency domain, let's visualize a simple tone's frequency spectrum using a flow graph. This will allow us to simultaneously observe how the signal behaves in both the time domain and the frequency domain. And here we will start with our existing project we created in our previous lecture. We will open the flow graph you created previously, and let's save it under a new name. Let's name it the signal tone FFT. Okay, save as ffd.grc. This ensures you can work on this variation without losing your earlier one. We will add Qt GUI frequency sync block. We will insert this frequency sync block into the flow graph, and here this block computes and displays the FFT of the connected signal, showing the frequency components in real time. And here we will link the signal source block to the frequency sync block. And here, when you connect these blocks, you will notice a red arrow indicating a mismatch in input and output types. And to fix this, we will set the type parameter of the frequency sync block to a float. And we will also set the spectrum width parameter to half. Let's save this, click OK, and that's it. And we will verify the flow graph layout. The flow graph should now resemble this, a combination of the signal source, graphical user interface blocks for the time domain and frequency domain. And when we run it, here, it's also for the and that's it. And when we executed this flow graph, you should see a time domain plot, the frequency domain plot. Here you can see that displaying a spike representing the tone's frequency. And the frequency slider, which you can use to adjust the tone's frequency in real time. Here, 8.16, it's the same. Initially, you will notice here, if I put it to the start, and here you will notice a single spike in the frequency domain plot near the left side, corresponding to signal's frequency. In this case, the default is 0.5 kilohertz, and here, if we go to there, we can see the 0.5 kilohertz minus 33.55 decibels. Now, to get a clear view of the spike, we will zoom in by clicking and dragging a box around the spike, and you will find the spike located precisely at 0.50 kilohertz, which corresponds to 500 hertz. Here, the time domain plot reveals how the tone oscillates as a sinusoid over time, and this frequency domain plot derived using the FFT simplifies this view by isolating and showcasing the dominant frequency or frequencies in the signal. This dual visualization highlights how the same signal can be represented in two different domains, each offering unique insights. The frequency domain plot provides a clear view of the dominant frequency in a signal, in this case 500 Hz, which aligns with the default frequency of the signal source. However, you might notice that the peak in the plot isn't perfectly sharp. Now let's dive deeper to understand why this happens and how we can refine it. And here, the spike in the frequency plot appears at 500 Hz. But it's not isolated to an exact point. Instead, it shows some signal presence between approximately 400 Hz and 600 Hz. So this spread isn't because the tone contains multiple frequencies, rather it's due to the approximate nature of the FFT algorithm. The fast Fourier transform isn't an exact representation. It's a numerical approximation with inherent limitations influenced by parameters like FFT size and windowing. To validate and refine the frequency domain plot, we will need to access the FFT control panel. We will use middle mouse button or on the scroll wheel to click anywhere in the frequency plot. In the context menu that appears, we will select the control panel. And here we will locate the FFT size drop-down menu in the control options. And you will see values ranging from the 32 to 32,768. And we will change the FFT size to 4,096. And here, after increasing the FFT size, we will zoom back into the spike using this click and drag zoom. And here the spike at, let's zoom it better. So the spike at 500 Hz will now appear narrower, spanning approximately like 470 Hz to 530 Hz. A larger FFT size results in a more accurate and sharper frequency representation. Here. Increasing the FFT size might help you in most scenarios, but it has trade-offs. The first is computation. This increased precision comes at a cost. Your CPU must perform more calculations, which could slow down processing, especially for real-time signals. But a larger FFT size provides more precise frequency resolution, reducing the spread of the spike. And for the experimentation side, you need to try the different FFT size, and here I choose the here. So, and you should observe how the plot changes the balance and find the balance between accuracy and computational efficiency for your system. This exercise demonstrates that while the FFT algorithm is an approximation, its accuracy can be fine-tuned by adjusting parameters like the FFT size. The result is a cleaner and more precise visualization of the signal's frequency content. By exploring the frequency domain using a simple tone generator and FFT visualization, we have uncovered several critical aspects of signal analysis. The first is sinusoid produce pure tones. As sinusoidal signals generate a single dominant frequency as verified by the spike in the frequency plot at 500 Hz. Second, FFT's imperfections and adjustability. The spread of the frequency spike isn't due to the presence of additional frequencies, but is a result of the FFT's mathematical approximations. Increasing the FFT size narrows the spike, improving accuracy, but requires more computational resources. The third is importance of frequency analysis. Whether working with audio signals or radio signals, frequency analysis is foundational for identifying, isolating, and processing signals. The frequency domain view, powered by tools like the FFT, allows us to break down complex signals into their frequency components, providing insights not immediately apparent in the time domain. So with this understanding, you are now better equipped to analyze signals across various domains, from audio processing to software-defined radio. In subsequent exercises, we will build on this foundation to explore more complex signals and applications. My name is Tayfun, and I'm waiting you in next lecture. By the way, you can also download this file in resources section of this lecture. Hello everyone, my name is Seyfun, and now we are going to experiment with a more intricate sound, a chord that combines three distinct tones. This will give us an opportunity to see how complex sounds differ from single pure tones when visualized in both the time and frequency domains. And now we are going to save our existing project. To keep the earlier one intact, and we will disconnect the existing signal source from its outputs, and we will copy the signal source block twice so that you have three signal blocks. And we will set the frequencies, the first one to 523.25 Hertz. Apply, okay. And the second one to 1318.5 Hertz. And the third one to 1568, and that's it. To combine the three tones, we will use an add block to sum their signals into one. This will allow us to hear a richer sound and observe the combined waveform in both the time and frequency domains. I will drag and drop add block from the library into our workspace, and be careful not to select this add const. No, by mistake we will add block. Here. And we will open the add blocks properties, and here you can see the num inputs. We will change it from 2 to 1 to match the three signal sources, and the type, input output type, will be set to float. Click OK, and that's it. And now we will connect the output of each signal source block to an input of the add block. And here we will connect the output of the add block to the audio sync for audio output, the QT-GUI time sync for visualizing the combined signal in the time domain, and the frequency sync for visualizing the combined signal in the frequency domain. When finished, your flow graph should look like this. Before executing the flow graph, I missed something here. So this frequency should be 1600. And here we are. And now let's run the flow graph. Also increase the sound. So the sound here is richer as it combines three distinct frequencies. This sound corresponds to a C major chord, though some of the notes are separated by octaves to make them more distinct. And a more intricate waveform will be visible, representing the sum of three sine waves. And the frequency plot will display three distinct spikes at 523.25 Hertz, 1318 Hertz, and 1568 or 1600 Hertz. So after executing this flow graph, the frequency sync displays the frequency domain representation of combined signal. So this plot provides insights into the signal composition. Move your mouse pointer over each peak in the frequency domain plot. Observe this x-axis, which is frequency value, which approximates at the frequency of each peak. And the y-axis value displayed corresponds to magnitude of the signal in decibels. Decibels measure the relative strength of the signal at each frequency. So here in this lecture, we learned how to create individual frequencies in a merged signal without the tools like FFT. The original signal frequencies of combined signal will be indistinguishable. And the GUI frequency sync here reveals these frequencies, enabling precise analysis. While we haven't discussed the decibels in detail yet, they are crucial for understanding signal strength and dynamics in both audio and radio domains. So my name is Typhoon. That's the end of this section, and I'm meeting you in next lecture. Hello everyone, I'm Typhoon. Welcome to another lecture. So think about the sounds you hear every day: people talking, dogs barking, or car engine revving. These sounds are much more complex than the simple tones we've been working with so far. Today we will analyze one of these real-world sounds, a human voice, and see how it looks in both the time and frequency plots. Before, we worked with basic tones. They were neat, clean, and easy to understand. But the world around us doesn't sound like that. Real sounds are full of energy, frequencies, and surprises. By studying them, we can learn how to handle more complicated signals in SDR. So let's jump into it. To make a room for our real-world sound, we will delete this signal source block, but let's actually create a new one, new Qt GUI, and here we are, and save this as, let's call human voice. And that's it. We will add a new block called WAV file source. So this block takes audio from a recorded file and feeds it into our flow graph. And here's how to set it up. We will add the file source block. We will open its settings and select the file you can download from the course attachments or resources. And here we will come to Typhoonix. No, it was somewhere in desktop. And here OSR US8 key Typhoonix.wav file. It's a relatively small size, by the way. And here we are. Click OK, and we will also add audio sync. To hear the sound, let's also add time sync. So this time sync, as you remember, shows how the sound looks like in the time domain, like as a waveform. And we will also add frequency sync. This frequency sync shows us the sound frequencies in a graph. Now let's connect this. Here, as you can see, we have red lines, which tells us something is wrong with the parameters, and blocks are not compatible with each other. That's because the sampling rate of audio file you are using, as you can see it, I named it as 8 key, so this means 8000. So we need to change the sampling rate of our all sync blocks to 8000. But before that, I want to show you something. Let's delete this, and as you can see, we don't have any problems with this audio sync. But it's obviously will works in a relatively different way. Let's test this. And here you can see it's like fast forwarding, and that's not what we want. So we will change it all the sampling rate to 8 key. 8,000, and 8,000. And we also need to edit this turn complex to float. That's why we are getting errors as well. Again. And that's it. After connecting everything, your flow graph should look like this. It's simple, but it packs a punch. Now, when you execute this flow graph,
the birch canoe slid on the smooth planks. Glue the sheet to the dark blue background. It is easy to tell the depth of a well. These days, a chicken leg is a rare dish. Rice is often served in round bowls. The juice of lemons makes fine punch. The box was thrown beside the parked truck. The hogs were fed chopped corn and garbage. 4 hours of steady work faced us. A large size in stockings is hard to sell. The birch canoe slid on the smooth planks. Glue the sheet to the dark blue background.
So, when you execute the flow graph, three things happen. First, you hear a human voice through your speakers or headphones. And here you can see the time domain plot. This shows a complicated waveform full of twists and turns. So as you can see, the FPS is relatively slow because I'm running this program in my virtual machine and my computer is slow. And the third you are seeing is the frequency domain plot, reveals a forest of peaks representing the many frequencies that make up the voice. So let's break it down. So in the time domain plot, before we solve smooth waves for simple tones in previous lectures, now the waves looks messy and unpredictable. This is because real-world sounds like human speech are made up of many overlapping waves. And what you're seeing in this frequency domain plot, the peaks in this plot shows the frequencies present in the voice. You will notice that most of the energy is in this mid and lower frequencies where voices usually are. There are also some higher frequencies here which add detail to the sound. So the frequencies move and shift as the voice changes over time. So why is the frequency plot is important? So when the WAV file is played, the frequency sync uses a process called fast Fourier transform to break the sound into its individual frequencies. Without this, we wouldn't be able to separate and understand the different tones in the sound. This is one of the most powerful tools in SDR. It helps us analyze the process, even the most complex signals. So, as you can see here, we can also zoom into signals like we did in previous lectures. And if you are feeling creative, you can record your own sound and analyze it. Here's how. You should use an audio recording software to record a sound, like your voice or a musical instrument. Save the file in WAV format with a sampling rate of 8 kHz, or adjust the flow graph setting for your other rates like 32 kHz or like 48 kHz. And load your file into the flow graph and see how it looks like in the time and frequency plots. You will discover that every sound has its own unique pattern of frequencies. So you might ask, why does this matter? Now that you've seen how to analyze real-world sounds, you are ready to take the next step. Most signals we work with in SDR aren't clean or simple. They're complex, just like the human voice we analyze today. By understanding the frequency domain, you can uncover hidden patterns and solve problems in your flow graphs. In the next lecture, we will learn how to shape and change signals using two powerful tools, gain and filtering. This will let you make a weak signal stronger and remove unwanted noise. These tools are essential for signal processing and will take your skills to the next level. My name is Tayfun. Thank you for watching, and I'm meeting you in the next lecture. Hello everyone, I'm Tayfun. So, in this lecture, let's talk about gain, a simple but powerful concept. So, think of a gain as a way to make your signal bigger without messing up its shape. Imagine you have a wave with an amplitude which maximum height of 3. If you apply a gain of 2, the wave's amplitude grows to 6. With a gain of 3, it stretches even further up to 9. It's like turning up the volume knob on your stereo. The shape of music doesn't change, but it gets louder. And here you are seeing the quick math behind it. So for most practical purposes, you don't need to stress over calculating precise values for complicated signals. Just know that gain multiplies the whole signal by the same factor everywhere. We are interested in two gains. The first is audio signals and the second is radio signals. So gain makes sound louder or softer. Crank up the gain and your favorite song blasts louder through your speakers. Neighbors, be aware. And the radio signals here doesn't, in the radio, gain doesn't make things louder in the usual sense, but makes the signal stronger and easier for your radio receiver to pick up. Now, while gain is your friend, too much of it can lead to problems like distortion in audio or interference in radio. But don't worry, we will dive into these details soon. Now that we know what gain is, let's see how it works using GNU Radio Companion. So we are going to build a simple flow graph that shows how gain affects the signal, both visually and audibly. So don't worry, it's easier than it sounds. We will start by creating a new GRC project and saving it as gain.grc. This will be our playground for experimenting with gain. So we will need some blocks to build our flow graph. The first is signal source. Multiply const. Audio sync. And two time sync. That's it. So this signal source generates a 1000 Hertz sine wave, a smooth repeating wave. So we will set its output type to float and amplitude to 0.1. And here we have multiply const. This block is where the magic happens. It multiplies the signal by a constant value, which is how gain is applied. We will set the I/O type to float. And the constant property to gain val. We will create this variable later. And the audio sync. So this audio sync lets you hear the signal through your speakers or headphones. Let's bring the time syncs here. And that's it. And this, you might ask why we need two time syncs for. So this time syncs display the signal waveforms in real time. Now we will set the type to float for both of them. And y mean here, as you can see here, great advanced. Let's also set them to float. And we will change for both of them, we will change the y min to 0.1, y max to 0.1. So y min for negative 0.1, remember. We'll do the same for this. Scroll down, minus 0.1, y max to 0.1. And now we will connect the blocks. we will connect the signal source to multiply const. The sine wave goes into the multiplier. We will connect the multiply const to audio sync. We will send the amplified signal to the speakers. Also, we will connect signal source to time sync. This is the input signal source section here. We will show the original signal in one time plot. And also, we will show the amplified signal. So we will connect the multiply const to time sync. At this point, your flow graph should look like this. And also, as you can see, we have the read label here because we have entered the variable that we haven't defined yet. So we will bring the gain to life. So to make things interactive, we will add a slider to control the gain. So we will add range block. We will set the ID of a range block to gain val. We will also set the default value to 1. So we will start with no change to signal. We will set the stop 10. This is the maximum gain. And let's see. Let's also create a step to 0.1 so we can make small adjustments. So start 0, the default value is going to be 1, start 0, stop 10, and step 0.1. To make the output easier to interpret, we will rename the time sync blocks. The first one, which is connected to the signal source, as input. And the second one, which is connected to multiply const, as output. Actually, let's readjust the ymin and ymax to 10 to ensure we can see the amplified signal without having to zoom in or out. So 10. So ymin is going to be minus 10 and ymax 10. And we will change this output time sync 2. And that's it. Your flow graph should now look like this. And let's run the flow graph and observe it. So you can hear the sine wave getting louder as you increase the gain using slider. That's too loud. And you can see let's actually mute this computer. And yeah. So you can see the waveforms change as you increase the slider. Remember, this is the input and this is the output. So we are expecting to just change the output. As you can see, input never changes because this is not amplified. So this experiment shows how gain works in real time. It's a simple way to understand how amplifiers boost signals without changing their shape. Whether you are working with sound, radio waves, or other signals, gain is a fundamental tool for shaping how your system interacts with the world. So when you run the flow graph again with default values, the first thing you will notice is two tiny identical sinusoid waveforms displayed on your time sinks. One represents the input signal, the original wave, and the other is the output signal, the amplified wave. So you may ask, why are they identical at first? That's because we set the gain val slider to 1. Look at this here, to 1 by default, and multiplying any number by 1 leaves it unchanged. Now let's explore how gain affects the signal. So you can adjust the gain in 4 ways. You can drag the slider to the right, left to the right, right to the left, and you can type the value like 5 or 10. And you can also use up and down arrows in your keyboard, or you can also click on the slider or in the text box like this. Now let's try setting the gain val to 5. So here you can see the output sinusoid grows by factor 5. So making it much larger than the input. So you will see this clearly on the output timesync, and if you are listening, the tone will become noticeably louder. Now let's try lowering here. Let's try lowering to 0.3. And here what happens now, the output waveform shrinks to 30% of its original size. This process is called something attenuation, which means reducing strength of a signal. You can see how the audio becomes quieter as you attenuate a signal. And feeling adventurous, we will swap out the signal source block for a WAV file source like this, like we did in previous section last lecture. So where file source here. Select the file. You can also download this file by the resources section of this course, of this lecture. It should be somewhere here. OSR US 8 key Phonics valve. And that's it. Click apply, and here we are. And we will change the sample rate to 8 because this file source WAV file has a sampling rate of 8000. You can see when we change this variable value, it changed in everywhere. Let's start it again.
Glue the sheet to the dark blue background.
Yeah. So this here lets you experiment with real-world audio signals instead of simple sine waves. So what you will observe is the peaks of the waveform gets taller or shorter as you adjust the gain. So the audio will grow louder or softer in your speakers or your headphones. And if you increase the gain too much, the audio might become distorted or choppy. This happens because your sound card has limits on the size of a signal it can handle without UGs. Here, you can listen to it. You can see we got distorted and choppy audio. And that's it with our lecture. So these experiments with gain demonstrate how signals processing in GNU Radio is both intuitive and powerful. For boosting signals to attenuating them and working with math blocks, you've taken another big step toward mastering software-defined radio. Now, if you are ready to explore more, I'm waiting you in the next lecture. A filter is a powerful tool in signal processing designed to separate the useful parts of a signal from unwanted noise, interference, or other signals. Imagine it like a water filter. Impure water goes in, the filter removes the impurities, and clean water comes out. Similarly, in the world of radio signals, filters help refine the messy spectrum of signals picked up by an antenna, leave behind only frequencies we are interested in. So, you may ask, why do we need filters? Real-world radio signals are far from clean. Instead of just signal you want, an antenna gathers a cocktail of signals, noise, and interference. Without a filter, your receiver would struggle to isolate the desired signal from the chaos. Now, filters allows us to extract the desired signal by suppressing unwanted frequencies and reduce noise and interference, improving signal clarity. So filters act as a frequency gate, controlling which parts of signals spectrum pass through and which are blocked. Filters rely on the frequency composition of a signal, which can be analyzed using tools like the Fourier transform. Every signal consists of multiple frequencies, and filters selectively amplify or suppress these based on passband, which are frequencies that filter allows through, and stopband, which frequencies that filter blocks. In a sense, a filter adjusts the gain or amplification factor of a signal, but this gain varies by frequency. For example, if gain is 1 in the passband, which are frequencies are preserved, and if gain is 0 in the stopband, this means frequencies are suppressed. So while this is a theoretical ideal, real-world filters aren't perfectly sharp and may allow some bleed between the passband and stopband. There are 4 primary types of frequency-based filters, each designed for a specific purpose. Low-pass filter, LPF. Low-pass filter allows frequencies below a certain threshold, the cutoff frequencies, to pass. Blocks higher frequencies. And the common use of low-pass filter is for removing high-frequency noise from a signal. High-pass filter, HPF. High-pass filter allows frequencies above a certain threshold to pass. It blocks lower frequencies, and the common use for high-pass filter is for removing low-frequency hums or interference. Band-pass filter allows frequencies within a specific range to pass, blocks frequencies outside this range. And common use for band-pass filter is for isolating a specific communication channel in radio systems. Band reject filter, also called notch filter. Band reject filter blocks frequencies within a specific range, allowing all others to pass. And common use for this type of filter is for suppressing particular interfering signals, like power line noise at 60 Hz. While filters sound ideal in theory, practical implementations involve some trade-offs. Sharpness. Filters aren't perfect and may have gradual transitions between the passband and stopband. Delay and distortion. Applying filters can introduce changes to the signal's timing or shape. Complexity. More advanced filters like digital or adaptive filters require careful design and computational resources. By understanding and applying the right type of filter, you can refine raw signals into usable data, enabling everything from a clearer audio to precise radar detection. Filters are indispensable in the realm of signal processing, and mastering their use is a cornerstone of radio communication and electronics. A low-pass filter, LPF, is a signal processing tool that lets low-frequency components pass through unchanged while reducing or eliminating the high-frequency components. This makes it essential for applications where unwanted high-frequency noise or signals needs to be removed. So, you may ask, how does a low-pass filter work? The operation of a low-pass filter revolves around a concept called the cutoff frequency. This is the dividing line between low frequencies and high frequencies. The low frequencies is the part of the signal that passes through with minimal changed, and high frequency is the part of the signal that is suppressed or completely removed. The placement of this cutoff frequency depends entirely on the filter's design and the needs of the application. For instance, in audio processing, the cutoff might be 2 kHz to separate bass sounds from treble. In radio frequency communication, the cutoff could be at several megahertz to isolate at a specific signal band. In an ideal world, the output of a low-pass filter would look like this. Frequencies below the cutoff are unaffected and retain their original strength. Frequencies above the cutoff are completely removed as though they never existed. Let's consider a signal represented by an FFT, fast Fourier transform, showing frequency components from low to high. If the cutoff frequency is set at 2 kHz, frequencies below 2 kHz pass through and frequencies above 2 kHz are blocked. Real-world filters, however, are not perfect. There's often a transition band where frequencies near the cutoff are partially attenuated instead of being sharply stopped. Here we had some project that we created earlier, as I remember, and we used some filter. I think it was the resources and add. No, that wasn't it. Yeah, here. Now, here in previous first AM receiver, we used something called low-pass filter. The low-pass filters are commonly used in audio processing, removing high-frequency noise or hiss, communication systems, eliminating unwanted high-frequency interference in radio signals, for electronics, like smoothing out high-frequency ripples in power supplies, and data analysis, extracting long-term trends by filtering out high-frequency fluctuations. Now, if we run this, why can't open the file? Yeah, however, we will create this in next lectures as well. So, this well-designed low-pass filter ensures that desired signals remain intact while unwanted components are effectively suppressed, so enhancing signal quality and usability. Hello everyone, I'm Typhoon, and in this guide we will help you create a fully functional 3-band equalizer in GNU Radio Companion with detailed explanations for each step. The equalizer will control low, mid-range, and high frequencies separately and output both the audio and frequency spectrum visualization. Now we will first launch a GNU Radio Companion. So if it's your first time using ERC, it is located under your system application menu. Or you can also start with terminal with GNU Radio Companion command. And here we are. Now here we have a new flow graph created. If you don't have one, we will click on File, New, and GT GUI. And this a blank workspace will appear where you can drag and drop blocks to create your signal processing flow graph. And we will save this flow graph as band equalizer. And we will add a variable block from the block menu, but as you can see here, it's already added. Let's call it, let's set the default value to 32 kilohertz. That's a typical sample rate for audio processing. This will ensure consistent sample rates across all blocks. And we will also add WAV source block. File source. And from this block library, we have added file source block to this flow graph. We'll double click on it to configure it, and we will provide the path for the WAV file, a WAV file we used in previous lectures. You remember it was some human talking. Yeah, OSR US 8 key. So you can also find this file in the resources section of this lecture easily. And here, the sample rate for this you cannot set. And yeah, that's it. And repeat, set repeat to yes. To create the three bands, which is low, mid-range, and high frequencies, we will use band pass filter. And drag a band pass filter block to the flow graph, and we will configure it for the low cutoff frequency to 20, high cutoff frequency to 400, and transition with 100. So this 100 smooth transition between pass band and stop band. And in the gain side, we will use a variable named, let's say, also we will use the variable named low gain, which we will add later. So this will control the gain, to control the gain dynamically. And we will also add mid-range frequency band. We will add band pass filter again. And we will set the low cutoff frequency to 400, high cutoff frequency 2600, transition with 500. And we will, for this gain side, we will use a variable named mid gain. And lastly, we will add high frequency band. Let's get another band pass filter from this toolbox and open this block to configure it. And for the low cutoff frequency, we will set 2600 and high cutoff frequency to 10,000. Transition width to 1000. And for this gain side, again, we will use high gain variable to control the gain. That's it. And to allow real-time adjustment of these gain variables for each band, we will add range block, 3 range blocks. So in this range block, let's label it low band gain slider and set this ID to low gain. Remember, low gain, default value to 1, range, and here default value to 1, step size to 0.1, 0.1, and start 0, stop 10. Click apply, and that's it. And we will do the same to other 2 range blocks. Remember, mid gain, label, let's say mid band gain slider. It's going to be float. We will also change this pass filters to float because by default they are complex, so we don't want that. and start 0 to 10, step 1, and click on apply. That's it. Start 0. Oops. Yeah, we will also change the default value to 1. That's it. And we will do the same for a third range, a block. So the label is going to be high band gain slider. Remember this high band variable we defined in band pass filter. High band. Well, default value is 1, range from 0 to 10. Step size is going to be 0.1. Oops, and we also need to set this step size to 0.1 as well for the mid gain. And now we will connect the file source to our band filters. And here you will see red arrows. That's easily fixable by changing it to float. We made a mistake here. Oops. High gain. And here we are. And now we will add an add block. We'll drag and drop add block to our workflow. This block sums the filtered signals from the 3-band pass filters. And we will change the num of inputs to 3. And we will connect these band filters to here. Change this to float, click apply, and click OK. And now what we left to do is we will need to output these combined signals. So we will first need an audio sync. We will add audio sync block to our workflow. We will set the sample rate to sample rate, and as you can see, it's set by default. And now we will connect the output of the add block to input of the audio sync. And we will also add frequency sync. So we are adding this to visualize the signal spectrum. Now we will configure the signal. We will set the FFT size to 1024, and as you can see, it's already set by default. By the way, higher values give more resolution. If you have more computing power, you can set it to higher values. And here, let's set the title to frequency spectrum analyzer, or spectrum of equalized audio. And here, when you scroll down in this, you will see Y min, Y max, Y label, and Y units. These are two are real and the two are strings. And here, instead of is Y min here, we will change it to -10. And we can also adjust as needed based on the signal strength. So we can change this later. And we will connect the output of the add block to the input of frequency sync. And here we have an type mismatch. That's because the frequency sync type is complex and we will convert it to float. Click apply, okay, and that's it. But I think we made some mistakes here because the transition width should be set to 10 for each one of them. Same one applies for this first band pass filter. And let's double check it. Yeah, our main problem stays here. That's because the sampling rate should be set to sample rate and gain to low gain. Oops, this not decimation one. Decimation set to 1, sample rate. Yeah, that one was true. Let's check this one, decimation 1 gain. And yeah, that's it. Now let's try it, run it. And here we are. Hello everyone, I'm Typhoon, and welcome to a deep dive into your AM radio receiver. In the section we will uncover the magic behind the tuning into specific station, extracting the audio signal and converting it into something your speakers can play. But instead of creating another flow graph, we will break down the why behind every step. So I think of this section as peeling back the curtain on how radio works layer by layer. We will start with the GNU Radio Companion. We will open it and save our project file as AMRXGRC. There's a clean slate for your AM receiver built here. And we will add file source block to our workflow. So this block will feed in our raw radio data. We will choose the IQ file. This is the same file we have worked with before. So you can download it from the resources section of this lecture again. Let's choose it and say repeat to yes. Now we have a virtual radio station ready to broadcast. Click OK, and that's it. Now we will also need to visualize the RF input. We will add a frequency sync. To our flow graph. We will set the FFT size to 1024. This controls the resolution of the spectrum. If you have a powerful PC, you can also increase the size. We will set the bandwidth. Actually, let's first change the variable to 400,000. And here, as you can see, bandwidth also changed. So we need to set this bandwidth to 400,000, 400 kilohertz. The range we are analyzing, and let's set the name as RF input just to keep things organized. So once this in place here, let's connect this and execute the flow graph. And here you will see the graph showing the frequencies present in the IQ file. It is like looking at the DNA of the radio signal. And now let's tune into a station. Now we need to tune into a specific frequency. The signal source block generates a reference signal that helps us isolate the station we want. So signal source, we'll add this to our flow graph. Now, let's open its properties. The sample rate will be sample rate, which is 400 kilohertz, waveform to cosine, a smooth oscillating wave, and frequency to 20 kilohertz. We are picking a station centered around this frequency, and we will set its amplitude to 1. And here on the offset and radiance, we will leave this at 0. Click apply and click OK. Now, here's where the magic starts. Now, we will need to multiply the incoming signal from the file source with the reference signal from the signal source. So remember, we need to multiply the incoming signal from the file source with the reference signal from the signal source. So this operations shifts the frequency we want down to a baseband, making it easier to work with. And we will also connect the output of the file source into input of multiply block and output of signal source into second input of the multiply block. Let's organize it. And yeah. And to extract the audio, we will need to add low pass filter, which you learned in previous lectures. So think of this as a bouncer at the club. It lets only certain frequencies in while kicking out the rest. So we will need to add low pass filter. And here, well, we will leave it decimation to 1, so no downsampling yet. Gain to 1, neutral amplification, cutoff frequency to 5 kilohertz, so 5000 hertz. So we are isolating the audio signal. Transition width to 1 kilohertz, so 1000 hertz. So this is a smooth roll off, and window is Hamming. And here, let's click apply and OK. So this cleans up our signal, removing unwanted noise and other frequencies. Now we will also connect the output of the multiply block to input of the low pass filter. Now let's decode the audio from the carrier wave. So we will add AM D-mode block to our flow graph, and we will set its audio pass to 5000 and audio stop to 5500. So let's click OK. And here we need to set the channel rate and audio decimation. We will set audio decimation to 1 and channel rate to sample rate variable. So it's 400 kilohertz. And we will connect the output of low pass filter into input of AMD mode. And also let's organize it a bit. In order to make it playable, we will add rational resampler. So this block change the sample rate of the audio to match what your sound card expects. Now we will rational resampler here. And here we will set its interpolation to 32. This is a upscaling factor. Decimation, we will leave the decimation as 1. And click OK. But we will later we will change this decimation, remember. And here we will connect the output of the AMD mode block into input of the rational resampler. And here, as you can see here, we have a type mismatch. And finally, last block to add to our flow graph is audio sync. So this block outputs the audio to your speakers. and we will set to 32 kilohertz, which is standard for audio playback. And we will connect the output of rational resampler to input of audio sync. And now let's fix the errors. So we here got an type mismatch. That's because we need to do it to float real tabs, and here we are. All errors are gone, and in the AMD mode, in the rational resampler, we will change the, as you can see, we have interpolation and decimation. So we will set its decimation to 400, click apply, and here we are. So what's happening behind the scenes? In the complex data, notice how the output of the file source is blue. That's because it's complex data, numbers with real and imaginary parts. This is how radios represent signals. And here in the AMD mode, rational resampler, we transitioned it to float. As we process the signal, it gradually becomes simpler, like floating point numbers, before reaching the sinks. So if you run this, and now let's make our AM receiver more user-friendly by adding graphical user interface entry options. This will allow us to adjust the frequency and center frequency dynamically during runtime. So think of it as adding knobs to your virtual radio. So let's write entry, the first one, and this is another one. Put it on the top, because that's what we do to variables. And here, we will need to control the target frequency dynamically. And we will open its properties, and we will set the ID to frag and default value to 880,000. Oh. Yeah. And here, which is 880 kilohertz. And in this second entry block we added, we will set its ID to center frag. So here, this will act as the variable for the center frequency, and we will set its default value to 900 kilohertz. And that's it. So you might ask why this matters. So by adding this graphical user interface entries, you can tune into different AM stations without stopping and reconfiguring the flow graph. And it gives you real-time control over your receiver, just like adjusting a knob on your physical radio. Now, what we need to do next is we will need to replace any static value for frequency or center frequency in your block to variables with frag and center frag, but let's test it without it. So here we may see these blocks, but if we even change this, and as you can see, it affects nothing. It affects nothing, so we need to change some properties of the sources. So here, in the file source, we don't need to change anything. In the signal source, we will set the frequency to frag. Click apply, and here we are. Let's see here. Decimation, sampling rate, cutoff frag. Yeah, and we will also set it. And here we are. And center frequency to center frag. And what we left to do is, yeah, IM demode, channel rate. Yeah, we don't need to change that. Check this again. So when we execute this flow graph, the FFT here shows that a wide range of frequencies is contained in this RF data. However, if you look closely, you will notice that a few peaks stand out above the rest. For example, 1880 kilohertz, 800 kilohertz, 750 kilohertz, 710 kilohertz, and so on. So these peaks occur at a regular frequencies interval, which is exactly what we expect to see in raw AM radio data. This in AM broadcasting, several stations transmit simultaneously on different frequencies, which appear as sharp peaks in the FFT. So these peaks are evenly balanced and spaced. So if you measure the gaps between them, you will find they correspond to the AM station spacing standard. So typically multiplies of 10. For example, the FFT might show peaks at 880 kilohertz, 890 kilohertz, or 900 kilohertz. For example, this one, 890 kilohertz. We are seeing it. So this and 900 kilohertz. Let's see here, 910 kilohertz again, 920 kilohertz, and so on. This each representing a separate AM stations. So each AM station's number, for example, like 880 or 750, corresponds directly to the station's broadcast frequencies in kilohertz. So let's do a quick research. US. Let's see in the Texas. And here we are. We are seeing the 1280, which is 1280 kilohertz, as written here, and so on. We have a lot of AM radio stations in Texas. And this is how AM radio stations works in your car and here. And we will also discuss in this lecture about negative frequencies. So what's up with the negative frequencies? So you might have noticed something strange in the plot. So if you turn the center frag to 0, the horizontal axis shows frequencies ranging from negative 200 kilohertz to positive 200 kilohertz. So you might ask, what does this mean? Why negative frequencies? The reason for this range is the default value of the frag variable in our flow graph is 880 kilohertz, meaning you are tuning to a frequency of 880 kilohertz, right? 800 or 880,000 hertz. But instead of seeing frequencies near 880 kilohertz, the plot shows data between negative 200 and positive 200 kilohertz. So here's the explanation. The file source block here provides data captured over a limited range of frequencies, specifically from 700 kilohertz to 1100 kilohertz. This range is centered at 900 kilohertz, which is 900,000 hertz. So, the radio frequency data represents frequencies from 900 plus minus 200 kilohertz, right? So the horizontal axis here, you see, the 900 plus minus, so it shows from 700 to 1100, 1100 kilohertz. So the horizontal axis of the FFT is shifted so that the center frequency appears 0 hertz. So this is a common technique in digital signal processing to simplify analysis. So this means actual frequency range of the data of this file is from 700 kilohertz to 1100 kilohertz, but it is displayed relative to the center frequency. Remember? So if we change this to 900 kilohertz, we will see the same signal. Here, the peaks are the same, right? So this means the actual frequency range of the data is from 700 kilohertz to 1100 kilohertz, but it is displayed relative to the center frequency. So center frequency tells us negatives and positives. So we need to understand another concept in radio, which is input bandwidth. The original hardware that captured this RF data didn't record all possible frequencies starting from 0 hertz. Instead, it only captured data within a specific input bandwidth. In this case, receiver's input bandwidth is 400 kilohertz. Like, remember this value in the variable sample rate? Yeah, the input bandwidth of 400 kilohertz covering a range from 700 kilohertz to 1100 kilohertz. So that's the so let's open the calculator. My Ubuntu is slow. So 1100 kilohertz minus 700 kilohertz is equals to 400. So that's why our sampling rate is 400 kilohertz or 400,000 hertz. And the data is centered in 900 kilohertz. So we set the center frag variable in the flow graph to 900 kilohertz. So this ensures that the flow graph matches the conditions under which data was recorded. And that's it with the input bandwidth. But if we set the center frag to 0, we have one more thing to fix. So the FFT's horizontal axis has center frequencies of 0 hertz now, which doesn't align with the real world frequencies we are analyzing. And to fix this, we will open the frequency sync blocks properties and we will set the center frag to 900, or you can leave the default, by the way. This is the true, remember. We will set the center frag to center frag variable itself, which is equals to 900 kilohertz, or we will need to change it to 900,000, which is this million, yeah, which is 900 kilohertz itself. Remember, 1 kilohertz equals 1000 hertz. So we will, in order to like play with it, we will set it again to center frag, which is as well 900,000 hertz by default. And here again, when you run this flow graph, the FFT plot's horizontal axis will correctly show frequencies ranging from 700 kilohertz to 1100 kilohertz. So the peaks in the plot will now align with their real-world broadcast frequencies. For example, a peak at 880 kilohertz represents the AM station you are currently listening to, and other peaks correspond to other stations within the captured range. The FFT isn't just a tool for identifying stations, it provides critical insights into your radio frequency data. It shows the peak sizes indicate signal strength, and larger spikes represent stronger stations. It also shows the peak spacings, shows how frequencies are allocated and whether stations are crowding each other or not. And we can also see the baseline noise levels, reveals how noisy the environment is. And we can also see the peak widths or bandwidth, indicate how much spectrum each station uses. These details will become increasingly important as we dive deeper into signal processing and noise analysis in future sections. With the FFT giving us a clear view of captured RF data, we are now ready to explore the tuning process in greater depth. This involves understanding how your flow graph isolates a specific station and processes its signals for playback. Now, let's dive into that next. I'm waiting you in next lectures. By the way, you can also download, remember, this IQ file and test it yourself in your own home lab. Tuning in the context of the radio signals is essentially the process of selecting and focusing on one specific signal from a collection of signals while ignoring the others. So you have likely experienced this when operating an AM radio in previous lectures. As you turn the dial or press the buttons, the radio locks onto a particular station and plays the corresponding audio. All other stations remain silent, even though they might be transmitting at the same time. In software-defined radio setup, tuning works in a very similar way, but involves some technical steps. Let's break down how this happens in an SDR flow graph for AM radio signals. Tuning in an SDR receiver involves two main steps. The first is frequency shifting, and the second is filtering. Now, in this lecture, we will explain each of the steps in simple terms. So I will start by explaining frequency shifting. So imagine your SDR is receiving the data from the radio spectrum. So this data might contain several different signals, and we can see them using fast Fourier transform, which is FFT. So the FFT represents frequencies present in the received signal. If you look at this FFT plot, you might see several sharp peaks, each one representing a signal at a specific frequency. For example, the plot might show 5 peaks, 1, 2, 3, 4, 5, each corresponding to a different radio station transmitting at different frequencies. Now, say you want to listen to the station that's represented by the middle right peak you can see here. This peak might be located at, for instance, 900 kilohertz, but we want to shift it so that it is centered at 0 hertz. So you may ask, why do we do this? By shifting frequencies, we move the target signal to the center of the frequency spectrum, which makes it easier to isolate and process. This shifting is done by multiplying the incoming signal by a sinusoidal wave of the desired frequency. In simple terms, the signal you want is now centered at 0 hertz, and this adjustment makes it easier to work with. The shape of the FFT doesn't change here. The only difference is that signal's position on the x-axis shifts. And the step 2 is filtering. After the frequency shift, we now have a signal centered at 0 hertz, but we still have to deal with all other signals around it. This is where filtering comes in. Filtering removes all other signals that are not centered around 0 Hz. In practical terms, we apply filter that allows only the frequencies we are interested in to pass through. The filter essentially removes the surrounding noise and other signals, leaving us with a clean, tuned signal. After filtering, the FFT looks much cleaner. Only the target signal is visible and all other signals are removed. This is the tuned signal. So imagine this. Initially, the input data contains 5 different signals, each represented by a spike in the FFT. You decide to tune the middle right spike, your target signal, and in the first step, frequency shifting, we adjust the position of the FFT so that the target signal is centered around 0 Hz. The overall shape of the FFT stays the same, but the signal we want is now positioned at the center. Next, in the second step, which is filtering, we remove all signals except the one we want. The FFT here now only shows one peak corresponding to the signal at 0 Hz. This process ensures that we are isolating just the signal we want and eliminating all other signals around it. Why tuning is important? Tuning is an essential operation in any radio receiver, whether it's an AM radio, FM radio, or software-defined radio. It allows you to focus on the station or signal you are interested in, while excluding all the noise and interference from other stations. If you are building your own radio receiver or working with an SDR like in this case, understanding the tuning process is critical. It helps ensure that your receiver is accurately detecting and processing the signal you want. And now that we have covered the theoretical part of the tuning, now let's take a look at how this process works in GNU Radio Companion, a tool used to build SDR flow graphs. And in this experiment, we will see the 2 steps of tuning in action, frequency shifting and filtering, and we will go through each step, observing how the signal is adjusted and isolated. Once we combine both steps, we will have a complete understanding of how the AM receiver flow graph tunes to a specific station. This is where the theory comes to life. Stay tuned as we explore these concepts further through practical examples and visual demonstrations. Hello everyone, I'm Tayfun, and in this lecture let's dive into the first step of tuning process, which is frequency shifting. This technique allows us to change the frequency of a signal to make it easier to analyze and process. The basic idea behind frequency shifting is to multiply the incoming radio data by a complex typed sinusoid. In this section, we will walk you through a simple experiment using GNU Radio Companion to demonstrate how this works. To get started, you need to create a new project in GNU Radio Companion. This experiment will help you see how the frequency shifting process works in a practice. We opened GNU Radio Companion and we will create a new Key2 GUI project, and let's name it frequency shift.grc. And you can also keep your AM/RX radio flow graph open. You don't need to close your previous AM radio flow graph. GNU Radio Companion allows multiple projects to be open at once. And so you can keep the AM receiver project running while starting this new one. And we will add the file source from the block list. We will drag and drop file source onto the flow graph. We will select the file property. It should be on the desktop. Yeah, this one. We will select this 72 megabyte file, radio file, IQ file. And here we are. So you can also download this file by the resources section of this lecture. Click apply, and that's it. So this is the contains synthetic radio data that we will be working with, and this data will serve as the input for our experiment. And we will also need to add straddle block. Now this straddle block we will connect to connect the output of file source to input of throttle block. So the throttle block is important because it ensures that your computer doesn't work too hard when processing the data. Essentially, it controls the rate at which the data is processed, preventing your system from getting overloaded. And now we will need to add frequency sync for visualization. We'll connect the output of the throttle block to the input of the frequency sync block. We'll set the name property to input so we can identify it easily later. And after adding the blocks, ensure your flow graph looks something like this. And let's run the flow graph. So when you run the flow graph, you will be able to visualize the frequency domain of the radio data coming from the file. At this point, you should see a single peak in the frequency spectrum, as you can see here, 1, 2, 3, 4, and so on. So this peak represents the main frequency of the radio data in the file. The experiment isn't over yet, so we are about to start applying the frequency shifting technique to manipulate this data. And now that we have got basic flow graph set up, we can begin to apply the frequency shifting process to manipulate the incoming radio data. The key operation here is to multiply the data by a sinusoid with a variable frequency, which will help us shift the frequency of the input data. Now, to start, we will need to create a sinusoid that can vary its frequency based on user input. And now we will add a signal source from the block list. Drag and drop signal source onto your flow graph. Open its properties and set the frequency property of the signal source block to frag. This makes the frequency of the sinusoid variable. We will keep the other properties at their default settings. With these settings, the sinusoid will be of complex type, which is important for this frequency shifting operation. And we will also need to create a variable for frequency control. In this case, we will use a GUI entry. We will set the ID of entry block as frag. So we need a way to adjust the frequency in real time, and we use the entry. The label, let's say, we don't need to assign a label because it's just a variable. Let's entry. And here we will set the default value at 0 Hertz. So this allows you to control the frequency of sinusoid dynamically while running the flow graph. And next, we will need to perform the actual frequency shifting. And to do that, we will multiply the input radio data by sinusoid. So we will add multiply block, just to multiply. We will connect the output of the throttle to input of the multiply block. And we will connect the output of the signal source, the sinusoid, to the other input of the multiply block. This operation will multiply each sample of the RF data by the corresponding sample of the sinusoid, effectively shifting the frequencies of the radio data. And now you need to visualize the frequency spectrum of the shifted data. We will add another frequency sync block to our flow graph, and we will connect it to the output of the multiply block. We will set the name as shifted, and so you can easily distinguish it from the original input plot. Here. And to better understand the impact of the frequency shifting, we will need to adjust the frag value and see how the spectrum changes. So we will change the name of the first frequency sink. Before you continue, we will rename the frequency sink to input if you hadn't do so you can track the original data before any shifting. And now we will execute the flow graph to visualize the frequency domain of the radio data before and after frequency shifting. At this point, you should see two frequency plots, one labeled as input, this is the original data, and another labeled as shifted. This is the data after frequency shifting. And in this case, they are both identical. See the spikes, same spikes here. They are the same. And next, we will explore what happens when we change the frequency of the sinusoid to 1000 Hertz and observe how the frequency domain shifts accordingly. Now, let's see. So here we have a spike at 1.60 kilohertz, and now it's 0.60 kilohertz. We had a spike at, in original, we had a spike at 8 kilohertz. Now it's 9 kilohertz. We had a spike at minus 8 kilohertz. Now it's minus 7 kilohertz. And now that you have added the variable frequency sinusoid and connected it to the input data, it is time to analyze deeper and see the outcome and see what happens when you apply different frequencies. So when you hover your mouse over the peaks in both the input and shifted frequency plots, you will observe the input plot should show the main peak around like negative 1.6 kilohertz. Or let's see the center frequency. So 0 kilohertz, right? So the shifted plot here now shows this zero frequency at here at 1 kilohertz instead of 0 kilohertz. So here this illustrates how multiplying the RF data by sinusoidal signal with frequency of 1000 Hertz results in a shift of the frequency spectrum by exactly 1000 Hertz. So if you experiment it with other frequencies, you will see that the frequency plot shifts accordingly. For example, multiplying by 4000, which is 4 kilohertz sinusoid, will shift the frequency spectrum by 4 kilohertz to right. Multiplying by negative 4000 will, and as you can see, it's gone. Here it's gone. No, it's not gone. Sorry. I think we zoomed in. That's why. Yeah. So multiplying, I will say it again, multiplying by 4 kilohertz, sinusoid will shift the frequency spectrum by 4 kilohertz to the right. Let's see. This is the input. Here we have 0. And this identical signal will be showed at 4 kilohertz if we shift by 4000. And if we make it negative 4000, this spike at 0 kilohertz in the input will shift to negative 4 kilohertz. So that is how shifting works in radio. So the idea of negative frequencies can be difficult to grasp, but it's a mathematically valid concept and an essential tool for frequency shifting. So to demonstrate this, when you multiply the RF data by sinusoid with negative frequency, such as, for example, minus 4000 Hz, you will notice the frequency plot shifts in the opposite direction, which is to the left, and centers around 0 Hz. So this phenomenon happens because multiplying by a negative frequency shifts the spectrum to the left rather than right. So it shifts to left. This frequency shifting behavior can be generalized as follows. To tune to a specific frequency, you multiply the radio frequency data by a sinusoidal signal with a frequency that is the negative of the target frequency. For example, to tune to a 5 point negative, or let's start with 0, of course, to be more accurate. To tune to this signal in minus negative 1.60 kilohertz, we will write, or not tune, to frequency shift, minus 1600 hertz, which is equivalent to negative 1600, negative 1.6 kilohertz. And in the input, in order to write, so we will, here we are seeing this negative 1.6 kilohertz on the 0. If we shift this by 1600 right. So what's next? Now that you have a basic understanding of how frequencies shifting works, you can move forward with applying this principle to tune into specific radio signals. Next, we will explore the second step of tuning process, which is filtering out the unwanted signals so that you can isolate your desired signals after shifting its frequencies. I'm Typhoon, and I'm waiting you in next lecture. When working with real-world radio data in an SDR, which is software-defined radio flow graph, like the one in your AM receiver project, you encounter a crucial concept: the need to manage two sets of frequencies simultaneously. And these are real-world frequencies and GNU radio frequencies. A real-world radio frequency is tied to physical radio signals and the laws of physics, and GNU radio frequencies, which are shifted to simplify digital signal processing. This dual frequency consideration adds a layer of complexity to the tuning process, which becomes especially relevant when handling actual radio signals as opposed to synthetic or pre-processed data. Now, let's break this down step by step to understand why this happens and how to navigate it. In earlier exercise, you may have noticed that the input FFT plot ranged from negative frequencies, like those to positive frequencies. So while this might seem straightforward in mathematical sense, in practice, real-world radio signals do not exist at the negative frequencies. Instead, all signals you encounter will have positive frequencies that are typically far from 0. For example, the frequency plot of the input radio data for the full AM receiver, and yes, let's open that project and I will show you something about that. So here, first AM receiver, and yep, let's start it. Yeah, so here, which demonstrates a range starting at 700 kilohertz and extending up to 1100 kilohertz, which, as you remember, we did that in previous lectures. And yeah, this range directly corresponds to the real-world radio frequencies captured by the SDR hardware at the time of the data acquisition. So if you were tuning to 880 kilohertz signal, you were effectively interacting with a real-world signal at precisely 880 kilohertz at that time. So you may ask why zero-centered frequencies matter, like in this previous lecture where we created frequency shift operation like this. So here from the left of zero we have zero frequencies, right? So zero-centered frequencies simplify many mathematical and computational tasks like digital signal processing, DSP operations such as filtering, modulation, and demodulation often rely on zero-centered signals to minimize computational overhead. This approach is more efficient because it allows algorithms to leverage symmetry and reduces the complexity of frequency domain manipulations. From a user's perspective, though, always thinking in terms of zero-centered frequencies can be counterintuitive. Real-world frequencies make more sense when working with AM or FM signals where broadcast stations are tuned to specific physical frequencies. For instance, 900 kHz AM broadcast station will always be referred to as such in user-facing context, not as shifted frequency centered around zero. This discrepancy is why systems like GNU Radio employ mechanisms to reconcile these two representations, allowing you to work with real-world frequencies intuitively while maintaining the internal benefits of zero-centered processing. And to bridge the gap between real-world frequencies and zero-centered processing, the AM receiver flow graph incorporates a critical parameter, which is center frag we will create in this lecture. So this parameter will act as reference point, enabling the flow graph to align user's input with GNU Radio's internal representations. So here how it works. So here we will create a new entry called center frag. So if a user input or displays a data, all user-facing element such as this frequency sync and like tuning controls which operate using real-world frequencies. For instance, so you can specify a frequency of 880 kHz to tune into a station which is intuitive and matches the physical reality. And we can also do internal adjustments with that variable. So if you have a center point, the flow graph uses the center frag parameter to translate frequencies into zero-centered frequencies. So this is done by offsetting the desired. Here, let's actually open the notepad and do some simply math, right? Don't worry, we will not discuss any logarithmics here. Now, here, so center frag minus frag in the project we will create. For example, center frag will be equal to 900 kilohertz minus 880 kilohertz, and this 880 kilohertz will be our frag. Let's actually write it under this. And this is going to be equal to 20 kilohertz. So when tuning to 880 kilohertz with a center frequency of 900 kilohertz, the effective tuning frequency for GNU Radio becomes this, which is 20 kilohertz. This means that the signal is shifting 20 kilohertz to the right in the zero-centered representation, making it compatible with GNU Radio's processing framework. And let's find this spike here. Yep, that's it. And yes, and here we can see the spike at 15 kilohertz, 8 kilohertz. Yeah, we will learn that in this section. So, and we can also use output the frequency plot. So the frequency sync here shows the result in real world terms, ensuring that user sees signals at their actual broadcast frequencies. So this dual bookkeeping system ensures seamless interaction between the intuitive real-world frequency domain and computationally efficient zero-centered domain. The concept of managing dual frequencies, real-world and zero-centered can feel abstract at first. However, as you gain more experience building and analyzing SDR flow graph, this duality becomes second nature. So remember, real-world frequencies are for humans. They are intuitive, easy to understand, and directly tied to the physical world. But zero-centered frequencies, like you see in this flow graph, they simplify the complex mathematics of digital signal processing. Mastering this interplay, along with a solid understanding of filters and their applications, is key to becoming proficient in an SDR systems. Keep experimenting with different configuration, frequencies, and filter settings to deepen your understanding and refine your skills. And now we are diving deep into the process of building a fully tunable AM receiver using GNU Radio. So we will not only create a flow graph step by step, but also explore the theory behind each component to ensure a solid understanding of the concept. So by the end of this section, you will not just have a working AM receiver, but a comprehensive knowledge of how and why it works. And now let's get started. Now we will create a new project. So why this matters is starting with an empty project provides a clean slate to carefully design our flow graph. This project will process real-world RF signals and demodulate an AM station for playback. And now we will drag and drop a file source. And we will open its properties. We will set the IQ file from the resources provided in this, both in this lecture and earlier lecture. We used this, remember, 2024 AM example to phoenix.iq file. Click apply. And yep. And we will also need to set the repeat to yes, and it's already set by default. And here, the file source block serves as our input, simulating live data from an SDR device. This IQ file contains pre-recorded RF signals. And by setting this repeat, the file will loop, providing a continuous signal for testing and tuning without interruptions. So you may ask why it's important. Working with recorded data allows us to repeatedly test and tweak our flow graph without needing a live SDR device. And we will need to add a signal source as well. We will drag and drop a signal source block to our flow graph. And here we will set it, of course, we need to first change the sample rate here, 4000. And we will set its sample rate to sample rate, a waveform cosine, frequency to 20,000, which is 20 kilohertz, amplitude 1, and offset 0. Click apply. Okay, that's it. So the signal source again generates a sinusoidal signal used to shift the RF data in frequencies. So the frequency shift is necessary to tune the signal by centering the target frequency at 0. So frequency shifting simplifies signal processing by aligning the desired frequency with the center of the spectrum for easier filtering. And now we will add frequency related variables here. So we will add two entry blocks and 1, 2, and configure these blocks. Let's actually put this here so it will look nice and clean. So for the first block here, we will set frag default value to 880,000. Oops. 880,000. And here in the second we will set it center frag to ID, and we will set it 900,000, which is 900 kilohertz and 880 kilohertz. And here we also have the sample rate, which is set to 400 key, which is 400,000 megahertz. And this frag here represents the frequency of the AM station we want to tune into. Center frag is a reference frequency of the recorded radio frequency data, this data. And the sample rate ensures synchronization between all blocks. So you may ask why it's crucial. So the variables allow dynamic adjustments of tuning parameters and maintain a consistent framework for signal processing. And now we will need to visualize raw input data. We will add a frequency sync block to our flow graph and set its name to radio input, FFT size 1024, and here we have the bandwidth in hertz is sample rates, and click apply, and that's it. So the frequency sync here provides a visual representation of the RF data in the frequency domain. It reveals the structure of the incoming signals and helps identify the frequencies of various stations. Now here in bandwidth we have the 400,000 hertz. In variable we also have the 400,000 hertz, 880,000 hertz, and 900,000 hertz. So these both are 900 kilohertz, 880 kilohertz, and 400 kilohertz, and frequency sync is as well frequency sync bandwidth equals to 400 kilohertz. That's because we set it to reference the variable. And we will need to add a multiply block for frequency shifting. We will add a multiply block, and we will connect its input 0 to the output of file source and input 1 to output of the signal source as well. So here this block performs element-wise multiplication between the RF data and sinusoidal signal from the signal source, and multiplication in time domain results in frequency shift, centering the target signal at 0 hertz. So frequency shifting simplifies the tuning and processes and filtering processes, making them more effective. And also let's connect the frequency sync named radio input to the output of the file source and put it here. And now let's add a low pass filter block and configure it. Now here open its properties, and here set decimation to 1, gain to 1, sample rate leave it as default, and cutoff frequency to 5,000 hertz, and transition width to 1000 hertz. And now click apply here, and we will connect its input to the output of the multiply block. So here the low pass filter isolates the desired signal by removing high frequency noise and other unwanted components, and this cutoff frequency we defined here determines the highest frequency the filter will allow through. So why this is vital, you may ask? So filtering ensures clean audio by eliminating interference from other stations or noise. And now we will need to also visualize the intermediate stages. So we will add 2 more frequency sync. Here. So now the first one, we will set its name to shifted, which this will connect to the output of the multiply block like this. And here we will also set 1 to filter out. This will be connected to the output of the low pass filter. So this shifted frequency sync named shifted shows the RF data after frequency shifting. Remember, multiply helps us to shift the frequencies, helping verify that the target frequency is centered at 0 Hertz. And this filter out, let's make it closer. So this filter out shows the filtered signal, ensuring unwanted frequencies are removed. So why it's helpful? Visualizing these stages aids in debugging and understanding the signal processing pipeline. And now we will need to add AM demode block. Oops. Here, AM demode. Put it here. And here we will set the channel rate as samp rate, decimation to 1, audio pass 5000 Hertz, and audio stop to 5500 Hertz. And now we will connect its input to the output of low pass filter. And this block here extracts the audio signal from the amplitude modulated RF data. It effectively listens to the selected AM station, and without demodulation, we wouldn't be able to convert the RF data into audible sound. And now we will add rational resampler to our workflow and open its properties. So we will set the interpolation to 32, decimation to 400, and we will connect its input to the output of AM demode. And lastly, we will add audio sync block to our flow graph and configure its sampling rate as 32,000. And we will connect its input to the output of rational resampler. So by the way, the rational resampler adjusts the sample rate of the audio signal to match the playback device requirements. For in this case, our playback device is 32 kilohertz. Will work with compatible with 32 kilohertz, and your device, I'm 99% sure that your device is 2. And so here, and also the resampler ensures compatibility with this audio sync, preventing playback issues. And here we connected the audio sync here. The audio sync outputs the processed audio signal to your computer's speakers, and the final step allows you to hear the demodulated AM station. And here you can see we have some red lines. As you know, this means type mismatch. So there's something wrong with our flow graph. The thing is here, it's the type of rational resampler. So we will need to turn it to float complex. And here the entry is fixed. But since audio sync takes float as well, and we will need to change it to float real tabs. And here we are, our flow graph is done. And now let's save it as AM tuning example and start it. And here we are, our flow graph works now. And here you can see the frequency plots at a different stages and the audio output from the speakers here. Yep. And yes, and also the audio output from the speakers. And the expected results here are the radio input sync shows raw RF data like this. Shifted sync at the top confirms the frequency shift here. And filter out here, sync displays the isolated target signal. And clear audio of the selected AM station plays through your speakers. And now that we have built our tunable AM receiver, let's take a closer look at what frequency plot tells us. So these visualizations are critical for understanding how each step in the flow graph transforms the signal, ultimately isolating and extracting the audio from the desired station. So here, let's firstly see the input plot, which is the raw signal. Remember this? Radio input. So this is what we see directly from the file source. So in the input plot, the RF input plot shows the unprocessed data captured from the IQ file. This data mimics what an SDR hardware receiver will capture in real time, centered around 900 kilohertz. And you will notice multiple peaks across the frequency range. Each peak represents different AM radio station transmitting within the SDR input bandwidth. And the peak we are interested in the station broadcasting is 880 kilohertz. So it sits slightly to the left of the center. And remember this calculation, 20 kilohertz. So it's at the left, 20 kilohertz. This is the peak we want this. And this offset here matches the configuration of the IQ file, which represents the signal in range from 700 kilohertz to 1100 kilohertz. So you may ask why this matters. So this plot provides a real-world view of the radio spectrum, showing all the signals present within the input bandwidth. It's a snapshot of the chaotic environment your receiver has to navigate. And we also have the shifted plot. So the shifted plot reveals the data after frequency shifting. Our flow graph uses a sinusoid to shift the target signal 880 kilohertz to 0 hertz here, which is the center of the frequency axis. And importantly, the horizontal axis of the plot is zero-centered, representing the way GNU Radio processes signals internally. So by shifting the frequency, we simplify the process of isolating the desired signal. So this transformation aligns our mental model of the data with how the software processes it. So the rest of the flow graph can now treat the target signal as if it's the only signal present. And here we are, our filter out plot. So the filter out plot shows the, also I want to show you where this filter out plot is after the low pass filter, remember? But this shifted is after the multiplying. So multiplier does the shifting job for us. Now we have the frequency sync of the filter out. Now let's see its plot. And this filter out plot shows the data after applying the low pass filter. Here the signal is tightly constrained, retaining only 5 kilohertz band around the center frequency. So the low pass filter eliminates everything outside this desired signal. For example, other signals, we don't see the other signals here, right? Which peaks from the neighboring stations are removed now. And we also don't have a noise. So random energy between these peaks here, for example, this random energy between peaks is filtered out too. So this is the importance of filtering. So imagine trying to listen to a single person in a noisy room filled with chatter. Without filtering, all those voices overlap, making it impossible to hear the one you are interested in. Filtering isolates the voice you want while silencing the background noise. And here, each plot plays a pivotal role in understanding and debugging the tuning process. For example, the radio input plot shows the raw spectrum and helps identify the station you want to tune to. The shifted plot demonstrates the effectiveness of frequency shifting, ensuring the target signal is centered for further processing. And filter output confirms that the target signal has been successfully isolated, free from interference and noise. To reinforce these concepts, tune to other peaks visible in the RF input plot, adjust this frag variable in the flow graph, and observe how the shifted and filtered outputs respond in this case. Radio input, shifted, and filter out. So you will see the tuning process in action, providing instant feedback on your settings. Mastering the art of tuning is a milestone in your journey into radio communications. It's a foundational skill that underpins nearly all software-defined radio applications, from basic AM receivers to advanced communication systems. With these tools, you are well on your way to exploring the rich and dynamic world of radio signals. My name is Tayfun. Thank you for watching, and I'm waiting you in next lecture. And now that we have successfully isolated a single AM radio signal using the low-pass filter, it is time to extract the audio hidden within that signal. This process, known as demodulation, is a critical step in the flow graph, converting the modulated radio wave into something we can actually hear with this audio sync. Now let's take a closer look at how this works, the significance of the AM demod block in GNU Radio, and why it serves as the bridge between the radio world and audio world. An AM radio signal is essentially a carrier wave, a consistent frequency that's modified or modulated by an audio waveform. So this modulation affects the amplitude of the carrier wave, encoding the audio information onto the radio signal. So think of the carrier wave as a reliable delivery vehicle and the amplitude modulation as the package it's carrying. And in our case, the carrier wave remains at constant frequency, like 880 kilohertz. The audio waveform is changing amplitude that represents spoken words or music shaped by the original recording. So when we pass the modulated signal through this AM demod block, the block extracts that package, which is the audio information, and discards the vehicle, which is the carrier wave. Demodulating an AM signal manually will require techniques like envelope detection, which is tracking the peaks of the modulated wave to reconstruct the audio, and product detection, which is actually multiplying the signal with local oscillator to isolate the modulation. These methods involve advanced signal processing concepts that can be done to implement manually, but the AM demod block in GNU Radio, however, handles all of this behind the scenes, saving us from the complexity. So here's what it does. Carrier removal. So AM demod, it identifies and discards the carrier wave. Audio extraction. It extracts the amplitude variations that correspond to the original audio signal. And type conversion. It converts the signal from complex, here you can see this complex, which is used for radio data, to float, which is used for audio data. This automated functionality allows us to focus on understanding the results rather than the intricacies of manual signal processing. A critical feature of the AM demod block is its ability to serve as a transition point between these two parts of the flow graph. This one on the left is the complex input, which is radio side. the data entering this AMD mod block is a complex signal. Here you can see complex, 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 and complex as well. So here, complex numbers are necessary in radio processing to handle both amplitude and phase information, which are key to manipulating signals in the frequency domain. But on the right side, here, the float, here, rational resampler is float, audio sync is float, output of the AMD mode is float as well. You see this orange? Orange means float in GNU Radio, and blue means complex. Now let's also select this. So here, this is the audio side, which is float output. The data exiting this AMD mod block is a float signal. Floating point numbers are simpler and sufficient to represent a real valued audio waveform. So this type of data is what your sound card and speakers require to produce a sound. And as I said, this type of conversion is easily visualized in GNU Radio. For example, the AMD mod block has a blue input tab for the complex signal and an orange output tab for the float signal. So complex comes in, float goes out to the audio. And by segmenting this flow graph into two parts, you can see the clear separation between the radio processing chain. This actually, it's not radio processing, it's just a sync block where you can see the waveforms. And this orange output tab for the audio output chain. So you may ask, why demodulation is essential? So without demodulation, your flow graph would output the raw radio signal, a high frequency carrier wave modulated by audio. So this would sound like a high-pitched noise if played directly through your speakers. The AMD mod block transforms this chaotic signal into something intelligible, delivering the audio content encoded in the radio wave. So you remember, radio wave, the audio, or audio in the radio wave is encoded, so you have to decode it. So as I said, think of your flow graph as two-part machine. The radio processor, which is complex data, handles the captured radio data, shifting and filtering it until a single station remains. And the audio extractor, which is the float data, focuses on isolating and outputting the audio signal encoded in the radio data. The AMD mod block acts as the hinge connecting these two sections, seamlessly converting radio signals into audio. The AMD mod block represents more than just a technical convenience. It embodies the transition from the abstract, mathematical world of radio waves to the tangible human experience of sound. By demodulating the signal, we bring the encoded voice or music to life, completing the journey from the airwaves to your ears. Hello everyone, I'm Typhoon, and at this point in our journey through this AM radio flow graph, we have successfully tuned into a radio station, filtered out unnecessary frequencies, and demodulated the signal to extract the audio. But however, there's one last step before we can actually hear this audio, which is resampling or rational resampler block we added here. The audio signal coming out of this AMD mod block is sampled at a rate of 400 kilohertz. But here's the problem. Most sound cards can't handle this. Typical sound cards are designed to work with sample rates much lower, like 33 kilohertz. But there's an important rule you must always remember in GNU Radio. So when connecting these two blocks, the outputs, and this is where resampling or rational resampler comes in. So resampler adjusts the sample rate so that data flows seamlessly from one block to the next. It doesn't alter the signal's fundamental characteristics like its frequency or amplitude. It just changes how fast the samples are taken. Resampling involves two key processes. The decimation, which reduces the sample rate by discarding some samples, and interpolation. This increases the sample rate by inserting new calculated samples. And for our flow graph, we will need a combination of both processes to bridge the gap between 400 kilohertz and 32 kilohertz. Now let's dive deeper into these concepts to understand how they work. So let's start with this decimation. Decimation is the process of lowering the sample rate by systematically removing data points. So think of it as zooming out on a picture. By discarding some details, you can still see the overall image, just at a lower resolution. So here's a simple analogy here. So imagine you're writing down the temperature every second for an hour. If you decide to record the temperature every 2 seconds instead, you're essentially decimating the data. In the context of signals, decimation works similarly. For a signal sample that, let's actually open the notepad and do some basic math. Here. So, for a signal sampled at 1000 samples per second, discarding every other samples leaves us 500 samples per second. So and this here, we call that decimating by 2. And to visualize this, here you can see a figure. So the original stream has evenly spaced samples, and after decimation by 2, only every second sample is retained, reducing the density of the stream. And in GNU Radio, decimation is performed using blocks like keep 1 in n and keep 1 in n. This block allows you to specify how many samples to keep versus discard. And now, to understand this practically, let's create a new project called decimation. New, save it as deci. Close the old one, and here. And in this lecture, I will demonstrate the effects of decimation on a signal step by step. Now we will first add a signal source block to generate a simple test signal. This block creates the signal we will be working with. So we will use default settings, but make sure that type is set to float. And next, we will add throttle block. So this block regulates the flow of data to prevent your computer from being overwhelmed. So think of it as a traffic cop, ensuring that data flows at a manageable pace. Again, use the default settings, but set the type. And to observe the effects of decimation, we will add time sync to view the input signal, and we will connect it to the output of the throttle block. We will also connect the output of signal source to throttle. And now we will rename it as 32 kilosamples per second input. We will set the number of points to 128 for a clear view. And under the config tab, we will set the line 1 marker to circle. Click apply and OK. Also, we forgot to change the type to float. And here we are. And now we will add keep one in n block to our flow graph. We'll connect its input to the output of throttle. Set its type to float. And now we will add another time sync to view the decimated signal. We will connect it to the output of keep one in n block. Rename it to decimated output. Set the sample rate to 8,000 because, I will explain right now, and the number of points to 32. And from the config tab, line 1 marker to circle. So the reason we set the sample here, let's actually open it, and yeah, the reason we set the sample rate, of course we need to also change the float again. So the reason we set the sample rate to 8,000, no 800, 8,000, because we have decimated it by 4. And now we have one last thing to do with our project. We will set the n to 4 in this keep one in n block to decimate the signal by a factor of 4. This means, let's actually open this. So this means the block keeps every 4th sample from the input data and discards the rest. By doing it, the sample rate is effectively reduced to 1/4 of its original value. For example, if the input signal has sample rate of 32 kilohertz, 32,000 hertz, that's actually, the 32 kilosamples per second, decimating by 4 reduces the sample rate to 8 kilosamples per second. So this is useful when we want to lower the sample rate to make the signal more manageable or match the requirement of downstream blocks while retaining the core information of the signal. And when complete, your flow graph should look like this. And when you execute this flow graph, here, you will see two domain plots. The first plot shows the, let's actually start with the second plot. So the second plot shows the original signal sampled at 32 kilosamples per second. This one. And the first plot shows the decimated signal, now sampled at 8 kilosamples per second. This one. And you can notice how the decimated signal has fewer data points which over the same period of time you can see. This is because we have effectively reduced the sample rate while maintaining the overall structure of the signal. While decimation is useful for reducing sample rates, but it's not always enough to reach the target rate. In the next lecture, we will explore interpolation, the process of increasing sample rates to complete the resampling process and make our audio signal ready for playback. My name is Typhoon and I'm waiting you in next lecture. Now let's shift gears and talk about throttle block. This unassuming block plays a vital role in synthetic flow graphs, preventing your CPU from being overwhelmed. When you specify a sample rate in GNU Radio, it defines how fast the data flows between blocks. For instance, a sample rate of 32 kilosample per second means each block processes data at a rate of 32,000 samples per second. However, in a purely synthetic flow graphs used without real-world hardware like SDRs or audio sinks, GNU Radio has no external timing constraints. Your computer processor, being extremely fast, can execute this flow graph far faster than the specified sample rate. But this causes two issues. Resource hogging. Without a throttle block, GNU Radio runs the flow graph as fast as possible, consuming all available CPU resources. And it is also inefficient, so this can slow down other applications on your computer, making it difficult to multitask. And of course, the solution is throttle block. The throttle block enforces a specific data rate, effectively slowing down the flow graph to match the desired sample rate. And so, here's how it works. The throttle block sample rate property defines the rate at which data flows through the block. And it introduces a and in our decimation example, the throttle block ensures that the data flows at 32 kilosamples per second, maintaining a consistent rate and preventing the CPU from being overutilized. Decimation and throttle block are fundamental tools for building efficient and practical GNU Radio flow graphs. The AM radio receiver you built is just the beginning. As you progress, you will learn to construct more advanced analog receivers using a similar framework, with only a few variations. Even digital receivers share many of these foundational components. In the next section, we will continue this journey with a new type of analog receiver. Hello everyone, I'm Typhoon, and now let's start with quick comparison. In traditional hardware radios, all the heavy lifting, like decoding and processing radio signals, was done using analog circuitry. Essentially, the design relied on physical components to perform specific mathematical operations. But times have changed. With modern computers becoming significantly more powerful, we can now handle these calculations using software. And that's what exactly software-defined radio, or SDR, is. It moves these tasks from hardware to software. So you may ask here, why does this matter? Well, this shift has made it possible to create advanced radios that were once dependent on complex analog hardware. Now we can replicate and even enhance those capabilities with just a computer and the right software. Features like wideband tuning and waterfall displays, which used to cost a fortune, are now affordable and accessible to more people. In short, SDR is revolutionizing radio technology, making it simpler, more versatile, and budget-friendly. What is the RTL SDR? Now let's talk about the RTL SDR, one of the most affordable and popular tools in the world of software-defined radio. The RTL SDR is essentially a repurposed digital HDTV USB receiver dongle, originally designed for watching televisions. But what makes it special is the RTL2832U chip inside it. Back in 2012, hardware hacker Eric Fry, Linux driver developer Antti Paulosaari, and the Osmocom team, who were working on their own SDR project, discovering something fascinating. They found that RTL2832U chip had a unique mode, allowing it to function as a general wideband SDR receiver. This discovery transformed an everyday TV dongle into a powerful tool for radio enthusiasts. With the help of custom software drivers, these low-cost dongles, often priced under $20, can be turned into highly capable SDR receivers. And just a few years ago, you'd need to spend hundreds or even thousands of dollars for similar functionality. Now, while it is true that the performance of RTL SDR won't match a high-end dedicated SDR, it delivers exceptional value for its price. In fact, most hobbyist projects that require expensive radios or SDRs can also be accomplished with RTL SDR. Plus, its widespread popularity means it benefits from a large, active community. Owning a wideband SDR like the RTL SDR opens up countless possibilities, from listening to radio signals across the spectrum to exploring advanced radio concepts. And there's no shortage of exciting projects. In later sections, we will dive deeper into some of these applications and how you can get started. Hello everyone, my name is Typhoon, and in this lecture we are going to explore the technical specifications of RTL SDR and other software-defined radio devices. And you will also get familiar with some important SDR terminology. And let's get started with the technical specifications of RTL SDR. The frequency range, the most RTL SDR devices can tune into frequencies ranging from 22 megahertz to 2200 megahertz. However, these numbers are approximate and may vary depending on the specific tuner model used. And we also have a bandwidth. The RTL SDR has a maximum bandwidth of 3.2 megahertz, but it's more stable around 2.8 megahertz. And bandwidth refers to the range of frequencies that device can process at once. And we also have the analog to digital converter. The ADC in RTL SDR is 8-bit, which gives it a dynamic range of just under 50 decibels. So dynamic range is the difference between the strongest and weakest signal that device can handle. And we also have the noise figure. This noise figure, which indicates how much noise the device adds to the signal, is less than 4.5 decibels for the RTL SDRs here. At a lower noise figure means the better performance in weak signal conditions. And we also have the learn in this lecture, the terminology is input impedance. The input impedance is 75 ohms for all RTL SDRs, which is a measure of how much the device resists the flow of electrical current from the antenna. And the ADC, the analog to digital converter, is a crucial part of RTL SDR. This ADC stands for analog to digital converter. It's a small electronic component that takes an analog signal, like the radio waves picked up by your antenna, and converts it into a digital signal that your computer can understand. So for this ADC here, we have two main things: the bit depth and dynamic range. The bit depth of ADC, in this case for the RTL SDRs, is 8-bit, determines how accurately the analog signal is converted. And 8-bit ADC can convert the signal into one of 256 different values, which is not as precise as 12-bit ADC that can differentiate between 4096 values. And we also have the dynamic range. The dynamic range of ADC tells us the difference between the smallest and largest signals it can handle. For an 8-bit ADC, like the RTL SDRs, the dynamic range is about 50 decibels. This means it can handle a wide range, wide variety of signal strengths, but it might miss some of the very weak signals, especially if there are stronger signals nearby. The maximum bandwidth that an RTL SDR can handle is 3.2 megahertz. This is specific to RTL 2880, RTL 2832U chip, which is most RTL SDR devices. However, depending on the performance of your computer, the most stable bandwidth is usually either selecting the 2.4 megahertz or 2.8 megahertz, because this matters here. So if you set the bandwidth too high on a slower computer, the device might not be able to keep up, leading to lost samples that can result in choppy audio or other performance issues. And the most SDR, most software that works with RTL SDR will let you choose your bandwidth. This setting is sometimes called the sample rate, for example in SDR++. While the bandwidth and sample rate are not exactly same, the context of RTL SDR, the setting the sample rate to 2 MSPS, which is megasamples per second, will give you 2 megahertz of bandwidth. But setting it to 2.8 MSPS will give you 2.8 megahertz of bandwidth. So if you are familiar with Nyquist theorem, which we will learn in next lectures more deeply, you might wonder how a 2 MSPS sample sample rate can result in 2 megahertz of bandwidth. So this is possible because the RTL SDR uses something called IQ sampling, which involves two ADCs, analog to digital converters, working together. So in simple terms, the bandwidth is the range of frequencies that you can see and analyze at any one time when using RTL SDR. So this RTL2832U dongles, the main component in the RTL SDR, are originally designed for use with the television equipment. So they have an input impedance of 75 ohms. So the most radio equipment used by amateurs and professionals operates with like 50 ohm cables, connectors, and adapters. So you might worry that this is a difference in impedance could cause problems, but the signal loss due to this mismatch is very small, like less than 0.2 decibels. This means it won't noticeably affect the performance of your RTL SDR. So the RTL, the R82 820T and its improved variant, the 820T2, are most commonly desired and purchased RTL SDR variants. The R820T2 is a newer variant of the R820T tuner. So here this green one I have here came with R820T2 model, which has better sensitivity compared to 820T, just T. And the E4000 used to be the most popular since they were first available, but Elonix, the manufacturers, has closed down making these chips, rare and expensive, but you won't find this E4000 chips. But if you would find that, it will be like pretty expensive. But other tuner variants are less common, especially online, but some compatible tuner variants can sometimes be found in local stores in Europe, European Union. So these tuners are not as common for a reason. They don't perform as well as the this R22 here. It's actually this one is R828D, but this one is R820T2 here, so it has better sensitivity here. So based on price and availability, currently I recommend this tuner here, because it's almost, I bought this from AliExpress for $21, but the other one I bought for $40. Like I could buy the two for the price of one here, but as I tried, like, it has better performance. And I also wonder what's specific. Yeah, these are almost same megahertz. And yeah, this is $20, this is $40. And while the RTL SDR offers best value for money, of course, there are like several more advanced SDR radios available that come with additional features. So these more advanced SDRs might include the front-end filters to help reduce interference from signals outside your desired frequency range. The larger ADCs, analog to digital converters, these improve dynamic range and sensitivity, allowing SDR to pick up weaker signals more accurately. And they might have wider bandwidth. This allows the SDR to process a larger range of frequencies at once. For example, for the HackRFs here, I have like 6 gigahertz, and they will have the wider frequency range. This expands the types of signals the SDR can tune into. And some SDRs can also transmit signals, not just receive them. So here I have the HackRF, which is frequency range of from 30 to 6,000, 6 gigahertz. The bandwidth is 20, ADC bit is 8, and it can both transmit or receive, but not at the same time. So HackRF is half duplex. You can buy the HackRF for original one for $300, $400, or even $600. But I bought this one from AliExpress for 150 United States dollars, and this one I bought for $105. This has the PortaPack installed on it, but I recommend this blackboard because the PortaPack installed in it. I will just show you my old broken HackRF right now. Yeah, that's the one I broke. So the USB ports broke easily. I think some capacitors died there too, because I can listen to like other signals, send them, but I cannot connect this to computer because of the some, I think some capacitors died here. So I will work through that. So I recommend that. So this installed with PortaPack comes with this green board, but I highly recommend if you see that if you are buying from the AliExpress, I highly recommend this blackboard. They are still they are clones of the HackRF, but as you know, HackRF is open source, so it is legal to buy one and use one. But they will have the similar performances as well, because they both use similar chips, but their design structure, the diagrams, is just little different. And we also have like FunCube, AirSpy, Mirrorx, SDR Play, which I don't have them right now because for this course and for the most purposes of this HackRF, for the most purposes of SDR, RTL SDR, you will just need RTL SDR or HackRF for transmitting as well. And these are, of course, the AirSpy, Blade RF. They are the expensive ones. For example, Blade RF, it just is around $800, like USRP. B200 is costs more than $1,000. So I highly recommend the HackRF if you have like bigger budget. But if you are on a budget, you can buy the RTL SDR. And for the reception only SDRs, there are several options that offer improved performance compared to RTL SDR. The AirSpy, this has better performance than the RTL SDR due to its improved ADC bit size and advanced RF design. And I can also recommend you the SDR Play. This uses the Mirrorx MSI 3101 chip, but includes switched first order filters for improved performance. And in the mid-high end of the SDR hardware, you will find HackRF, Blade RF, and USRPs. This HackRF is capable of both receiving and transmitting, but it can only handle one at a time. And Blade RF supports full duplex operation, meaning it can receive and transmit at the same time. And we also have the USRP, Universal Software Radio Peripheral, offers advanced capabilities. The B210 can receive and transmit in 2 different channels at the same time, but B200, this is a full duplex on a single channel. So thank you for watching. I hope this lecture got you informed for the main SDR devices and some terminologies. In next lecture, we will do another test with RTL SDR and to install drivers and things. So I'm waiting you in next lecture.
Hello everyone! Today we will go through the process of downloading and setting up
SDR++, a fascinating and fantastic software-defined radio application. Whether you are on Windows, Linux, or even a Raspberry Pi, I will guide you through every step. Now let's get started. Before diving in, let's briefly talk about SDR++. It's an open source cloud platform software designed for SDR enthusiasts. It supports a variety of SDR devices such as RTL SDR, HackRF, AirSpy, and more. So what sets SDR++ apart is its simplicity, versatility, and the fact that it's constantly updated. Now let's head over to SDR++.org, the official website for SDR++. And on the download page, you will see two options, the download manual and the download here. So when you go to download page, you will be redirected to here. And now you're seeing the nightly build and releases. In the releases, you can also see the release build. So the release version here, this is the stable version of SDR++, perfect for most users. And we also have the nightly build. This version includes the latest features and updates. While it's called nightly, it's still very stable. For this guide, I recommend using this nightly build to access the newest capabilities covered in this tutorial. Now, to download the nightly build directly, you can go to this release section here, show all assets, and choose the one that suits your operating system. Here it has Ubuntu, Windows, Android package here, Debian, macOS, and we can also download source code and build our own. Now for the Windows, we will download the zip file on nightly page. It's just 7 megabytes. And open the zip file here. Let's delete the old one. Yeah, open the zip file and let's go to documents and extract it. Now you can also choose the folder in this C disk, like here, paste it here, change the name to strpp, create the shortcut, here, and drag and drop it on the desktop so you can easily access it. And now, in order to run the SDR++, you don't, in Windows, you don't need to do anything. You just double click on it, click on run. Some command prompt will open and quickly it will close. It's now loading the dynamic libraries. Here we are. And we are done with installing SDR++ in Windows. Now you can run it, choose the device, and which we will do that later in this course. But now let's try to install it in Linux. And now we are on the Linux operating system here. First, we will check our system version. In order to do that, we will open the terminal, write lsp release A. Ubuntu release name is 24.10, codename Oracular. Now we will open our browser. strpp.org, download, and here we will select the Debian SID. It's not downloading. Open the terminal again, cd to downloads. Now we will sudo dpkg strpp, enter password, and here we had encountered some problems. Some of the libraries is not installed, so we need to install these libraries one by one. Sudo apt install lib. Yep, and that's it. It's installed. STR++. And here we are. We installed STR++ in Ubuntu. And yes, STR++ is available for Android as well. Now you just need Android 9.0 or later and OpenGL 2.1 or higher. So you can check this by installing OpenGL extensions Viewer app from the Play Store. And currently the app for the Android here supports some SDR devices and protocols like AirSpy, HackRF, RTL-SDR, RTL-TCP, and SDR++ server as well. Now, but you can run the Pluto SDR as well, but just network only. So final tips for this lecture is you can use Dragon OS. So if you're looking for a dedicated operating system for SDR, try Dragon OS. This is a Ubuntu-based distro preloaded with SDR++ and other SDR tools as well. You can also see this. You can install a Raspberry Pi. And the nightly builds ensure you have the latest features. Now you can also check the nightly build page in GitHub for regular updates. Hello everyone, I'm Typhoon, and today we are diving into the process of setting up your SDR receiver and selecting it as a source in SDR++. So if this is your first time using SDR++, don't worry, I will walk you through every step, explain why things work the way they do, and throw in a few tips to make the process smoother, whether you are using Windows, Linux, or Android. By the end of this lecture, you will have your SDR receiver ready to explore the world of signals. So, let's get started with the first task, installing your SDR receiver. These devices, often called dongles, are small but mighty tools that let you explore the radio spectrum, from FM radio to air traffic communications and beyond. Why you need to know about SDR compatibility? SDR++ supports a wide variety of SDR receivers, and the setup process is usually straightforward. However, every receiver is a little different. Now, here's what you should know. Drivers first. So before anything else, you will need to install a appropriate driver for your SDR receiver. Most manufacturers provide these on their websites, so look there first. But in this case, of course, SDR++ has pre-installed drivers as well, like the DLL files. Here you can see the HackRF, libusb, and so on. So in the 90% of the cases, you don't need to install drivers if you are with SDR++. And if you don't have the driver, once the driver is installed, connect your SDR receiver to your computer, and SDR++ should recognize it automatically. But don't worry if it doesn't. We will troubleshoot that in a moment. Here you can see I have HackRF connected here. So there's a special cases to consider. For Linux users, Linux has built-in support for many SDR receivers, but occasionally you will need to install additional modules or drivers. So if your receiver isn't detected, try adding support through SOAP SDR. For example, this SOAP SDR acts as a middleman between SDR++ and your hardware. So you can do like SOAP SDR, sudo apt install, sudo SOAP SDR, sudo if you are using the RTL SDR like that. But if you are using the HackRF, sudo apt install HackRF. So this will install the Linux drivers for your RTL SDR receiver or other SDR receivers here. But for HackRF, by the way, HackRF is also a transmitter. Now, to check if HackRF works, you can write this command after installing, and this will show you information about HackRF drivers and the device here. Now you can also, as I said, check the manufacturer's website. For example, some advanced receivers like AirSpy or SDR Play might need their own configuration tools or special drivers. Always check the documentation provided by the manufacturer here. And this is their websites if you have one of this. But in this case, we will use HackRF and RTL SDR. Now, if your receiver isn't working right away, don't panic. Double check that you have installed the correct drivers and that your operating system recognizes the device. And here, as you can see, Universal Serial Bus devices, I have HackRF 1. And now let me connect the RTL SDR right now. Here. Device Manager. Now it should be somewhere here, but it might be unrecognizable like the balcony interface. This might be it. But the thing is, the SDR++ will still recognize our RTL SDR. And here you can see no serial, generic RTL 2832 UOM here. And also let's connect. I have another RTL SDR, the one in their official website, rtlsdr.com, V4, model V4. You can see the picture. And here now I have connected 3 SDR devices. Click on refresh. Run. You can see I have two RTL SDR devices and one HackRF. Now let's connect my another HackRF. And here I have also connected my other HackRF. Now let's click on refresh or open SDR++ again. Here. Now you should see it. Now you can see they have different IDs. Here they both work. And here we have successfully connected two HackRFs and two RTL SDRs to our SDR++. And now that your receiver is connected, you can start and do everything with your SDR++, your gateway to the radio spectrum. Now, SDR++ work on multiple platforms, as you learned that in previous lectures. So if you are using SDR++ on Android, make sure to connect your SDR receiver before opening the app. So unlike the desktop systems, Android doesn't allow the application to detect new hardware after it's already running. And for Windows, Linux, or macOS users, if your SDR receiver isn't plugged in when you start SDR++, just click the refresh button and the software will scan for connected devices. And to launch SDR++, on Windows, you can locate the SDR++.exe file in the folder where you installed SDR++. This is actually SDR++ is just like a portable application, so you don't need installation process for this. You can just unzip it and get started by working. But you can also open the folder after unzipping and choose the SDR++ strpp.exe file in the folder. And on Linux, you will typically find SDR++ in your system application menu after installation. And here you can go to open terminal, strpp, and it will start here. And you can also go to system application and write SDR. And here we can also run this from here. So what happens when you launch SDR++ for the first time? So when you open SDR++ for the first time, the interface might look overwhelming, like there's so many things to control here, but don't worry, that's normal. For now, we are focusing on just one part for this lecture, which is the source menu, which is where you will select and configure your SDR receiver. So with SDR++ open, the next step is to select your SDR receiver as a source. This tells SDR++ which device to use for receiving signals. Now look for the source module tab in the main menu. So if you don't see the menu, click on the small icon in top left corner to toggle it on. By default, menu is located on the left side of the interface. And now click the drop down menu in the source module. Now look here for receiver in this list. So you will usually see its model name like RTL SDR, HackRF, Blade RF file. You can also use the file that we did in previous lectures. So if you don't have an SDR here, you can use the file. And here, yeah, we have Herm, Slime SDR. We can also use the network, Bluetooth SDR, RF space, RTL SDR, which was and the most important, the RTL SDR and HackRF is here. And if you don't have the SDR at hand, I strongly suggest you to buy one. But there's still another option. You can use the file. Now you can download the WAV files from internet. That's pre-recorded SDR images, and click on this, open, and here you can see we can see this spectrum. So you can play with it if you don't have an SDR device at your hand. But luckily we have one, and not one, like I have 5 SDRs for this lecture. And if your receiver doesn't show up, hit here, let's actually set RTL SDR. Now, if your receiver doesn't show up here, hit the refresh button to rescan for devices and double check that the driver is installed correctly and that receiver is securely connected. I have 2 HackRFs. Let's see, system devices, and so on. Yep, here. Now, here, let's actually open the SDR right now, select our SDR receiver, whether it's a RTL SDR, HackRF. Now let's go with RTL SDR, but yeah, I have the antenna on HackRF, first HackRF here. So we will choose the HackRF. Broadcast, shortwave broadcast. My mouse again. Here. You can see there's a names for the each spectrum. Here. Now we are in the FM broadcast. Here, let's zoom in. Here. Minute. Yep, that was it. Now, here you can see I have 2 HackRFs connected. Now, let's listen to FM broadcast. I will actually disconnect other SDR devices. And now I have disconnected other SDR devices. Now, we have just one HackRF and one RTL SDR here, and our source tab should be updated. Here I have just one HackRF and I should have one RTL SDR here. Now, before wrapping up, let's take a closer look at the source menu and its options. Now, the source menu adapts to the SDR receiver you are using. For example, an RTL SDR dongle might display different options than HackRF. Here, you can see it displays different options, or an SDR Play device. So some options in the source menu are only available when SDR++ isn't actively receiving. You see here, it's grayed out. If a setting here like this is grayed out, simply stop the receiver, make your changes, and then restart it. SDR receivers provide various methods to control the gain applied to incoming radio signals. Now, the available options include main gain control, automatic gain control AG, C, or combination of both. Understanding how to configure these settings is essential for optimizing your signal reception. Now let's delve deeper into each aspect to get a more comprehensive understanding. Manual gain control allows you to adjust the gain manually by increasing or decreasing the amplification applied to the signal. This setting is crucial for fine-tuning your reception quality and is particularly effective when dealing with a variety of signal strengths. The gain is measured in decibels and is typically adjusted using slider or a control bar. In SDR software, for example, you can drag a blue bar to the right to increase the gain or to the left to decrease it. Let's actually increase our saturation a little bit, and here. Now our gain is increased, decreased. Now get started by initial setup and begin by tuning to a strong and clear FM broadcast signal. Now let's get started. And also, by the way, if your audio is grayed out, simply click on the radio, enable the checkbox on the right of the radio box, and you will hear the audio. Now let's begin by tuning to a strong and clear FM broadcast signal. Now we will adjust the gain until we achieve a signal that is free from noticeable hissing or static. Also increase this a little bit. And yeah, like this, low pass enabled here. Now, interestingly, reducing the gain rather than increasing it can sometimes improve signal clarity. This happens when excessive gain amplifies unwanted noise along with the desired signal. So, as you gain experience with your SDR receiver, you will encounter weaker signals. Adjusting the gain for these cases requires a bit of patience and experimentation. Focus on achieving the best signal-to-noise ratio, SNR. So, which is the balance where the desired signal is much stronger than the background noise. This adjustment is particularly useful for decoding faint transmissions like amateur radio and distant broadcasts. Additional control. So some SDR receivers also offer an intermediate frequency IF gain control. So this setting adjusts amplification at a different stage in the signal processing chain, allowing for even finer adjustments. Experimenting with IF can help you overcome specific challenges, such as strong nearby signals that interfere with weaker ones. So automatic gain control simplifies the signal adjustments by dynamically balancing the signal levels. This is especially useful when the signal strength varies frequently, such as during mobile operations or when monitoring fast changing frequencies. So the AGC system, the automatic gain control system, automatically amplifies the weak signals while reducing overly strong ones to ensure the output remains within a comfortable range. This reduces the need for constant manual adjustments. So depending on your SDR receiver, you might have several AGC settings. So for example, fixed levels, devices like AIRS by HF Plus Discovery provides preset automatic gain control levels. Off, low, high, like that. So allowing you to select how aggressively the receiver balances signal levels. And advanced SDR receivers may allow you to specify parameters like attack and decay times, giving you a greater control over how quickly automatic gain control responds to changes in signal strength. And keep in mind that enabling AGC often disables manual gain control. So choose the mode that best suits your use case. AGC for dynamic environments and manual gain for precise tuning. So the sample rate also we need to consider is the sample rate. Sample rate determines the width of the radio frequency spectrum that your SDR receiver can process and display at any given time. This parameter significantly influences both performance and usability. Now you can see here we can also set the sample type and container radio and so on. And high sample rates, as you learned in previous lectures, devices like the SDR Play RSP1A can display up to 10 megahertz of spectrum, providing a wide view that's useful for monitoring multiple signals or identifying signal patterns. And lower sample rates, devices such as AirSpy HF offer narrower bandwidth, such as 768 kilohertz. While this might seem limiting, it often improves performance by rejecting strong, unwanted signals from nearby frequencies. So the higher sample rate demand more processing power and may cause glitches or interruptions on less powerful computers. So if you experience performance issues, reducing the sample rate can help, may offer like stabilize your system. And for instance, the RTL SDR dongle typically supports, this RTL SDR dongle typically supports up to 2 megahertz of sample rate or bandwidth, which is sufficient for most hobbyist applications. In contrast, professional grade devices may offer much higher rates for advanced use cases. Now, also we need to consider the compatibility here. So not all sample rates listed in SDR software are supported by every SDR receiver. Always refer to your receiver specifications to ensure compatibility. Bias T. A bias T feature allows an SDR receiver to supply power through its coaxial cable to an external RF amplifier or active antenna. This capability is indispensable for enhancing reception in setups that require additional amplification, such as long-distance HF or VHF, UHF operations. And before enabling bias T, consult your receiver's manual to confirm compatibility and power requirements. So ensure the attached amplifier or antenna is compatible with the receiver's bias T specifications, and verify the receiver's bias T provides adequate power for the external device. Using an incompatible setup can damage your SDR receiver or connected equipment. So by understanding and effectively managing these features, manual gain, AGC, sample rate, and bias T, you will be well equipped. To optimize your SDR receiver for a variety of signals and operating connections and conditions. And now let's dive into a neat feature that can significantly expand the frequency range of your SDR receiver can handle: offset timing. Essentially, you can use additional hardware to shift a specific range of frequencies into the SDR receiver's accessible range. To activate or deactivate this feature, you just need to check or uncheck this offset timing box once you have set the correct offset mode. So we don't have the antenna for RTL SDR. I haven't connected antenna for RTL SDR, so we will go back to HackRF. Yeah. And yeah, now, for example, we can also consider the practical example, like let's say your SDR receiver is designed to cover VHF from 30 to 300 megahertz and UHF frequencies 300 megahertz and above, but you're interested in listening to HF from 3 to 30 megahertz or MF from 300 kilohertz to 300 megahertz. So this is where a converter like the Hamitop comes in handy. It's an up converter that raises the frequency of incoming signals to match the SDR's range. So for example, it shifts signals by 125 megahertz. So if you want to listen to 7 megahertz signal, you'd tune to your SDR to 132 megahertz. But of course, you want the display to show the actual 7 megahertz frequency you are listening to, right? So to make that happen, you will need to select the appropriate converter type in the offset mode settings. For HackRF, we don't have the offset mode, but for RTL SDR, you can say offset tuning. Now, there's available converters for these offset modes like Spyward or Hametop, D-Key 5AV X-band converter, Q-band satellite, LNAs, and which used as down converters. Now, let's talk about IQ correction. Now, let's talk about this IQ correction here. So, this is an important setting that helps fix issues with your SDR hardware that might cause unwanted effects, like the DC spike on the frequency display. It can also help with imbalances that impact things like audio quality or data reception. Now let's go back to HackRF and enable IQ correction. Disable it, enable it. Now you see the spike here? So this helps with the DC spike appearing on this frequency display. It can also help with, as I said, imbalances that impact things like reception and audio quality. And to adjust it, you simply tweak the value until the spike disappears or moves outside the range you are tuning to, called VFO's passband. And next up is decimation. So you actually learned this decimation in our previous lecture, but this setting basically reduces the number of samples taken from the incoming radio signals. A radio decimation of 2 means the SDR takes 1 sample every 2 incoming signals, while 4 means 1 sample for every 4 signals, and so on. So you have actually learned that decimation in our previous lecture. We have separate lecture about the decimation captured here. So if you forgot, I suggest you to watch that lecture again from beginning to end. So to summarize, offset tuning allows your SDR receiver to cover a wider frequency range. IK correction fixes display and signal imbalances, and decimation helps optimize your SDR's dynamic range, but with some trade-offs in frequency width and signal quality. Adjusting these settings carefully can make a big difference in your SDR experience. My name is Typhoon, and I'm waiting you in next lecture. Hello everyone, I'm Typhoon, and I am thrilled to welcome you to today's lecture. In this lecture, we are diving deep into SDR++, one of the most versatile and user-friendly software-defined radio applications out there. Specifically, we will focus on navigating the main screen and mastering its key controls. By the end of this whole section, you will not only understand what each part of the interface does, but you will also gain practical tips on how to use them efficiently. This will set the foundation for smooth and productive experience with SDR++. So let's get started. We will start by understanding the top bar, the dashboard. The top bar in SDR++ acts as your control hub. It's packed with essential tools you will use constantly. Now let's go over its components one by one. So we have a start and stop toggle. This toggle is your gateway to starting and stopping the receiver. It's simple. Click the play button to begin the receiving signals, and once it's active, the button will change to this stop button. Clicking this will stop the receiver. So think of it like the on-off switch for your radio operations. Volume slider. This volume slider here allows you adjust the audio level quickly and precisely. You can drag the slider to increase or decrease the volume. If you prefer quick actions, you can simply click at the desired level on the slider bar. Now, clicking the speaker icon also will mute or unmute the audio. So if you're working with multiple VFOs, variable frequency oscillators, this slider controls to volume of the selected VFO. So you can also adjust the volume for each volume variable frequency oscillators separately using individual controls. Frequency selector. The frequency selector is where you will see the frequency your receiver is tuned to, displayed in hertz. It's an intuitive tool for making precise frequency adjustments, which we will explore in detail later. And we also have the SDR meter. This is a signal to noise ratio meter. Gives you a visual indication of the strength of your signal relative to the background noise. So if we go to like this, as you can see, this will change over time. And while this signal to noise ratio meter is accurate for general use, it's not calibrated S meter like you'd find on professional transceivers. So it is optimized for a wide range of SDR hardware configurations. So think of it as a guideline rather than a precision tool. Now let's move on to the menu button and the side menu, which house many of the SDR's powerful features. The menu button is located on the top left. Clicking it toggles the side menu, which contains all the available modules and settings. So you can show or hide the side menu depending on your needs. Hiding it gives you more screen space for the spectrum display and waterfall, making it easier to analyze signals visually. When the menu is visible, you will find all the modules listed in an organized layout. Also, you can adjust the order of these modules like this by simply dragging and dropping them. This customization ensures that the here let's go back and here. So this customization ensures that the most frequently used modules are always within easy reach. The side menu modules include tools for frequency management, audio control, signal processing, radio settings, which we will cover some of these modules in depth in future lectures. But for now, just know that the side menu is a control panel for everything SDR++ can do. And let's revisit the volume control for a closer look at how it works. So to increase or decrease the volume, drag the slider or click on the bar at the desired level. Clicking the speaker icon will mute the audio. And we have the multi-VFO volume management. If you are using multiple VFOs, the volume slider adjusts audio for the active VFO. To adjust audio for the other VFO, select the desired VFO and use its specific control. And this signal to noise ratio is one of the most critical metrics in radio communications. It helps you identify strong signals and filter out noise. The meter here measures the relative strength of the signal you have tuned compared to the background noise. Like if you go to there, you can see it's increasing, decreasing, increasing, decreasing, and so on. And now let's explore the frequency selector, an essential tool for finding and locking into signals. Now, the frequency display shows the current tuning frequency in hertz. It's broken down into decimal points for clarity. For example, in 90.900 like this. This means here megahertz. This can also be written like this. We actually covered this in previous lectures, but I will revisit that again. So here, 9 this hertz, like 90 million 900,000 hertz means 90.9 megahertz. So this can be written as like this. And you can tune your SDR in several ways in SDR++. You can also tune your SDR in several ways. You can hover over a digit in the frequency display and use your mouse scroll wheel to adjust it up or down. You can click or tap the upper part of the digit to increase it by 1, or the lower part to decrease it. And to input a specific frequency, click on the first digit you want to change and type an entire frequency like this. Now that's it. You can also use the spectrum display or waterfall, and you can hover over to the spectrum display or waterfall to use the scroll wheel to adjust the frequency. The adjustment interval is determined by the snap interval setting in the radio menu. You can click on a signal of interest like this in the waterfall to tune to directly, like this, here, here. And remember, SDR++ is an incredibly powerful tool, and mastering these basics will make exploring its advanced features much easier. In our next lecture, we will dive deeper into specific modules and advanced settings to further enhance your SDR experience. Thanks for joining me today. If you have any questions or want to explore specific topics, feel free to ask, and see you next time. The display menu in SDR++ is your command center for configuring the appearance and behavior of the spectrum and waterfall displays. These settings allow you to fine-tune how data from signals is visually represented, making it easier to analyze and track transmissions. Now let's understand what is FFT and why does it matter. Actually, you learned that in previous lectures, but before diving into these settings, it is important to understand the core technology behind visualizations you see. The fast Fourier transform, FFT, is the mathematical algorithm that SDR++ and GNU Radio we used earlier uses to convert raw radio signals into graphical data you see in the spectrum display and waterfall. So think of it as the bridge between invisible radio waves and the beautiful, colorful visualizations that make signal analysis possible. Now, you can show the waterfall here. The simple toggle enables and disables waterfall display. When it is off, you will only see the spectrum display, which can be useful if you are focusing on solely on frequency amplitudes. And we have also full waterfall update. Let's see it. Now, the entire history here of the waterfall display is updated whenever you adjust viewing parameters such as zoom or min max values. So let's try it without that and you will see the difference here. So this feature ensures continuity, helping you review previous waterfall activity in its entirety after making display adjustments. Here, you can see it is weird. I suggest you to enable that. And we also have this FFT hold option here. This feature creates a trace line across the spectrum display that indicates the highest signal level reached over time. Here. It is like a signal strength tracker that doesn't immediately fade. Here. And we have also log menu order. The feature logs the position of the menu sections to prevent accidental rearrangement. You can see we can change this. So on Android devices, this is particularly useful when scrolling to avoid unintended menu moves. If you try to move a menu section while this is active, SDR++ will display an error message in Android. We also have the high DPI scaling, this one. This adjusts the size of controls, borders, scroll bars, and text in SDR++. This is invaluable for users with high resolution monitors or small displays like smartphones or tablets. So let's try to change it to 200, and this is, as you can see, the restart is required. Let's restart it. And here, as you can see, it is like magnified, but in our case, we don't need that. So we will go back to 100%. So it in its own size. Restart it. And here we are. And we also need to set the parameters for fine-tuning FFT here. The purpose of this FFT size here is this determines number of data points shown in the spectrum and waterfall displays. So the trade-offs, there are the trade-offs for the higher values. Let's choose this. You can see the higher values show greater resolutions. You can see the resolution is much greater than this one here. But of course, you don't want to use 1024 FFT. I always recommend it to use integer. And the higher values show greater resolution, making it easier to detect weaker signals, but require more processing power. And for the lower values, like 2048, reduce CPU load, which is ideal for slower computers, but may result in reduced detail. So let's do it with the You can see the audio quality doesn't affect it by changing this one, but FFT is just visualizing this. And let's go back to default value, run it again, and as you can see, it works. And more about this FFT window, we can select rectangular, Blackman, and Nuttall. This applies specific algorithms to the data before running it through the FFT. These algorithms affect how signal peaks are displayed. So we have three options here, as you see, rectangular, Blackman, and not all. So rectangular provides the simplest processing, offering sharp but less smoothed peaks. And as you can see here, it is selected not all by default. And we have also Blackman. This adds smoothing for a more visually pleasing display, and Natal is introduced in version 1.1.0. This is now default choice, balancing clarity and accuracy. And we also have here color map under the FFT window. The color map defines the colors used to represent the strength of signals in the waterfall. You can choose from various presets to match your preferences or enhance visibility. Now we have classic, classic green, electric, and so on. Now let's set the classic green. You can see the color is changed. Electric. This. Grayscale. Magma. So you can play this with this later, WebSDR. And we will use classic for now. And I also have another thing to talk about in this lecture is something simple yet incredibly handy. We can customize our VFO colors. So imagine you are monitoring multiple frequencies simultaneously. Having each VFO in a distinct color isn't just aesthetic, it is functional. Now you can set up, now you can click the colored square next to the VFO you want to change. And here a color picker tools here pops up, letting you choose your favorite shade or input a specific hex code if precision is your thing. And you can also need a quick reset. So SDR++ has you covered with this clear all option. So if you prefer to let the software decide, you can also click auto color, and SDR++ will automatically assign unique colors for each VFO. So this feature keeps things organized, making it easier to differentiate between squares at a glance. Now let's talk about band plans, the roadmap for navigating radio frequency allocations. Different countries and regions have unique band allocations, especially in this VHF and UHF ranges. For example, the 60-meter emitter band differs worldwide, and some regions include 4-meter, which is 70 megahertz amateur band, which isn't available everywhere. And SDR++ simplifies this complexity by providing preloaded band plans for various regions, like the UK and USA. These band plans act as a visual guides, highlighting frequency blocks for radio amateurs, broadcasters, and even niche users like HF air and marine allocations. And by default, SDR++ opens with a worldwide band plan. But if you are operating in a specific region, you can switch to localized band plan using this drop-down menu. The band plan can be displayed at the top or bottom of your spectrum monitor, depending on your preference. You can see band plan will change. Russia, Netherlands, general. And you can also customize this band plan, like you can edit the band plan files located in the SDR++ directory in the res folder, band plans. And here you can see the band plans. These are the JSON files, are straightforward to modify. Just ensure your frequency here. Entire entries are in order and follow the existing format. So if you are feeling adventurous, you can even create new allocation types or tweak the colors by editing this config.json files. And now we move on to the heart of SDR++ on the radio module. This is where you choose the type of modulation to receive, such as AM, FM, or sidebands. You can temporarily disable this module by unticking this text box next to this radio tab here. So while SDR++ will still show the spectrum and the waterfall, it won't send any audio to your speakers. Now let's break down the available modes and their uses. We have the NFM. This is narrowed bandwidth. Because we hear the FM radios, but not like where like we hear this in FM. So narrowband FM. This is your go-to for citizens band, business radio, and amateur radio above 27 megahertz. It is also used for VHF, UHF data transmissions like DMR, NO-AA, APT, and POXAC. The default filter is set to 12.5 kilohertz. And we also have the VFM here. This is the wide band FM. This is perfect for broadcast FM broadcast stations in the 87-180 megahertz range. You can toggle stereo sound and adjust the emphasis for audio clarity. And the default filter is 150 kilohertz. We also have this AM. This is amplitude modulation. This is found in a long wave, medium wave, and short wave broadcast, as well as citizens band and air band communications. The default filter width here is 10 kilohertz. And we also have the DSB here. DSB is a double sideband, typically used for dual sideband suppressed carrier transmissions. The filter width is 4.6 kilohertz by default. We have USB and LSB. This is upper and lower sideband. USB dominates amateur bands above 10 megahertz and data modes across all HF bands, while LSB is standard for amateur bands below 10 megahertz. Both modes have a default filter width of 2.8 kilohertz. And we also have the RAW. This outputs the intermediate frequency IF as audio, separating I and Q branches into left and right channels for advanced analysis. And we also have the CW continuous wave dedicated to Morse code transmissions. This mode uses a narrower filter of 200 Hz for precision. The default filter widths are optimized for each mode, but SDR++ gives you full control to adjust them. For instance, you can use the minus and plus buttons or type in a custom value to modify the width. Alternatively, you can drag edges of the VFO band directly on the spectrum display. So these adjustments can make audio more pleasant, reduce interference from adjacent signals, or ensure you are capturing the full bandwidth of a data transmission. We also have the snap interval. Snap interval determines the frequency steps when you are tuning. For FM radio, you typically set this to 100 kilohertz, allowing you to jump neatly from 93.1 megahertz to 93.2 megahertz, and so on. So you can see. So each mode retains its snap interval setting. So adjustments for USB, for example, won't affect NFM or other modes. On FM signals here, VFM and NFM, high frequency audio is emphasized during transmission and de-emphasized during reception. This enhances clarity and reduces noise. So for example, Europe uses 50 microsecond de-emphasis setting, while the United States uses 75 microseconds. So you can toggle these options, this feature, or fine-tune it to match your region's standard. And finally, we have to learn about the squelch. Let's discuss the squelch. A feature can save your ears and sanity. The squelch mutes audio until signal exceeds a specified threshold, cutting out unwanted background noise. Now, to set it up, tick the box here in squelch. Drag the marker to the right until the noise disappears, and fine-tune the setting to ensure that the only desired signal breaks through. Here, this is how squelch works. And keep in mind that noise levels vary across frequency range, so you might need to adjust squelch levels as you explore different bands.